All right, it's 9 o'clock almost, so we better get started. Before we proceed with the keynote, we have Frank Tip, who is the General Chair of SPLASH 2026, who is here to introduce to us what we are to expect in a year. Please go ahead, Frank.
Thank you, Alex. So next year, SPLASH will be in Oakland, California, in the United States. And before I tell you a little bit more about the event, I have a short video that the Oakland Tourists Bureau provided to us, and we will take a look at that first.
Our place in the world and our ability to make it better. We've always been ahead of the curve and are proud to be a destination with experiences as diverse as our culture. Our vibrant, colorful city has so much to offer, including a great location with access to everything. The town is a wonderful, welcoming choice for business or pleasure. It's where you can be in the heart of bustling downtown, vibing in uptown, strolling along the water's edge, or nestled among the redwoods, all within 20 minutes. It's not just about who we are, it's where we are. So come over and see things from our side. They say location is everything, and Oakland has one of the best in Northern California. With easy access via plane, train, automobile, or ferry, Oakland is just 20 minutes from San Francisco, 40 minutes from wine country, and 50 minutes from Silicon Valley. However you choose to get here, once you arrive in Oakland, there are amazing places to stay. With 40 hotels ranging from convention properties to boutique and luxury hotels, Oakland has 5,500 guest rooms just waiting to welcome you. Oakland is an ideal place for meetings and events with an array of venues that accommodate 15 to 50,000. From traditional settings to unique hotspots, whether indoors, outdoors, out of this world, or out of the box. In Oakland, there's something for everyone to enjoy. There is so much to see and do in the town. Oakland is home to fun, engaging group activities on the water, on foot, on tap, at the game, in the kitchen, in the air, and in the groove. Explore immersive arts and cultural experiences, our award-winning culinary scene, vibrant bars, and nightlife. With all that Oakland has to offer, the successful meeting and event possibilities are truly endless. So come over and see things from our side. You'll really be glad you did. We look forward to welcoming you.
All right, so SPLASH 2026. The venue will be the Marriott Hotel in downtown Oakland. For the hotel, we have a negotiated rate of $225 plus tax per night, which is quite good by California standards. It's a very nice 4-star hotel, very centrally located, and it's right across a BART stop. BART is the local public transport. So you can get to the hotel very easily by public transport from San Francisco Airport. SPLASH will be co-located with ISTA next year. ISTA is the International Symposium on Software Testing and Analysis. It is somewhat similar in size to SPLASH, and the focus is on testing and analysis. It's one of the main software engineering conferences. And we will be organizing several of the tracks that are associated with these conferences jointly. So there will be a joint doctoral symposium, joint workshops. There will be a summer school with tutorial-style talks on topics that you might want to learn more about. And we will have a large joint industry track rebase. Here's what the schedule tentatively looks like. It runs from Sunday, October 4 until Friday, October 9. Day 1 will be the doctoral symposium, PLMW, and some workshops. Then the OOPSLA research papers track will be Monday, Tuesday, Wednesday, and ISTA will be Wednesday, Thursday, Friday, so there will be one day of overlap. Onboard will be on Monday and Tuesday, and the industry track will be Monday through Wednesday, and the summer school will be Monday and Tuesday, with workshops throughout the entire week. This is the organizing committee. All the committees are in place. So we have obviously the research papers, doctoral symposium rebase. I'll let you take a look at the webpage later so you can learn more about this if you're interested. For research papers, we will follow largely the same process as this year. So there are 2 submission deadlines. The round 1 deadline was just passed, and we had a record number of submissions. The round 2 deadline will be March 17 next year. The possible outcomes of the when you submit a paper are basically the same as this year, except that we merged the conditional accept category with the other categories, minor revision and major revision. And very importantly, we will continue the reserve reviewer system. This is a mechanism we put in place to handle the fact that the number of submissions has been skyrocketing. So if you submit a paper, you are likely going to be asked to review 1 or 2 papers as well. Lastly, I wanted to mention that we will do a sick plan papers track. And that means that if you have a paper that was published at a sick plan conference in the past 12 months before SPLASH'26 takes place, you can submit a talk proposal if you haven't presented your paper before. And this is a way to provide authors who are maybe not able to leave the US for SPLASH'25 to give their talk at SPLASH'26 instead. And similarly, you would be able to present an unpresented POPL or PLDI paper at SPLASH. And with that, I will turn it over to Alex.
All right. Yep. Oh, yeah. Thank you very much for introducing 2026 SPLASH. And without any further ado, there is just one more thing. We convinced Ilya about a year or so ago to do the SPLASH together with ICFP, because I knew him for a long time, about 15 or more years, when I first met him at an ECOOP conference where he asked me, oh, how do you do them PhD somewhere? And I helped him set him up. We've been sort of friends and worked together ever since. This is the largest SPLASH we ever had, and I think it's probably the best SPLASH we had in the last 15 years since the SPLASH started in 2010. I don't know if people enjoyed that. During that time, he had to deal with ICFP, which has its own quirks, and the SPLASH, which has its own quirks. And throughout that, he had to basically bend people to, follow the rules and things that happen in a very, very uncoordinated way. I had to listen to his messages almost probably hourly for the last year and a half. And some of you may know he's a bit of a Futurama fan, so the number of memes I've seen on the theme of Bender and others is probably more than I ever wanted to see in my entire life. So as a result, on behalf of a SPLASH committee, we decided to give him a special trophy for the Ilya Sergey, the most bendable SPLASH ICFP General Chair. And we'd like to thank him for making this event happen.
Thank you.
Right.
Thank you.
Thank you very much.
Thank you.
And I know Ilya is wondering what the emergency was that I called him up for. Ilya, I have good news for you. There is no emergency. I don't think you folks understand how much he has done. Those of us behind the scene, everybody who's behind the scene is nodding their head saying like, yes, you do not understand how much he has done. Like he wanted to do ICFP and somebody said, we're gonna have you do SPLASH as well. And the poor man just said, okay, I guess. Ilya, thank you so much. Thank you. Okay, and it is my immense pleasure to introduce today's keynote speaker. So I could do the usual thing. I believe Frank went to college at some point. He might have gotten a degree, et cetera, all the usual stuff. But I thought I'd actually say something a little bit less formal about Frank. You know, we all know that there's this notion of a full stack developer, right? And a full stack developer is somebody who can do like both Java and JavaScript, right? Frank has a rather different view of the stack. Because if you go through Frank's papers, you go through his history, Frank not only knows everything down from the level of bits and packets and, you know, things of that nature, all the way to category theory, okay? That is a full stack, all right? And I not just say knows in that he can talk about it. He's got like non-trivial papers, like really amazing papers on it. And he does really great research. I like to think informed by all of his background in theoretical CS and everything else in programming languages, but actually helping us secure the systems that we work with on a daily basis. So it's an immense pleasure to have Frank with us today. Thank you.
Thank you. Thank you so much, Sriram, for that very nice introduction. It's a great honor and a great pleasure for me to be here and have the opportunity to give this talk at OOPSLA. So thank you, also the audience, for being here. So I want to talk today about confidential computing. And what is confidential computing? Well, it's certainly something that's gathering a bit of industry attention these days. So I have a quote here from Mark Russinovich. He's the CTO of Microsoft Azure, the cloud branch of Microsoft, and he says, confidential computing is set to redefine our expectations of data safety and privacy. That sounds good, right? And it's not just Microsoft. If you look at the Confidential Computing Consortium, that's an organization that promotes the development of this technology, all the big tech companies are there, hardware and software, right? So what is it about? Well, roughly speaking, confidential computing is an umbrella term. It means different things to different people. I'll give my definition later in the talk. But the central idea is we want to protect data while it is being computed on, while it is being used. We want to protect data in use. And this is not only gaining interest in industry as we speak, but it's also something that builds on a very long line of research in system security. I think many of you will recognize at least some of the terms that you see on the slide there. Well, these are all enabling technologies for confidential computing, and they've been worked on in the systems security research community for decades. So there are two big schools, two lines of thought. There's the crypto-based approach to confidential computing, and they say, don't trust anything about the platform on which you want to do your computations. You have to anchor your security in cryptographic assumptions. And then you have to go to techniques like fully homomorphic encryption, secure multi-party computation, and so forth, that are quite performance costly. You'll slow things down. There's a second line of thought, the second school, that's hardware-based confidential computing, and they say, well, maybe you can trust a small part of the platform on which you will be computing. Maybe a small part of the hardware, maybe the CPU package, the chip that actually contains the CPU, maybe you can trust that that is not being under the control of the attacker and so forth. And if you want to do that concession, you can kind of gain a lot in terms of performance. So that's what I want to focus on for this talk. So my scope for this talk will be hardware-based approaches only. So this will be about hardware-based confidential computing. What is confidential computing hardware, and how can we build secure software stacks on it? So that leads me to a structure more or less like this. I will spend quite a bit of time on defining what confidential computing is exactly. So what exactly is the objective here? What do we want to get at? And once we understand that, we look at how to break that objective and then maybe fix it. Right? And one of the key points I want to make, I think in doing fixes, the OOPSLA community would be very well placed to help, and I'll try to explain that towards the end of the talk. Okay, so what is confidential computing? So I'll actually define what a confidential computing platform is. And a computing platform is very simply something on which you can launch programs. And it will be useful later on, bear with me on that, to split the programs that we want to run in two parts. A public part that contains at least the code, so think of it as a public executable, and then the confidential data that we want to compute on. And if you do that split, then starting a program will take two steps. You first launch this public executable, turn it into a process, or you take a virtual machine image and turn it into a virtual machine instance. And then you need to provision it with the confidential data it should compute on. So we split this in 2 steps for reasons that will become clear later. I say program here. What is such a program? So there are actually confidential computing technologies for all kinds of granularities of programs, ranging from a single library, a DLL, all the way to a full virtual machine image. For this talk, it doesn't matter too much. So you can have in your mind an executable launching into a process or a virtual machine image launching into a virtual machine instance, and both mental models are fine. It'll also be useful to have a couple of example programs with confidentiality requirements in mind. I'll use 2 examples that I refer back to a couple of times in the talk. One is a public web server, so very little confidential data, because of course the code is public, Apache for example. All the data, you serve it on the web, so it's public, but you still need, for example, a TLS key to authenticate the domain that you are serving the data on, for example. So you have a small amount of typically cryptographic key data that's very confidential. So preferably not a single bit should leak. And this is representative of a larger class of applications whose main confidential data is cryptographic key material. Then there are other applications who work on big data, and I have as example a medical image processing application that scans medical images for markers for a disease, for example. These work on huge amounts of data, megabytes, gigabytes, terabytes, all sensitive, and medical images are clearly sensitive. But maybe small leaks are fine. If you leak how many images you are processing or the resolution of these images, that's probably fine, right? So the requirements are slightly different for this second class of applications. Okay, keep these 2 examples in mind. I refer back to them every now in the talk. Okay, so now let's look at what a confidential computing platform is, and I'll do that by comparing it to other computing platforms. And I'll start with something we'll use as a baseline too, and the simplest one, a local computing platform. What is that? Well, that is you buying server hardware, installing system software on it, you control the system software, and then you can take your public executable, like your executable file, launch it into a process, and now you need to provision it with its secret data, and in a local system you can just use the file system for that. Everything is trusted here, nothing is attacker controlled. So where does Apache get its TLS key? From a config file on the file system, for example. So you can, using that communication channel, you can give the program its confidential data, and now it can start interacting with clients and servers on the internet, right? So clients visit the website, and the website might call API servers. And in this setting, the typical attack model that we have in mind is we worry that our confidential data might leak to attackers controlling the parties that we interact with or controlling our communication channels, the internet. So a typical attack that's relevant here might be the Heartbleed vulnerability, for instance. If your web server has Heartbleed, well, then maybe one of your clients can get your TLS key by using a buffer overread. That's the kind of threat model we have in mind here. But this is not how we run applications anymore these days. So it's more common to use cloud computing. Maybe your local hardware platform isn't scalable enough, or it's not well managed enough, so you don't want to use it for your critical applications. Instead, when you want to launch your public executable, what you'll do is you'll set up some kind of cryptographic connection to a machine owned by a cloud provider. So this here is intended to represent a cryptographic tunnel, let's say an SSH connection that you make to your cloud provider. And then when you want to launch your public executable, you essentially delegate that launch to system software on the cloud platform, which now turns it into a process or a virtual machine instance. And then you can use this cryptographic tunnel that you set up to also provision your program instance with its confidential data. And so now again we have a complete program, and it can start interacting with clients and servers. And we still have the same attackers to worry about. And maybe now we also worry about the fact that on a cloud platform, our program will not be the only one running on this system. There may be many other customers running code there, and that's code we don't control. In the local setting, all software on our platform in principle was controlled by us. Well, you can debate about that, but at least in principle. So now we might have attackers here too that try to learn something about our data. The typical attitude here is that this is the responsibility of the cloud provider. It's the system software on the cloud provider that has to make sure that none of the tenants can attack the platform or can attack other customers of the cloud. So we trust the cloud provider and the software that he or that they install to do that for us. And actually we trust the cloud provider and the system software of the cloud for more than that, because it can also see our confidential data, right? So the hypervisor or the operating system here can look into a virtual machine image or a process. It can actually, this cryptographic tunnel will typically terminate at some service running on the cloud platform. So the cloud provider could see our data as it's coming out of the tunnel. So we actually have to trust the cloud provider to not steal our data. Right? And this is something that's concerning sometimes. Maybe you don't trust the country in which the server is located. Maybe the government will kind of put pressure on the cloud provider to get that data and so forth. And so that's what confidential computing is about. Confidential computing is about changing that scenario of cloud computing such that you don't have to trust the cloud provider anymore. You only have to trust the hardware or a small part of the hardware. You don't have to trust who owns the machine, and you don't have to trust the system software on that machine. And the way in which that is done is to change the computing platform a little bit. Now, when I want to launch my public executable, I'm actually going to invoke a primitive offered by the hardware of the cloud platform to kind of do a couple of things in a single step. What I want to do is, I want to ask the hardware here to turn this public unprotected executable into a running program instance in a special way. That's why I colored the box dark gray or black now, in a special way such that this program instance cannot be observed anymore by the system software of the cloud provider. Right? How that happens, we'll come back to that, but the idea here is we launch the program. Once it's launched, once we have the virtual machine instance or the process, the system software can't look at the runtime state of this thing anymore. It will know what program is in there because it helped launch it. That's why we kept the program public, but it can't look into the running instance. At the same time, this primitive will set up a cryptographic connection, which is different than the previous one because it now terminates at this black box. Remember, in the previous setting, it terminated at some service provided by the cloud. Now it terminates at this black box. So anything we put in this channel only comes out inside this black box and hence is invisible to the system software. That's another reason why we split the program in a public and a confidential part, because we need a way to authenticate this black box. If I put something in this tunnel, I want to know where it's going to. Well, the guarantee I get from the hardware primitive here is, this is a cryptographic tunnel to a black box running this particular program. So I know this is a black box running Apache, for example. And once I know that, I might be fine with sending my confidential data over, and now it can be loaded into the program instance again. And now we have a running program, and it can start interacting with clients and servers again. And now we can actually consider a wide range of attackers, all the ones we considered before. But in addition, we might start to consider attacks from system software. So how could the cloud provider that we had to trust before, how could that cloud provider attack us, and how can we protect against that? And that is what confidential computing is about. So this is now, in a sense, my definition. A confidential computing platform enables users to launch programs remotely, as I just discussed, with essentially the disappointing security property that no more information leaks than it leaked in the local computing platform. So we don't get any improvement, right? So that's slightly disappointing. On the other hand, the good thing, the strong thing is we get this on a much stronger attacker model, right? So we get this guarantee even if all the software on the platform that runs our code is under control of the attacker. So that's the protection of data in use ID, right? So that's really the definition of confidential computing I want to use. I'm only going to study one aspect in this talk. I'm only going to talk about one aspect. So the creation of this black box is what is typically called the isolation property of confidential computing. And then the second part, you have the creation of this cryptographic channel. This is called the remote attestation, or the attestation part of confidential computing that I'm not going to talk about. It's also interesting, but we have to choose something. So I want to focus on how is it possible to run programs without looking into them. And this is actually tricky. You have all these technologies, Intel SGX, Intel TDX, ARM, SAV, ARM, CCA, AMD, SEV, and so forth, many complicated technologies. But the key insight is actually not that surprising. It's not that difficult. What the system software does is manage platform resources. Allocate memory, take away memory. Allocate the CPU to a program, take away the CPU. To do that, it doesn't need to look into the state. It doesn't need to look into the register of a virtual CPU. It doesn't need to look into the memory that it is managing, allocating and deallocating. And once you accept that, actually all that confidential computing hardware does is offer you a hardware implemented primitive to launch a program instance in such a way that it becomes impossible for any software to look into the state of this program instance. That's all it does. And the implementation details vary and are complicated, but they typically just use memory access control implemented in hardware and memory encryption implemented in hardware, and that's it. So we can do this. This is implemented, this is in many commercial systems. So now there is no direct access anymore to the state of this running program, but the question is, isn't there any kind of indirect access possible, right? So the system software might be able to influence or observe these program executions in many other ways that we haven't anticipated yet here. And that's what we want to study now, right? So we want to compare what can leak from a running program in the local computing setting and what can leak from a program in this confidential computing setting, and can we get them to be equal? Because then we achieve the promise of confidential computing. So in order to do that, it will make sense to think a bit more rigorously about what the meaning is of these programs, right? So we will need to model the behavior of this program, and of course, it's a software-based system. You know better than me how to model this, but a traditional, very standard way of doing is to use a transition system defined using operational semantics techniques, and we can do that both for assembly languages and for high-level languages. But that's not enough, of course. An important part of modeling will be modeling the attacker here, right? Because the program will be the same on the local system and on the confidential computing system, so essentially the semantics of the program will be the same. We also need to model what the attacker can do, right? And to do that, what we will do in our models is we will model the power of the attacker in labels on the transition system, right? So we will assume that whatever is in the state in the transition system is opaque to the attacker. He can't see that. Anything the attacker can observe and influence on the program execution will have to include in labels on the transitions. And it's of course important to get these labels right. If you underestimate what an attacker can observe, then anything we prove based on this model becomes worthless. Right? So I'll come back to that after we looked at a couple of models. So as an example of what that would look like, if we just consider the attacker model of a local platform, wherein at first approximation, the attacker can only provide input to influence the execution, application level input, and see output to observe the execution, then that would look a bit like this. So here is a very simple program. It's a Python program. I assume you can read Python. It manages a list of strings coupled with a Boolean that indicates whether the string is sensitive. So this is sensitive, this is not sensitive. And then clients can interact with it by providing an index, and then if it's a non-sensitive string, they can get a value, and otherwise they get some suitable error message. Right? And then you can see this would be an example transition for a program like that. If we start in this state, the attacker can provide as input index 2. That would point to this entry here. That's a non-sensitive one, so we get into this third case, and we get as output the value B, so the attacker can observe this, and we end in this state here, right? So this shows that even though states are opaque, values can of course flow to the attacker as soon as the attacker can do some observations, right? And this is an example of a very direct leak, a very direct flow. Leaks can also be indirect. Here's a very simple example of that. So an attacker can learn whether some sensitive string is present at an index by looking at the corresponding error message. That's a more indirect flow. So if we want to prove that nothing more leaks, we will need to turn to some notion of non-interference. Again, probably familiar, many of you are familiar with that. But I'm not going to prove anything in this talk, so I'll just get away with showing explicit leaks. But if you want to do the proofs, if you go to the papers, you'll see that what you have to prove is a non-interference property, some variant of non-interference. Okay, so now we know what we want to achieve. Let's think about how we could attack this. So what are these influences and observations beyond I/O that an attacker might have? So of course, the most interesting ones to look at are the ones that are caused by the attacker here, right? So we now control the system software. That's what's new in the confidential computing setting. So what does the system software do? As I said, it manages platform resources. So for memory, it will give a private virtual memory address space to programs and map that, typically using page tables, on physical memory. That for the CPU, it will allocate a virtual CPU to programs and then use timer interrupts to time share the physical CPU over many virtual CPUs. And this is operating systems 101. So these are the mechanisms we will try to abuse, and when we do that, these attacks are called control channel attacks. So this is using the resource management of the operating system to attack your programs. There are two important classes: page table-based attacks that exploit the virtual memory system, and interrupt-based attacks that essentially exploit the CPU virtualization system. And I'll give you a simple example and then point you to papers for more details. Right? So here's a simple example of a page table attack. To understand it, you need to recall a little bit how address translation works. So the page table is an operating system data structure that provides a mapping from virtual memory addresses to physical memory addresses. And that data structure can be complicated, but we can just think of it as a mapping. Now, there are three ways in which an address translation can go. Right? If a program accesses a virtual memory address, it needs to translate it to a physical address. The first thing that can happen is there's a translation cache, the TLB, the translation look-aside buffer. If the translation is already in the translation cache, the hardware immediately has the physical address, no system software intervenes, and this is great because that means the system software also can't see anything. Right? So if a translation is in the translation cache, that's good for the victim program. But it's not always in the cache, right? Sometimes it's not in the cache, and then we have to consult the page tables. So the hardware will walk the page tables to find the corresponding translation. But the page tables are a system software managed data structure that also has metadata that is modified by the hardware while it's walking the page tables. So as soon as we do that, if we get into the second step, the access in principle becomes visible to system software. Right? There's a third possibility. The hardware can walk the page tables and not find the mapping. The mapping is not defined. And then, of course, what will happen is a page fault exception. Control goes to the operating system, and clearly in that case, the operating system sees the access and can even intervene and do stuff. This is the worst of the three cases, obviously. Yeah. So with that, you should be able to see that by cleverly managing the page tables, system software can see any page access. The simple strategy is always allocate just a single page to the victim program, the one it's currently executing in. And then once it wants to go to a new page, there's a page fault, operating system comes in charge, gives it a new page, takes away the old one, and you continue like that. And then you see all page accesses. This is slightly oversimplified, because in reality, a single instruction can access multiple pages, like a code page and a stack page and a data page, for example, but that's the basic idea. Right? So once we can do that, it's clear that we can leak information, right? And so here's a very simple example how that, for a program like our public web server that wants to protect cryptographic keys, this leakage is definitely bad, right? So here, this is a function used, for example, in RSA cryptography. The details of the function don't matter. This computes a modular power, m to the d mod n, and what is important to know is that this exponent d is then part of the cryptographic key. So this is something we would like to keep secret, right? Now, of course, in the local computation platform, if this function executes, the attacker can't observe anything, and this is fine, right? But now in the confidential computing platform, with these page table attacks, an attacker can see every page we access. Now, if we assume that for this function, the modpow function is on one page, and the two functions that it calls, the square and multiply here, are on other pages, then we can see that you actually learn quite a bit. You don't need to look at the details of this algorithm, but what you have to see is that this algorithm goes over all the bits of the exponent. So the 0 here, the 1 here, the 0 here. And for each of these bits, it will always call square, and if the bit is a 1, it will also call multiply. So for a 0, we will see modpow calling square returning to modpow, which is pages AB being accessed. And for a 1, we will see modpow calling square returning to modpow, calling mult returning to modpow, which is this sequence of pages. And I think it's now pretty obvious that by just looking at the sequence of page accesses, you essentially read off the bits of the key, right? So clearly for a cryptographic program, that's already too much leakage. And here is an actual measurement. So the toy example on the previous slide was good to see the mechanism, but this is an actual measurement you can do if you use state-of-the-art techniques. This is a picture I took from a paper at Usenix Security this year. So what you see on this picture, so this enhances the attack with also using the interrupt power that the operating system has. It will use timer interrupts to make sure that we interrupt the program after every individual machine instruction. And this is tricky to do, but it can be done. I'll point you to papers explaining the attack techniques later. And what you see on this figure here then is, on the x-axis, you see individual machine instructions. So this is a run of a program for about 3,000 machine instructions. And then for every machine instruction, on the y-axis, you see the virtual memory address space. So this is the data section, this is the code section, this is the stack section, right? And for every instruction, we draw a dot for the pages that it accesses. And we see that most instructions access between 1 and 3 pages, right? And so that's the kind of measurement you can do then. And here, this box shows an actual invocation of this modpow function. You see here the code page containing modpow is this page, and we see here plenty of accesses to that code while we are executing the function. We see sometimes a call to square, and sometimes square and multiply. So essentially here, you read off the bits of the key that you're interested in. So clearly too much leakage. Is this also bad for the second class of applications we considered, like image processing, for example? Well, one of the things that the seminal control channel attack paper showed is that yes, the leakage is big enough also for these other classes of applications. So what they showed, for example, is that if you decompress an image that like this, or the original image looks like this, in a confidential computing setting, and then you try to recover that image using the measurements like this one, right? Then what you can reconstruct is what you see here, right? So clearly that's a fair amount of leakage. It's something we might want to worry about, okay? So that's the basic idea. Here are the papers where you can find more information if you would want to know the details of the attacks. I don't want to go into the details here. Unfortunately, so control channel attacks are perhaps the most relevant ones for confidential computing, but certainly not the only ones. All the other attacks that we already knew before we had confidential computing, like microarchitectural side channel attacks, where you monitor the cache to learn what memory addresses a program is accessing, or speculative execution attacks, where you influence the speculation behavior of a processor to learn about what a program is doing, or power analysis attacks, where power consumption by the CPU tells you something about the data the CPU is processing, or memory safety attacks even, where buffer overreads and buffer overrides allow you to read program state and influence program state. All these attacks become typically more powerful if you control system software. Because, for example, manipulating the cache will be easier to do for software at the highest privilege level than for a user level program. And it's interesting if we think about all these attacks. Well, here is the stack that Sriram was referring to in his introduction. If we, the way we build systems is by layering abstractions on top of one another, right? So we compile a structured language like Rust into a user-level instruction set architecture like RISC-V plus system calls, and the operating system implements the system calls using privileged instructions, and all these instructions are implemented in a processor described in Verilog, for example, which is compiled to a technology like CMOS or something like that. And if we now put all the attacks I talked about on this stack of abstraction layers, we see that they're all over the place. Memory safety exists because of the way the compiler is treating undefined behavior. Control channel attacks that we just discussed exist because of the way the operating system manages resources. Right? Microarchitectural attacks like the cache attacks and the speculative execution attacks, they exist because of the performance enhancements we implement in processors. Power analysis attacks exist because of the way CMOS transistors work. They consume power at the point where they flip bit, and so forth and so forth. So this should make you a bit pessimistic on how to defend against this, how to solve this, right? Actually, an argument I'll make is this probably means that to fix this, we also need to do fixes across all these abstraction layers. We probably can't fix this efficiently just at the top layer or just at the bottom layer. That'll be one of my main points when we talk about defenses. Okay, so let's look at defenses now. So if we want to design defenses and prove them secure, then we need models that incorporate all these attacks that I mentioned. So we need these label transition models that I mentioned, but we want to have in the labels the influence and observations that all these attacks that I mentioned give the attacker that controls system software. I'm going to give you two examples of such models, one old and simple one and one that's a bit newer. So the old and simple one is the constant time leakage model. That's maybe a model that at least some of you will have heard from. So this is a very useful model, an over-approximation, but a relatively tight over-approximation of the information that an attacker can learn through control channel and microarchitectural side channel attacks like cache attacks. So what this model does is, okay, we see all these complicated attacks. Essentially what they can learn is what memory addresses you are accessing. So let's just admit that the attacker, whenever the program accesses a memory address, the attacker can observe the memory address. And as a consequence of the fact that code is also in memory, this means the attacker can also see the control flow, because we will read instructions from memory too, so we know the program counter, so we know the control flow. And sometimes we consider other leaks, but for this talk I'll just consider these two. So if we add that as observations on our labels, we have modeled all these complicated attacks in a very simple way. That's the power of the constant time leakage model. And now we can try to write our software in such a way that secrets don't leak, even if we do these additional outputs to the attacker. And that's what constant time programming does. So a constant time program makes sure that it doesn't leak its secrets, even if we have all these additional observations. And modern crypto always at least aims to be constant time. There are still many vulnerabilities where they miss cases, but the goal of most modern crypto libraries is to actually be constant time. So let's build this into a model of a simple assembly language. I do that because I will build on that assembly language later to also model other attacks. So this is a very simple programming language model, right? So we have a finite set of registers, we compute on natural numbers, we allow in the assembly language arbitrary expressions so that we don't need too many instructions. We then only need 6 types of instructions. So this is a computation of an expression and assigning it to a register. This is loading and storing from memory. This is an unconditional jump, and this is branch if 0, branch if equal to 0, so a conditional jump. And then a program is just a list of instructions. And here you see how you could compile some pseudocode into this assembly language. This is standard compilation, right? The state of such a program would be what you expect. It's a memory, a register bank, and the current value of the program counter. That's the full program state. And then we can build the transitions. We can define an operational semantics for this. Again, you know better how to do this than me. So for example, if we start in a state like this, where memory has values 5 and 4 at addresses 0 and 1, and all registers 0, then what this program would do is compute 5 plus 4, right? It would compute the sum of the 2 elements in the array A starting at address 0. So the first step would be, we fetch this instruction, we check whether I is smaller than 2, it is, so that's a true, so a 1. So R0 becomes 1 and the program counter becomes 1. And in addition, the constant time leakage model says we should give the program counter to the attacker. Right? Same for the second instruction. And for the third one, when we do load our first array element here, this is a data load. So the address that we load from here is A plus I, which is 0. Right? So we tell the attacker, okay, we're loading from address 0. Because the attacker could learn that jumping through many hoops using a control channel or a cache attack, but let's just admit that it leaks. Okay? So, and we can continue doing that until the end of the program. So the nice thing about the constant time leakage model is that it's so simple. It only needs observations, and it's actually it's a bit over-approximative, but tight enough that we can actually still usefully work with it. So it's a very powerful and useful model. But the big downside is it doesn't model all the attacks we discussed. In particular, speculative execution attacks are not covered by the constant time leakage model, right? And these are important enough that we want to care about them in the confidential cloud computing setting. So just as a quick reminder, before I add this to the model, what are speculative execution attacks? Well, they exploit the fact that modern high performance processors, they don't fetch an instruction, execute it, fetch an instruction, execute it, like we did in the semantics on the previous slide. What they do is they fetch a bunch of instructions, 100 instructions in a reorder buffer, and while they're fetching them, they may have to speculate on the control flow, because if you reach a branch, you don't know whether it will go left or right, so you guess it will go left and fetch instructions from there. And once you have a bunch of instructions in the reorder buffer, you can execute them in any order that makes sense. Whenever an instruction's dependencies are satisfied, you can execute it. You still taking into account that you want to commit the effects of the instruction on registers and memory in program order to the architectural state, to the memory and the register bank. right? So that's the basic idea of an out-of-order processor. Now, on such a processor, an attacker can still observe this constant time leakage, right? So we still have the same leakage as we had in the previous model, but the attacker can do more, because an out-of-order processor has to make all kinds of choices. How many instructions will I fetch? Will I predict the branch to go left or right? Which instruction in the reorder buffer will I execute first, right? So there's all kinds of choices that a processor must make, and these are made by heuristics implemented in the processor, and unfortunately these heuristics are influenceable by an attacker controlling the system software. For example, an attacker could train a branch predictor to get used to the fact that the branch always goes left, and then the predictor will also predict for a victim program that the branch will go left. So we also have to model this influence of the attacker on the execution now. And one way to do that is by allowing the attacker to provide what are called directives to the processor. So whenever the processor has to make a choice that's made by heuristics in the processor, we actually give the attacker the choice to resolve the outcome of that decision, right? So I'm going to explain how that works, how we can extend our assembly language model to handle these things by walking you through the famous Spectre v1 attack, right? So what is Spectre v1? I assume most of you will have seen this somewhere, but let me briefly walk you through it. So this is the typical piece of code vulnerable to Spectre v1. So what we have here is an array read under a bounds check, right? So we have here an array A of length 2, and under a bounds check we read from it, and we know that the values in A are public. We don't care that they leak. So once we read R0 here, we don't care that we use it as an address, for example, later, which might leak it to an attacker to the constant time leakage model. We don't care because we know we're not reading a secret here. We do a bounds checked read from a public array, right? However, on an out-of-order processor, this branch might be misspeculated, and we might actually be reading out of bounds speculatively. And then we can actually leak this value, right? That's Spectre v1. So let's show this on this model with directives. So here we have again the state of our processor, now extended. We have the register bank here before and memory as before, but now we extend it with a reorder buffer of in-flight instructions that's initially empty. So we need to extend the program state a bit. So now the processor has to choose how many instructions will I fetch. And if I fetch many, what will I do with this branch? Will I predict it to be taken or not? Well, we allow the attacker to do that. So the attacker provides influence here, right? Label on the transition. It says fetch 3 instructions, and then for this branch, predict that it will go to address 3, so it will not be taken, and then fetch 2 more instructions. And the consequence of that is that we will have in the reorder buffer all these instructions, right? Don't mind the details. I'm not going to discuss the full formal model here, but that's the basic idea. Right? The next thing that the processor can do is execute some of these instructions. And again, several choices are possible. You could first execute this, or you could also already execute this, right? So again, we let the attacker choose. The attacker says, execute this third instruction first. Yeah? And now we see, well, I actually was out of bounds here. And what we're actually reading here is this secret that somewhere else in memory that this program isn't even talking about. Right? So we see that this happens. We also leak the fact that we access address 3, but that's not a bad thing yet. The bad thing is we have actually gotten the secret in our processor, and now the attacker can say, now execute this instruction, and this will actually leak this secret value because we're now using it as an address, and now the attacker has the secret value in memory. So this shows that by having these additional influences and the additional state of the reorder buffer in the model, we now actually model microarchitectural side channel attacks, control channel attacks, and speculative execution attacks in this assembly language model. So these are the kinds of models on which we want to build our defenses. Right? Okay, an interesting question here is, when is such a model correct, right? And that's actually tricky. So we should validate it in at least 2 ways. So first, the semantics should be functionally correct. It should behave as RISC-V, right? But that's a classic problem. If you build an operational semantics, you have to test it against the actual language that you're modeling. I remember a paper from Shriram, The Essence of JavaScript, so many years ago, doing exactly that. This is known stuff. But we need correctness here also in another sense. We need the attacker model to be correct. We need to have a correct model of attacker capabilities. And this is much harder to validate. So what we want to check here, the one-line summary is, whenever an attack that we want to consider, an in-scope attack, can distinguish two executions on the actual system, then these executions should also be distinguishable in the model. And this is trickier because distinguishing these two executions in the actual system might require quite a bit of ingenuity from the attacker, and so it's much harder to test this. Actually, I believe that the only way to build good models like this is to have attack research. So people with an attacker mindset should try to do these things, and once we understand what the power of attacks are, then we can try to come up with models like this. Okay, so based on these models, we can now start thinking about defenses. And as I said, when I mapped all these attacks on the tower or abstraction layers, it's unlikely that we will be able to defend against this by just changing the hardware or by just doing something in the programming language. So what I think is more likely is that to obtain both efficient and secure design, if you don't care about performance, we can do it. I mean, you can just use a very simple old processor that doesn't share any resources, and many of these attacks go away. But if you care about performance and security, we probably have to do smart things in all the layers of the stack. Yeah? Just as a hand-wavy example, at the programming language level, we could use a security type system, as the PL community has studied for many years. Then a compiler could deal with the microarchitecture side channel attacks by turning the code into constant time code, maybe doing control flow linearization and data flow linearization. And then we could handle maybe speculative execution attacks in the processor by doing taint tracking of secrets in the process. Very hand-wavy. So we have three mechanisms that work in concert to get a nice end-to-end security property. Actually, in their Turing Award lecture, Hennessy and Patterson, the two famous computer architects, they predicted that this kind of vertically integrated design will be instrumental for performance in the years to come. And they mention on the site, and likely also for security. So I completely agree with that. So this will be essential to get a combination of performance and security. Right? And I think this is actually the reason why I'm giving this talk at OOPSLA. I think doing this is what you guys at OOPSLA are good at. This is about integrating mitigations like type systems or runtime checks or taint tracking at multiple layers of abstractions and having kind of modularity in the sense that you want contracts between the layers. You want to know what guarantee you get from the previous layer when you're building the layer on top. And that's exactly what this community is good at. And I think this design space of coming up with defenses that you spread over these layers and that you coordinate, well, this design space is huge. And I want to give one or two examples, depending on how I'm doing on time, from things that we did in our group. There are examples from other groups, but we only scratched the surface here. So if you're looking for a good problem space to work on, where you can apply your systems and programming languages expertise, and that's the PSL in OOPSLA, I think. I think this is a great area to look at. Okay? So I'm going to give you a couple of examples just so that you have an idea what this might look like. Right? The first example is a paper from Usenix Security 2 years ago. It's called Prospect, and it's a hardware-software co-design, so it only works on 2 layers that deals with speculative execution attacks that I just explained. So that's why it's a good example to give here. I'm just going to explain how it works by going again over the Spectre v1 attack that we just saw. So what Prospect asks at the software level is, it uses essentially constant time programming as the mitigation there. So Prospect requires code to be constant time, but Spectre v1 snippet is constant time, right? It doesn't even touch secrets, so it's definitely constant time. So second, software should inform the hardware where secrets are. So you should, for example, tag memory whenever it contains a secret. There are more efficient implementation techniques, but conceptually that's what you do. You should make sure not to have a secret in memory unless that memory cell is marked. It's okay to do some over-marking, but you shouldn't have secrets that are not marked in memory. Why do we do that? Because now when the processor into the reorder buffer, into the microarchitecture, into the processor, it will know it's a secret. And it can taint track that secret throughout the reorder buffer. So when we compute on it and forward values to later instructions, we will know which values have been influenced by secret. And then the final thing, and that's the actual mitigation then that Prospect does is, whenever there is a potentially dangerous instruction, like loading from an address that is tainted, the countermeasure will take away this choice. The processor will not do that anymore, and hence we reduce the influence that the attacker has essentially. He can no longer ask to execute this instruction, and so the problem goes away because at some point the misspeculation, you can't execute this while it's speculative, and it's a misspeculation, so at some point the speculation will go away, it will be squashed, and the problem is gone. Make sense? So you see very simple mitigation in hardware, very simple existing mitigation in software, which is good because crypto is already constant time, and the two working together give us now the guarantee that the code running on an out-of-order processor doesn't leak any of its secrets. And we have in the paper a full proof of that. We have an implementation on out-of-order RISC-V core and a bunch of experiments. I just want to mention one thing. I don't want to fully explain the experimental evaluation here, but I want to make this point that by doing this cleverly, you can get security and efficiency. And what we get for Prospect is, if you do the marking of secrets precisely, then we don't have any performance cost. And you can even see that analytically. So we measured it experimentally, that's what the table does, and I'm going to point you to the paper for that. But even analytically, you can see that this must be true, because when do we block a speculation? So we block a speculation when a secret is about to leak. Right? Now, blocking a speculation can cost you performance, but it doesn't cost you performance if it's a misspeculation. And if an instruction is about to leak a secret, for constant time code, that must be a misspeculation, because constant time code will never architecturally, non-speculatively leak secrets. Right? So there you see that, again, the combination of the IDs is chosen to make sure that we keep our performance. Right? So that's the challenge of doing these kinds of vertically integrated design. Let me do one final example, and then I'll wrap up. So a second example published at Usenix Security this year is TL Blur. It's again a hardware-software co-design, so we do something at the hardware level, something at the software level, and this protects against the page table attack that I mentioned a bit earlier in the talk. So what does TL Blur need at the hardware level? The hardware needs to provide a mechanism where a confidential program can ask the hardware, call a handler in the confidential program whenever the operating system returns to me. So if there's an interrupt and the resumption, the confidential program must be able to be guaranteed that the handler will be called. Right? This is useful because the operating system is the attacker, so essentially when we come back from the attacker, we get the chance to do something, to implement a defense. And actually many possible defense strategies are possible there, and I'll explain one. Now, this hardware extension, we're fortunate enough to work together with Intel to get this in one of Intel's confidential computing technologies. That's in Intel SGX, the AX Notify extension. So this is available on actual commercial systems. So this is an attack we can immediately, defense we can immediately deploy, essentially. So how does it work? So recall the page table attack. So essentially what the operating system was doing here is trying to determine every page that you access. And remember I said, if an address translation is in the translation cache, it becomes invisible to the operating system. So the operating system will try to keep the TLB, the translation cache, empty, and it will do that by frequently going back and forth between the victim program and the operating system, because the TLB gets flushed on each of these transitions, right? So what TL Blur does is it uses this handler, the fact that it can intervene every time the operating system returns, to prefetch the TLB with all the pages it expects that will be accessed. And then all these accesses will be invisible. So a simple heuristic is to just instrument the program to remember all pages it has accessed in the past, right? We call that the working set. And then the handler will prefetch all these pages whenever you resume from the operating system. And the consequence of that is that all the operating system can still see is whenever you touch a page you haven't ever touched before. And that's an enormous reduction in information. So here you see the measurement I explained a bit earlier in the talk, right? So this is what you can still usefully measure once you implement TL Blur, even without remembering all the pages you accessed, because that's of course not realistic. You keep a small working set of recently accessed pages. You see that the amount of information that leaks goes down tremendously, from 3,000 to about 200 useful measurements. And you see that where here you could read off the key bits directly, here you can only see when the first time you touch a 1 bit, essentially, right? So maybe for crypto, maybe for the web server example, this is still too much. But for this image processing, this reduces the leakage to a point where it's not useful anymore to an attacker. So if this was an original image, this is what we could reconstruct, and this is what you can still reconstruct with the defense in place. You can still find the dimensions of the image, for example, but you can't reconstruct anything useful. Okay, so these are two examples. As a conclusion of the talk, what I hope I convinced you that this confidential computing area is a treasure trove of research challenges. You can do very interesting, challenging, intellectually nice attacks here, and you can do very interesting, challenging, intellectually difficult and nice defenses here. In particular, I hope that I convince you that this idea of vertically integrated design, where you like do multiple things at multiple layers in a well-coordinated way, is promising. And I hope you will consider looking at that with the expertise that you have. I think programming language expertise, formal methods expertise that is in the OOPSLA community is essential to this. If you want to do this, I just want to mention that, especially if you want to do hardware-software co-design, for years now we have been in the process of setting up an open source ecosystem of tools to help doing that. We have our own open source RISC-V core. We have both an in-order and an out-of-order implementation of it, and it's designed to allow easy extension with security extensions. We have now used it in about 5 or 6 papers. Some other groups have used it. We are trying to kind of build a community around this so that doing experimental work on this is a lot of work, a lot of implementation work. And if we can share some of that effort, that would be great. And so now we have the core implementation, and we have tools around it to do performance measurements, to do security evaluations. We're working towards an extensible compiler and so forth. And if we can get the community to work together on this, we will be able to explore this design space so much more efficiently. So if you're interested to look at that and want to work with it, don't hesitate to reach out. The main developer is very happy to assist people who want to get started with this. And with that, I think my time's up, so I have to wrap up here.
The mics are open. As you can see, F stands for Frank and also for full stack. So.
Ben Titzer, Carnegie Mellon. So this question might sound like it got you, but I promise you it's not. So one thing that I've learned about side channels is that they're outside of models. So when we add a side channel to a model, then we can prove that we've mitigated it. But there's a long list of them. And so a lot of vulnerabilities have started to show up. There's a long tail of them. I'm curious what you're thinking, what the long-term strategy for that is.
Yeah, great question. Thank you. So clearly, you're right. I agree with everything you said. And the way to manage this is by having an attacker-defender race, right? So yes, side channels will never stop. I mean, you can't have provable security in the real world. This is impossible. But what we can have is we can understand which of these side channels have what kind of power, and that's what attack research is about. So people should do empirical attack research. Say, if I own a cloud machine and I have this program running on, what can I do to it? And then only the attacks that are impressive enough, we model them, we take them in our models, and then we can reason on this. And maybe, of course, somebody 5 years from now comes up with another ingenious idea and finds another attack. That's unavoidable. I mean, we don't ever expect security to be done. This will never be the case. But we need to manage this in a kind of risk management style way. But that's why it's essential to have a combination of people with attack expertise, and I think the system security has that, actually too much of it maybe. But you need people with kind of engineering, defensive engineering skills for the other side. And it would be great to have some kind of competition between the security crowd and the formal methods crowd to kind of, a bit like the crypto community has these competitions about cryptographers and cryptanalysts. That's how we should handle this, in my opinion. I don't know if that answers your question, but...
No, thanks, that's great.
Yeah.
Hi, so in this model of initializing a remote process such that even the OS doesn't have access to everything about it. So in this model, the setting up part is still done via the OS. Yep. So if that part is evil, can it not just pretend to me that it has set up a secure enclave for my process?
Yeah, great question. I should maybe have emphasized that more. I'm going to go back to the picture. That's where the attestation that I didn't talk about comes in, right? So at the point where you do this setup, right? It's true. Maybe so. I'm sending this public executable. I'm sending Apache. Nothing prevents the cloud provider from bugging Apache, from putting all kinds of evil things in there, and then launching that. But remember that I said, you launch it and you also get this cryptographic channel to this black box, and the guarantee you get what the hardware will measure what the operating system launches. It will measure the identity of the code. What exactly is the code that is running there? And I know the code I want to run, and I get a cryptographic guarantee that about the code that is running in the black box. And if it's not the code I expected, if any bit of it has changed, I will refuse to send my data. But if it's exactly Apache as I sent it, then I am willing to send my data and get that guarantee. So essentially, I'm saying the code is the identity. In practice, it's a cryptographic hash of the code that is authenticated. So you know if the operating system would cheat, the attestation part would fail. If the operating system doesn't cheat, you have the guarantee that in the black box exactly your Apache is running and not a bugged version.
You still have the problem that like you're not communicating with the remote system by, like you're not attaching alligator clips to the legs of the CPU or the pins of the CPU. So anything you hear back from, including this, like, you give me an executable and they just give you the hash of it. But you
remember, we trust a small part of the hardware. So we trust the CPU package. And so the CPU package is involved in the loading process. So the operating system has to ask the CPU in steps, for example. So here is the first page of Apache. Here is the second page, and the hardware, the trusted part of the hardware will measure this. And will say in the end, okay, I have created this black box. I have now filled it with these bits. I have measured the bits that I put in the black box. And now I will set up a cryptographic channel showing to whoever did the launch that this is what's in the box. So that's where we need to trust. If you don't want to trust the processor, if you don't want to trust the hardware, we need to go to homomorphic encryption style solutions. But this is what you win if you trust a small part of the hardware. Yeah, does that make sense?
Yeah, thank you.
Thank you.
Okay, I had actually the same question, but now I have a follow-up. So what hinders how do you not know that the cloud platform basically emulates a CPU and like a malicious CPU? Yeah. You can't know that, right?
Yeah. Very good question. So there, cryptography is used to assure that. So when Intel makes a chip, or when AMD or ARM makes a chip with confidential computing technology, they embed a cryptographic secret in that chip. And so you need to use a kind of a public key infrastructure to be sure you're talking to a genuine CPU. And the idea is that the CPU package is so complex that getting that key out is undoable. And if you would want to emulate the behavior of the trusted part of the CPU, you would need to get such a key out. Actually, attacks, so one of the attacks our group did, one of the first attacks that completely broke Intel's first trusted computing technology was getting this key out. Once you get this key out, it's game over, right? So, and then they have a kind of a recovery mechanism where they upgrade keys and things work again. But that's the idea. So the trusted hardware part is initially preloaded with a secret known only by the hardware manufacturer, and the hardware manufacturer can attest that the cryptographic channel that's being set up is actually set up by a genuine Intel CPU. If the cloud provider can get that cryptographic secret out, it's game over. Yeah.
Okay, thank you.
Yeah.
Hi, Frederick, Nokia Bell Labs. A follow-up question to that. I'm pretty sure you're aware of the bad RAM work from some of your colleagues. Can you give your perspective on there, where they also try to attack basically the hardware threat assumption?
So some of the confidential computing technologies give guarantees not only against all system software, but they say even some parts of the hardware can be attacker controlled. Yeah, and let me say this bad RAM work that you refer to. So the idea of that work is, what if the cloud provider with physical access to the machine kind of puts a man in the middle between the CPU and RAM, right? Then that gives you even more attacker power than what I discussed here, right? And some of the confidential computing technologies claim to defend against that too. And so what that work did is showing that with a relatively cheap technique, you don't need a full man in the middle, you can kind of remap memory using tricks by lying to the processor about size of memory chips and so forth. And they show that with I think a $50 attack, they can actually break some of the confidential computing techniques. So I didn't talk about them, yes or no. Well, I think we should actually.
Do you see that as a part of the hardware software co-design?
I think this is something that probably can be solved in hardware.
Okay.
Well, maybe not. So good question. So the problem doing memory protection well is hard if you want to support large chunks of memory. Encryption is easy, but integrity protection is expensive. Actually, the very first confidential computing technologies had better memory protection and weren't victim to this bad RAM. This is absolutely critical memory, and I have a special malloc that allows me to malloc memory that will then be cryptographically encrypted and integrity protected, but another malloc that can be bigger chunks but you get less protection might actually make sense. But then I haven't thought this through, but you see that you have the security performance trade-off there, and we can only solve it by indeed looking at the multiple layers. So yes, thank you. That's actually a good suggestion, I think, to consider this. Yeah.
Okay, thanks.
I guess I'll use my privilege to ask the last question. Throughout your talk, as you've been talking about your models, I've been trying to think about the experience of trying to do these proofs, right? And it feels absolutely overwhelming because the amount of non-determinism that your attacker models have, I mean, that's what they have, of course. Are there lessons for us as people who do proofs about programs? Do you sort of restrict yourself to a small set of attacks each time? Because then, I think you get the question I'm getting at. Like, are there disciplines you have learned from doing this so many times that we could learn from about how to do this kind of modeling and proof?
Yeah, a very good point. So coming up, this is the million-dollar question, right? So finding the right abstraction that gives you something simple, but that covers enough of the problem space is just so difficult. And the constant time leakage model was a great example of that until it was not expressive enough anymore. And I don't think we have something yet that's as good as the constant time leakage model in terms of elegance. I think the constant time leakage model was okay to do. I mean, people have done machine-checked proofs with that. The people from INRIA are Gilles Bart and others have done that. So I don't think we are at that. We have models of that kind of elegance and abstractness, while at the same time covering enough ground for all the attacks yet. But I think this is what the PL people are good at, Shriram, no? Finding good abstractions.
Because I think like in crypto, right, the Dole-Evian model, I mean, obviously doesn't cover everything, but it's such a beautiful model. It's so easy to capture in a formalism, and it gets you so far. And I think maybe we're still more in infancy in the hardware setting for that sort of thing.
That's a good comparison, actually. Some of the proofs we do feel more like in computational crypto, where you have to do back translations, whereas it would be nice to find the right abstraction so that you can do this well. But that's the million-dollar question.
Cool. So I think on that note of challenge to the community, we should thank you again.
Okay, thanks. That means.
You made me feel good about
for the first one. I think
So yeah, our first talk will be given by He Zhu from Orchid University.
It's working. So is it started? Okay. Okay. Thank you for the introduction. Robots can learn from examples, but understanding how a demonstration works and what kind of abstraction can generalize from the demonstration is still a hard problem. Our work, Abstraction Refinement Guided Programming Synthesis, tackles this challenge. In robot learning, the goal is to produce a controller that drives the robot for task achievement. In this bit-solving example, as time step t, the robot observes the current environment state as t. The controller correspondingly computes the control action at to move the legs of the robot within the environment. Then the environment evolves to the next state as t+1. At each step, the environment also gives back a reward signal, RT, to feedback the controller. The objective is to learn the controller that maximizes the rewards the controller can receive from the environment. Deep reinforcement learning has emerged as a promising solution to this problem because due to its ability to learn controller without needing to know a model of the environment. Program synthesis for robot learning substitute programs in domain-specific language for deep neural networks. The benefit is twofold. First, programs are more interpretable. The learned decision logic can be read by the engineer. Second, programs are more generalizable. The same program can be deployed to mazes of various shapes alike. But traditional deep neural networks typically can only be learned and applied to environments of a fixed structure. There's a large amount of related work in programming synthesis for robot learning. Generally, a synthesis algorithm takes as input the robot environment, its reward function that gives a reward of 1.0 to task achieving states, and 0 for all the other states. Optionally, task demonstrations and a domain-specific language from which programs can be derived. Now the goal, again, is to generate a program whose execution maximizes the reward that it can receive from the environment from all possible initial states. So what does the DSL look like for robot learning? Assuming object-centric view, DSL variables refer to objects within the environment. In this pick and place task, for example, mu for the end effector of the robot, and then b for the block on the table. We assume a goal function g that maps environment objects to their target positions. The robot is expected to rearrange the objects within the environment to satisfy g. The DSL also includes expressions such as projecting variables to their attribute, such as 3D coordinates within its workspace. And for computing relational quantities, such as delta y, the vertical difference between the end effector mu and the block b. The DSL includes basic functions, such as norm for describing object spatial relationships, and arctan2, which is useful for describing their physical orientations. The DSL include event detectors, such as near, for checking whether the end effector mu is close enough to the block B. Those event detectors must be grounded using well-defined state abstraction predicates. Now here, phi is just a learned constant. The DSL also include abstract actions, such as moving the end effector mu to any position within the 3D, within the workspace. Those abstract actions also need to be grounded using low-level policies, such as deep neural networks. The DSL also include standard control structures, such as loops and conditionals. The main limitation of existing approaches for programming synthesis for robot is the reliance on handcrafted state and abstraction predicates. Handcrafted state abstraction predicate and also abstract actions. For something as simple as this pick and place task, that means defining state abstraction predicate for defining the robot, the end effector holding the block, or the end effector is moved above a block B, and also including actions such as opening and closing the grippers, moving the end effector up and down. So if you switch the synthesis algorithm to another domain, so those predicates and the abstract actions have to be redefined, which is not going to be scalable. So the research question we ask in our work is, can state and action abstractions be automatically inferred as part of the synthesis procedure? Our solution to this question is using abstraction refinement to automatically learn the necessary abstraction. And we call our method RobotScribe. So I'll describe RobotScribe through this block stacking example. So here the task complete condition is that all the blocks scattered on the table are formed into a tower. And finally, the robot arm moves away from the completed tower. To my knowledge, there's no existing deep learning algorithm capable of solving this task with a high success rate without assuming any domain knowledge. So in RobotScribe, the initial abstraction we constructed from the environment is simply true arrow psi-r, where psi-r encodes the task complete condition. So this abstraction means that we assume a single neural controller can be learned to rearrange the objects within the environment to satisfy the task complete condition psi-r from all potential initial states. The initial program, p-tower, takes as input the robot end effector mu, typed EE as input. So in this program, we expect this neural controller pi theta, which is used to ground the abstraction that can move the end effector until the task complete condition psi-r is met. However, from the execution of the learned policy, we know that just simply moving around the end effector all over the workspace cannot magically form a tower. Assuming access to demonstrations on how expert would perform this task, RobotScribe contrasts what went wrong with what went right. So this means that it learns by classifying states over failed program execution trajectory with the states just before success in the demonstration to learn what prerequisites are truly necessary to enable task success. In this case, it learns a classifier predicate at that captures an important subgoal. At least some block B1 has to be placed at its goal position. Here, the phi-c1 is also just automatically learned as a constant. Then we refine the initial abstraction by decomposing the whole task. The program from this updated abstraction gets some block from the environment and then use a neural policy pi theta 1 to to move one that tries to move the end effector to the end effector to the to move one block to the goal condition. And then it uses another neural policy pi theta to complete the rest of the task. In program learning, we deploy the robot onto the program onto the real environment, allowing each neural policy to gather experience in a replay buffer and apply standard reinforcement learning algorithm to improve the neural controllers to satisfy their goal condition. However, we didn't see any improvement. The neural policy pi theta 1 still struggles to place one block onto its goal position. Don't worry, we can continue run this abstraction refinement, which we call comparative abstraction refinement. And this time, we compare the states over field trajectories with the states in the demonstration just before sub-goal success in the demonstration. So we learn another important sub-goal predicate, hold. That means we need to first grab one object before trying to place it onto the goal position. Then we update we recursively update the initial abstraction, and in this new and the new program derived from the updated abstraction uses a neural policy pi theta 2 to first grab an object, and then use pi theta 1 to move it to the goal position, and then use another neural policy pi theta to handle the remaining objects on the table. At this time, the program is able to at least put one block onto its goal position. Through comparative abstraction refinement, we realized that we can use the on-the-fly learned predicate at to put another predicate to refine the abstraction, which means that other than placing B1 onto its goal position, there's another block B2 that has to be moved to its goal position. We marked the predicate at as a circular node in the abstraction. This means that the control strategy learned for one block should be and can be generalized to handle the remaining blocks on the table. So we derive a while program that iteratively hold one block and place it onto the goal position. And then the final policy pi theta after the while loop only needs to move the end effector away from the completed tower. RobotScribe also fill in the loop guard to generate an object ordering predicate to determine the order in which the object needs to be handled through the loop iterations. We also learned this loop guard by contrasting states in the from demonstration by constructing state where a block is handled from state where it's not. The learned loop guard means that at each loop iteration, the program needs to select a block which is not positioned at its goal position, and second, all the block underneath it has been placed correctly to provide support. And then we deploy the program onto the robot and let the neural policies to generalize across loop iterations for all possible blocks. As a summary, RobotScribe can be considered as an alternation between an iterative alternation between comparative abstraction refinement and program learning to construct the necessary abstraction for robot program synthesis. So we deployed the program into this Tower 5 environment and find that it learns well. There's a quick jump in the success rate, and this is because the final policy to move away the robot arm can be learned quickly. After this skill is learned, the success rate quickly jumps. And we compared this with some baseline algorithms and find that RobotScribe is able to generalize the program learned for stacking 5 blocks to stack even more blocks, such as 8 blocks and 9 blocks, and also the program can be deployed to onto new unseen tasks, such as stacking blocks onto a pyramid, where the baseline algorithms cannot complete the task. In the paper, we also describe environment. We also conduct experiments on more complicated environments and compare it with learning from demonstration baselines and find that RobotScribe is currently the best algorithm in this domain for task generalization. In conclusion, this talk, we present the comparative abstraction refinement as a general principle for constructive representation learning for synthesis. And we also present RobotScribe as a novel synthesis algorithm that automatically discovers the abstraction required in a DSL for synthesis. Thank you.
Okay, let's thank the speaker. Yeah, you can sit up. Okay, is there any quick question? I think we can ask while the second speaker set up the computer. Yeah, I have a quick clarification question. So how large is the RNN you trained for comparison? You trained a neural network as a baseline. So how large that neural network is?
So you have to use domain knowledge to help the neural network training, such as you need to first train the neural controller on 2-block environment and then 3-block environment until 5-block environment. And in this way, it can learn well. But in our approach, we
Ding. He did all of the work in this for this paper. My name is Ben Mikek. Unfortunately, he couldn't be here, but I'll do my best to be a maximal under approximation of the talk Shuo would have given. So C++ function templates look like this. They're an important feature if we want to constrain the types of inputs to functions. And so here, for example, we have a function f that takes x of type t. And for example, in this function, we can see that things of type t need to support the dump function call that's used inside this for loop. Unfortunately, if we call a function with a type that doesn't fit the type parameter that we expect, we get a very long and unhelpful error message. So here, if we call f with a null pointer, we get this error message that says that there's no matching constructor found. It's difficult to determine what went wrong based on this error message, and it goes on for 48 more lines after this. So clearly, this is a problem. After C++20, we got a new, better way of constraining types. So here you can see a type template where we have the concept of an integral constraining the type parameter t. If we try to break this again in the same way by calling it with a null pointer, we see a much shorter error message that only has 8 more lines that aren't shown. But more importantly, it tells us that there's no matching function call to f. So this is much more helpful in describing what the problem is and allowing a developer to try to fix the problem that's based on type parameters. So in C++20, all the problems in the world have been fixed. We have better interface specifications, we have better compilation error reporting, and we have better overloading control. But there's one problem with this picture. Programmers still have to manually write all of the constraints. And here's an example of a concept where a programmer will need to manually specify what this type t can be. In here, we want that things of type t support addition, and the result of adding 2 t's together should also be a t. And second, things of type t need to support the dump function call. And then, after that, we still need to see that we still need to put in place this function template where we say that things of type t need to either be of this concept int class or an std integral. So just to constrain this simple type t for this function g, we've had to write like 10 lines of code. And if we needed to do this for a more complex function, you can imagine this burden is growing pretty quickly. It grows even more quickly if we consider that we might have to do this for a bunch of legacy code bases that don't yet have type annotations. And so in this work, the problem that we face is that we want to automatically synthesize these function type parameters, the constraints on the type parameters, in order to reduce the developer workload and enable the introduction of these type parameters in legacy code bases that don't currently have them. So we want to infer the type parameter constraints for existing function templates. I'm going to summarize the method that's followed here in this paper in 3 simple steps. So first, if we look at a function, we're going to collect, if we look at a function that has a type parameter on one of its variables, we're going to collect all of the uses of that variable and encode each one as a constraint. So for example, in this function, we have x, which is of type u, and we see here that we call x.print. And so we're going to assign a constraint that x needs to support the print function call. We have a second call to x.print that doesn't add any new constraints. And then down here, we have a call to f with input y that's of type v. And so this is a little bit more complicated, but here we're going to just make a constraint that the type parameter, the type v needs to support whatever constraints there are on the input to f, whatever f is. To understand that a bit better, here's a deeper example. And what we need to do is, in step 2, to stitch together those different constraints for each variable and each type. We do that in 2 ways. First, if we have multiple uses of the same value in a function, values of the same type in a function, we simply conjoin their constraints. So here, for function f, we have postfix increment, prefix increment, and plus equals 1. And we encode this in the type constraint that the type t needs to support all 3 of those operations. For the second case, inside g, f is being called on the input x. But there are 2 different versions of f. There's the one that takes an integer, and there's the one that takes this generic type t. And so here we use disjunction to account for the function overloading. We say that U either has to be of integer type, or it has to fulfill all of the constraints on the types of inputs to the second function f, that is postfix, prefix, and plus equals 1. And then in addition, of course, here we also call x.print, so we conjoin the constraint that x needs to support the print operation. Finally, you can imagine that for large functions, these formulas get a bit unwieldy, and they can grow quite long if we have many uses of a variable with a generic type inside the function. And so we need to minimize these formulas. Unfortunately, minimizing arbitrary Boolean formulas is an NP-hard problem. And so in this work, we take the approach of doing an incomplete but fast algorithm, because performance is important in contexts like, for example, an IDE. And so we use an existing formula from existing work that has time complexity that's linear in the formula size and the nesting depth. So we've implemented this based on Clang and evaluated it on two sets of, two benchmark sets. One algorithm from the standard template library, and the other special functions from the Boost library. And the implementation is publicly available at this link, and you can also find that in the paper. We evaluate for 3 questions. The first of those is whether the synthesizer infers good interfaces. And to do that, we compare the constraints that are generated by the synthesizer to those that are given in the documentation for these libraries. This shows that example for the standard template library. And you can see that in this case, in every case, the synthesizer generates a constraint that is an over-approximation of that given in the documentation. So for example, if we look at the merge operation, we see that there are, the documentation says that this should be a triple with input iterator, output iterator, but our synthesizer says that all 3 of those should be an iterator. So it's an over-approximation. Yet you can see here that in most cases it's a useful over-approximation. There are very few cases, just a couple, where we synthesize an any type where we don't know anything about the constraints. The second question that we evaluate for is how useful these synthesized type constraints are for the end users. And as a proxy for that, we measure the length of error messages that are given by the compiler if you try to call the functions improperly with inputs that don't match the type parameters. So for both of the cases, both of the benchmark sets, the average number of lines of error messages decreases substantially by more than half, and in the case of special functions, from 43 all the way down to 15. And you can see that graphically represented here as well. The blue bars represent the original length of error messages, how frequently they occur in each length category. And the green bars represent the length of error messages after constraint synthesis. And you can see that they're much more clustered at smaller lengths, and we don't have any error messages that are very long and difficult to interpret. Even for error messages that aren't necessarily shorter, we claim that they're more easily interpreted. So here's an error message from the Boost Math template, from the Boost Math sign function. And here again, we have this invalid operands to a binary expression that goes on for several lines that isn't very helpful for users who might want to understand what the problem is and how to fix it. After we synthesize constraints on the types, we see a much more useful error message that says that the constraints weren't satisfied. And from that, a user can go back, look at the constraint set, and determine what was wrong and try to fix it in a much faster way than they could before the type constraints were synthesized. And finally, in this work, we take a certain trade-off between the speed of implementation and the precision of the type parameters. And in this work, we've chosen to take the speed side of that trade-off. So you can see that the execution time of our approach is very fast. It's 1/4 of a second for algorithm. It's just over a second for special functions. And we've successfully synthesized non-trivial function type templates for hundreds of constraints, for hundreds of functions in each case, but clearly not for all of them. So in this case, we've made a choice that speed of implementation is more important in cases like an IDE, and generating precise constraints for every function is less important. But you could take a different trade-off and embody that in your choice of for a Boolean formula simplification logic and achieve a different result. So in conclusion, we studied the constraint synthesis problem for C++ function templates. This is particularly important for synthesizing templates in existing code bases with large functions that don't yet have function templates. We designed and implemented a constraint synthesizer that generates automatically these function templates, and then we evaluated it on 2 libraries from the standard template library and the Boost library, and found that it's efficient and it synthesizes useful constraints in almost all cases. With that, thank you very much. Again, you really should thank Shuo Ding, who did the work here, but I'm happy to do my best to take any questions.
So, any question from the audience? Yeah, please go ahead.
So I think it's a really good work, but I just have a small question. Like, actually in the C++ community, there used to be a proposal to do a similar thing to this. It's not about concept, it's about no except. So once someone wrote that you should write no except auto to actually let the compiler automatically deduce what the no except conditions are. But a problem found with that is that there are often some unintended syntactic structures. Like, for example, if you call a function, you sometimes need to implicitly call the copy constructor and some of that. I wonder, is that handled well in the constraint generator?
So generating the type constraints, I think, is more, it's at a higher level than in the compiler, right?
Yeah.
So it's useful not like in guiding the compiler, but more so in letting programmers build code that is correct and doesn't contain the errors, right?
Yeah.
So I think this is really at the source code level, and so it shouldn't change the behavior of the compiler at all.
Okay.
It's just providing stricter type conditions for the users.
So essentially, you're just injecting those required clauses onto the functions?
Yeah, the templates.
Have you considered actually assigning a name for the concept? Like, for example, if you detect it must support ++, it probably is an arithmetic type or something like that.
I don't think that's been addressed yet. It wasn't in this work.
Okay.
That's a good idea for future work, though. We might explore that.
Okay, thank you.
Katerina from Carnegie Mellon and University of Lisbon. You mentioned a little bit how you're measuring the error reporting being better with like smaller size messages and everything. Do you plan on having any developers looking at those messages and comparing how they are compared to the previous ones?
Yeah, that would definitely be a good next step. I think so far we kind of have intuitive examples of that, and we've used the error message length as the closest proxy short of a user study, because user studies involve a lot of additional design questions. But I agree that would be good future work.
Okay, thank you.
Hello, everyone. Do you hear me? I'm glad you're here. I'm going to talk about special coordination synthesis for augmented reality. I'm Mohsen Lesani from University of California, Santa Cruz. My collaborators are Yijin Tsai and Jiasi Chen. All right, so you might have seen AR applications. You can maybe load a virtual object from the cloud on your screen. The latency for that is important. But more important is the latency of your interactions with that app. You want those to be very fast. And you can have multi-user augmented reality applications. For example, here we have a physical table and we have multiple virtual objects on top, and there are multiple users that are interacting with these objects. So what we want in these applications is first low latency, and we want to avoid rollbacks because these directly affect the user experience. And we also want to make sure we converge to the same state. If you're moving the object and some other user is moving the object, we want to eventually have the same position. And more importantly, we want to respect the physical restrictions. Like, for example, this ball shouldn't go into the table, right? So there are physical restrictions. And there are sometimes user restrictions, user policies. If there are confidential information on a virtual object, maybe it shouldn't go out of the room. These we traditionally call integrity properties of the object. And so there are some approaches already. So there is one by Google that's shipped by the AR framework for Android. What they do is that they do most of the coordination on in the cloud. And so the latency is pretty high in this framework. There are also works like Netcode where there is an edge server, so one of the devices can be the server. But similar to the previous approach, they have an optimistic transaction processing or reconciliation. And a lot of time that leads to rollback. And so the user can see the virtual object going back. And so this community, including my group, has worked on hybrid consistency a lot, right? And we thought that this problem, when my colleague talked with me about this problem, I thought that we can readily apply a lot of coordination conditions that we have developed in the past. So that when we are close to the vase here, the physical vase, and we don't want to hit or go inside it, we actually coordinate because the location needs coordination, right? We want to coordinate only when necessary. But if we are talking about this location far from the table, maybe we don't need to do any sort of coordination. So we want to have hybrid consistency and benefit from the places where we don't need to synchronize. We don't need strong consistency. And my group developed this notion of coordination called well coordination. And we successfully applied that to relational schema. And we thought that we could readily apply it to these AR applications until we realized that's not true. And we had to devise new notions. So here, you're looking at this ball in the game, and someone is trying to move it to the right. The issue is that if someone else wants to move it down, and your action A1 flies to the other process, to the other device, and then you move afterwards to the right, what happens is that you're going to enter this restricted area that we didn't want to get into, right? So here, integrity is violated. And we say that A1 permissible right conflicts with A2. It cannot commute past it to the right. And in well coordination, we had conflict graphs. So we would draw all the conflicts. And for this simple example I'm showing, the move method conflicts with itself. So we have a loop. What that means is that we have to synchronize all the time. We cannot do relaxed consistency at all. We should do strong consistency. We have to synchronize every time. And so that doesn't help us at all. It means that the application will be very slow. What we realized is that, again, this is very much dependent on the location. And well coordination had no notion of the current state. So we considered that. And if you look here, location L prime, there's no problem. You can move past A2. A1 can move past A2, and it's going to keep the integrity property there as well. So we want to be able to run them locally, and we do. So if the bar is very far from the table, these are the locations you can go without coordination. And this is something we captured in this new notion that we call well organization. But what do we do with the actions that are actually conflicting with each other? So I showed you one where A1 was conflicting with A2. What do we do in this case? Well organization requires that either A2 commutes, which in this case doesn't, or we have to prevent them. We have to prevent these concurrent calls that are happening. And it might seem very hard. How do you control the other device? You don't have much control over them. Well, if they need to do the action only after acquiring some resources, and we take those resources, then they cannot do it anymore. And when I talk about the implementation, I get back to this point. The other thing that well coordination did was observing the notion of dependency, and it showed that it's actually dual to conflicts. Doesn't seem like to be the dual, but it is the dual. So here, so you can do action A2, and it's going to be fine only because you did action 1, right? So you didn't enter the restricted area. But look at the right side. We are maybe the other device, Bob's device, and we received A2, and we have not received A1 yet. So we do action A2, and we enter the restricted area, which is not good. We are violating the integrity. So A2 is dependent on A1, right? It doesn't permissible left commute with respect to A1. If you move it left, then integrity is violated. And we kept track of dependencies in the past. using a generalization of vector clocks, which was very expensive. In this new project, we realized we don't need to do that. So if you receive the action A2 and you have no idea where the dependencies are, you can still check whether it's preserving integrity or not. And if it's violating integrity, you can simply keep it in a queue and wait until eventually all the other actions arrive, and there will be a state where action A2 is permissible, preserves integrity, and only then you can execute it. And this is much cheaper to do, right? You're not keeping track of all these complicated dependencies. All right, so we had this new notion, well organization, that relaxed well coordination even further, and now we had to implement it. What we did was that we adopted the escrow mechanism. You might have heard of this notion, but here there are so many things that we have to do on top of that. So here we have the ball at location 3 on the x-axis. We say there is 10 credits from one side to the other, right? So there are 10 credits. And from the location that you are, you need 3 credits to go to the left. There are 3 credits available for going left, and there are 7 credits available to go right. And so if Alice comes and wants to move 4 credits to the right, she needs 4 credits, right? And in this case, luckily, she has that credit, so she spends that credit and moves right. And the interesting thing is that, like energy, credits are preserved, right? So, but they convert from one state to the other. So when you move right, you create credit on the left. So, so that's new credit we get. But more importantly, how do we handle conflicts now? So you saw this issue that Bob is moving at the same time concurrently, and we got conflicts. What do we do about that? So it's not one axis anymore. We have to care about the other axis. We realized that to prevent this, if we acquire 5 credits from the down direction, then no one can take us to trouble, right? So before action A1, we have to collect enough credit and lock them. That's what we do. In this case, Alice doesn't have enough credit, so he first acquires that credit, asks others to give it the credit, and then locks it. So no one, like Bob, can now surprise us, right? And then we do the action A1, and only after everyone acknowledges they have done action A1, we release the locked credit, right? Only then we release it. So now that's good, because if Bob wants to do action A2, he realizes he shouldn't be doing that. He can observe the new state, and he doesn't do it. So I thought about locking, right? And immediately you might think, okay, what happens to failures? If a process fails, the credit that we have locked inside it will be locked forever, right? So that's dangerous. And I really thought that we cannot make it fault tolerant at the beginning. And reviewers insisted that you should make it fault tolerant. So we were forced to create. And we eventually did. So here's an example. So imagine all of these processes have 10 credits at the beginning in one direction, let's say D, and one of them moves two units in that direction. And there are some exchanges. As you saw, the protocol that I described has exchanges. So we have some exchanges. And suddenly process A crashes. So now what do we do? What do we know? How much credit did he have? What we can do is that we can have each process calculate how much exchange it effectively had with A1, with A. B calculates that to B2. Everyone else can calculate that, right? And they can communicate this information after the failure detector tells them that process A has crashed. And they can aggregate this, and effectively they have given him 1 credit. So now, at the very beginning, he had 10 credits. He used 2 of that sum, and then we gave him 1, so he had 9 in total. And we are 3 processes that are still correct. We divide it by 3, and each one of us recovers three credits. Now, the complication that arrives is that what if B crashes too? Now, well, with what I just described, we need information between A and B to be able to do the math that I described. But they have both crashed, and the information exchange between them is lost. So what we do is that we treat this whole set of A and B as a super vertex. And when we do that, we can still do the same. We can still calculate how much we exchanged with both of them together. C can calculate that, D can calculate that, And then we communicate that with each other. We can calculate the aggregate, which is 3 in this case. And then we say, okay, both of them together had 20. One of them used 2 because he moved by 2 units. And then we gave 3 to both of them together. So we sum that up, it's 21. And we have used 9 credit, we recovered 9 credits already. So we subtract that, it's very important. So we can now only recover everything together, but we remember how much we recovered before. So 21 minus 9, very important, we have to subtract 9. And then what remains for each one is a share of 6. So we have a lot of boards. We have 2D boards and 3D boards. And for each location and action, we have to know how much we have to lock, how much conflict we have with others. For that, we model this as in theory of linear arithmetic. So there is an action A, it's preserving integrity at location L, and there are some 2 other actions happening in other processes, action A1 prime and A2 prime, and they are fine, but when we do action A after them, we suddenly get into trouble. So we feed that into the SMT solver and ask what is the minimum magnitude for A1 prime and A2 prime that causes this trouble, right? And the SMT solvers can optimize for objective functions. They can tell us how much we have to log to prevent this. So we did experiments on devices up to 7 and with different restricted zones, as I showed you. Our latency is the smallest because we can do a lot of operations locally. But the latency for netcode is much higher because it has to do at least 1 round trip of communication between nodes. We avoid that. SAS, our own tool, is even worse. Our past tool was even worse. It has to do 2 rounds because it does consensus for each action. So they have higher response time. And eventually Firestorm is the worst because it has to go to the server and then come back in the cloud. So, and then we also experimented with different loads. We had a lot of different experiments. I get the chance to present some of them. So we increased the load, and again, the trend is very similar because we can do a lot of operations locally. Our response time is lower across the board. For throughput, because of all these coordination and heavy synchronization, for some of the higher workloads, for example, Firestorm and other previous frameworks couldn't finish the workload, but Hambazi did finish all of them. We also studied scalability. We increased the number of devices from 1 to 7, and we were consistently lower in response time. We also did fault tolerance, and the good thing about Hambazi is that it can continue to process actions even when failure happens, but Hamsaz, when the leader crashes, then we have to go and change the leader before we can process anything. So in summary, I presented special coordination in multi-AR applications with low latency, convergence, and integrity. I introduced a new notion of well organization. I presented how we can implement it with a credit scheme. I explained how constraint solving can help us synthesize custom coordination, and I showed empirical results that show significant improvements in latency, throughput, scalability, and fault tolerance. Thanks so much for listening, and I think I have to take the questions afterwards. Is that right? Thanks so much.
Test. No, your screen, that's an issue.
Sorry, what is the setup? This one? But, this one. Thank you.
Okay, please start.
Hi, thanks for coming to my talk. I'm Ziyi from NUS, and this talk is about synthesizing inductive heap predicates. So it's joint works with my advisor, Ilya. So separation logic. A lot of people like it, but just to give basic background, it's a program logic to reason about program heaps. For example, here we have x points to y and y points to x. And different from classic logic, the star here is called separating conjunction, which is about these two assertions is to be not overlapping in the sense that x points to y and y points to x are separately. So it's something widely used in a lot of domains. A very useful feature in separation logic is the predicates. When you want to reason about the data structure, then you need to use the predicate to express the data structure. Here's an example of singly linked list. And the base case is about the list is empty. And the inductive case is about we have a pointer j such that I points to the value a and j. And separating conjunctive with another recursive occurrence of the list. So other than the spatial part expressing the heap, we have the pure parts as the blue ones to describe some data payload. So although it's pretty expressive, but the expressiveness also come up with the difficulty, the complexity of this thing. So for example, you want to express doubly linked list segment. You are having the separating conjunction together with complex recursion, and you need to have 4 pointers as the arguments to express this predicate. Another example is nested data structure as list of cyclic list. It's not very intuitive about how to express that thing. And different systems are having different dialect of separation logic predicate to describe the payload. So overall, we find specifying separation logic predicate is difficult. We want to make it easier. And intuitively, examples can be more easy to come up with compared to the formal definitions. And what is the example here? It's the instance of the data structure. Like here we have the heap memory graph. On the right is describing a binary search tree. And what we want is to have a set of such memory graph to synthesize the corresponding formal definition of the separation logic predicate. So our task in general is to synthesize the predicate, and we want to have first effective method, and then to make it efficient. If you have heard of inductive logic programming, you might think it's quite relevant. So the problem setting here is giving positive and negative examples of the predicate and learn an optimal predicate that makes all of the instance, positive instance provable and all of the negative one unprovable. For example, we have 5 positive, 5 negative examples here, and we find the predicate can be learned by the state-of-the-art ILP system that is filtering out all of the odd number in the list. But what's the problem here is in ILP, you need to have negative examples, but in general, when we think about the data structure, we are thinking about the positive one. So we want to first figure out what happens and why we need the negative in the traditional setting. See, we want to learn sorted list, which is essentially singly linked list, but with the min set restriction saying that it is sorted. By giving the 2 positive examples on the left, what we learn from the existing ILP system is actually the version without the min set constraint. It's essentially singly linked list. So what's the problem here? Is there anything wrong? Nothing's going wrong because any sorted list is also a singly linked list. So the functionality of negative examples is actually about not to make the result too general. Here's the illustration. If we have 2 positive examples, the most general one can be too general. So the traditional setting uses negative examples. But we think about if we only have the positive example, it is also a case that we can learn the most specific one that can be meaningful. Here's another gap. let's see, we want to think about the shortest insize is the most general hypothesis, is a good approximation. But for the most specific one, the largest insize is not a good approximation, because thinking about F1 and F2 here, F2 is longer than F1, and it has an extra assertion saying A is greater than B, but it makes no sense because it has to be entailed by A is equivalent to B plus 1. So to make positive online learning work, we first need to normalize the search space. That is, in our case, by logic normalization, to get rid of such case and to learn the most specific hypothesis by positive online learning. Visit, and we have the example input, and we learn what we want. So is it currently be effective? It's not the case, because IOP learns per log program, and we are having separate logic predicate. To illustrate the gap here, we have another example on the left. We want to learn the predicate P from the graph on the left. But thinking about another predicate, the later one is actually also working in a per log program. Because you see, by replacing B with C and have two occurrences of P, then nothing goes wrong in per log. But it's not following the separating conjunction. So that's the gap. And we want to resolve this problem as, if you are familiar with separating logic, the later predicate is actually a binary tree, but it's not working at all. So as hinted by the title, we solve this problem by heap linearity, in the sense that for all of the facts describing this memory graph, we can only use it once during the per log proof to check the validity of separating logic. So only if it used once, then we can guarantee that it's within the separating conjunction semantics. So now it's being effective. Now we deal with efficiency. Actually, the previous one is about the semantics of separating logic. And here we also have different semantics can be used to prune the search space. For example, if the pointer is no pointer, we cannot use it anywhere, and something like heap functionality. So this semantics-based pruning are achieved by answer-step programming. Here we're basically saying that if a variable is no pointer, then it can only appear in the rule for twice. So our tool CP is a combination of traditional inductive logic programming plus positive online learning and a lot of separate logic domain. The user can specify the memory graph by manual written or get it from some programs, and we synthesis and output the heap predicate for further use. Here's our main result. We synthesize a branch of predicate, and most of them are out of the capability of existing work. Here's an example. So rows tree is actually very complex because there are some mutual recursion in the predicate, but in IOP we can deal with it. We have more discussion in the paper about the negative examples, about the formal definition stuff, and also have an illustration on the different application scenario. Now the story of separating logic stops here, and I want to give another aspect of the tool, which is about synthesis. So we use answer-step programming, which is essentially logic programming combined with satisfiability solving. And we are now the first one to use ASP to do the synthesis. Here's a list, recent list, but we also don't want to be the last one to use ASP to do the synthesis. So here's the secret. What happened to the system is about defining the search space as a set. For example, all of the possible inductive heap predicate as the search space, and the pruning as the set operations. They can be modeled by ASP encoding. And then there are a well-tuned solver. You can use it with a lot of useful feature for your enumeration in the enumeration-based synthesis. So if you are interested in details of the connection between synthesis and ASP, or you care about the domain in first-order formula, please check our latest paper. To wrap up, to do is the synthesizing separate logic. We propose positive online learning to make it work, and we have linearity to fill the gap between separate logic and logic programming. Then the semantics-based pruning make it efficient. So overall, we have a synthesizer and can be used in different separate logic-based tools. That's all. Thanks.
Any question from the audience? Yeah, maybe, I start from the first question. Since this is a positive only learning, do you observe in any case in your evaluation that the learned predicate is not the strongest one?
The strongest is defined in certain cases. So in general, the strongest one is the conjunction of all of the input examples. Yeah. But here, because we can restrict the shape of the predicate to be not that specific, so it has to be within the shape of inductive hip predicate, separate logic predicate. So, but after that setting, it can overfit, but it's always the strongest one.
But you have this you have a theoretical guarantee that the result is the strongest, right?
Within certain restrictions. So, for example, we have a predicate with certain size, and we can guarantee that in a larger size, there's no such more specific one, but it's not infinite.
Okay, thanks.
Hi, thanks for the talk. Actually, to follow up on that, the positive only learning is kind of dependent on the fact that your constructs aren't going to in any way form anything like a disjunction, right?
Right.
The minute you have a disjunction, you're immediately going to overfit way too much. Isn't separation logic a domain where you kind of risk that? Like, I mean, I'm impressed that this works, and I know that this works, but how did you finesse that into working?
So overfitting is in general anywhere in example-based synthesis, and at least in this work, given the certain domain, it is okay for not to get rid of overfitting, but yeah, it's in general unavoidable. If the quality of example is not that good, then you result in something you didn't expect it. So yeah, it depends on the input. It's actually the overall problem of example-based synthesis.
Okay, let's start. So, hello everyone. I'm Xuan Yu from University of California, San Diego. So today I'm going to present our works on synthesizing strongest and weakest specifications. So you might be wondering what this title means, and I feel like it is a little bit related to the last talk. We are both synthesizing predicates. But of course, this talk is definitely not about a single specification that is both strongest and weakest. That would be a contradiction. And instead, we are trying to infer two kinds of specification. So what are they, and why do we need both? Let's look at an example first. So now that we ask ChatGPT to write program for us, so suppose you ask ChatGPT to write a hash function using modular arithmetic, and it will probably give you two options, which looks almost identical, a times x mod m, except one used the modular operator and the other used the remainder operator. And as you may know, the remainder operator may produce negative output. So you are not sure which one is better, so you ask ChatGPT to generate some formal specification to understand the program. So for example, the output of the mode hash function should always be within 0 to m, and the output of the rem hash function should always be within -m to m. However, those specifications are actually not enough to describe the program completely, as they only talk about the potential outcomes. So for example, the assertion on the right, doesn't really tell you that the negative part can actually be produced, because the program on the left also satisfies the assertion on the right. So the specification might just not be strong enough. So in fact, we need another kind of specification to describe the reachable outcome. So for example, here, this yellow formula on the left basically says that for every output within 0 to m, and when some other condition holds, then there exists an input x that can produce that output. And the right one are similar. So now we can safely conclude that, okay, so mode hash function is a surjective function on 0 to m, and rem hash function is surjective on -m to m. Okay, that's good. And actually, the relationship between these two kind of specifications is just a duality between over and under approximation. So why do we need approximation? The reason is that the formula we show on the screen is not a useful specification. It just restates the program itself. So we have an assertion language with limited expressivity, and on which we want to build the specifications. Here, the blue formula, what we call safety properties, over-approximate the program, while the yellow formula, what we call reachability property, under-approximate it. And although both of them share the same formula, say 0 less than or equal to y less than m in their formula, their semantics actually differ from each other. So safety means that the condition holds for every input x, and the reachability, on the other hand, means that every number between 0 to m can actually be reached for some input x. So here I have also shown the complete condition that makes all output reachable, which I omitted in the last slides. So the condition basically says that if the modular m is a prime, and the coefficient a is neither 0 or m, and once this condition holds, we will know that this hash function will be surjective and thus doesn't waste the output range. Okay, so how do we automatically fund those specifications? So that's exactly what our framework does to synthesize both the safety property and the reachability property to better describe the program. So the Loud framework takes as input a program and assertion language, and it produces two things: safety properties and reachability properties. And the program also comes with a query that describes the relationship between input and output variables. And you can see that in the query, there is an exidential quantifier to model the input. And moreover, those properties are required to be incomparable and most precise. So the incomparable and most precise means that for the safety property, their intersection cannot be further strengthened. And for the reachability property, their union cannot be further weakened. So there actually has been a lot of existing work targeting this problem of specification inference. So how is our framework different from previous work? For example, like there are some dynamic technique called Daikon and QuickSpec. Actually, they learn specifications from the execution chases generated by some test inputs. As a result, they only guarantee the soundness over execution chases and give no guarantee on precision. Spiral, which is the work we build on top of, propose a way to synthesize the specification with both soundness and precision guarantee. But it is still limited to over-approximation. And our contribution is to propose a unified logic framework called Loud. And it is for synthesizing both strongest over-approximation and weakest under-approximation for program with extensively quantified input. All right, so how does Loud actually synthesize property? So there are two main challenges. First, it knows synthesize both over and under approximations. And second, it has to handle queries with alternating quantifier, and I will explain why that's important next. So our synthesis algorithm actually builds on top of the spiral algorithm, which only handled over approximation cases. And it follows a CGIS type approach. It also uses positive and negative example to approximate the synthesis objective. And at a high level, the algorithm has 3 main primitives, and each of them can be implemented as a call to the solver. First, it will try to synthesize a property from the current set of positive and negative example. And next, it will check the soundness of that property. If the property is unsound, the solver will return a new positive example. And if it passed the soundness check, we then need to check precision. And if it is not precise enough, the solver returns a new negative example together with a more precise property. So by iterating through these 3 primitives, what we call synthesize, check over approximation, and check strongest, we will eventually obtain a sound and precise over approximation of the program. And because of the duality, it seems straightforward to derive a counterpart algorithm for under approximation simply by flipping everything. But the things are not as simple because we still need to handle existentially quantified input. And let's see what will happen with this existential quantifier. So when we ask for a positive example, we are actually asking, OK, if there exists an example together with an input that produces this example. And that's fine. You could imagine that to implement this as a single call to the solver. But when you're asking for a negative example, the situation is different, because a negative example means that it can never be generated by any input. So here we get an alternating quantifier. And the way we address this is through another layer of quantifier instantiation. Each time we generate a negative example candidate, we reduce the universal quantifier by checking only over a finite number of instances. And we have this loop to generate it and validate it, the negative examples. OK, if you don't understand those technical details, don't worry. Let's see how the loud framework works in practice and how it can be applied to real problems. So in our implementation, we implement this 5 subroutine as queries to the sketch solver. So sketch provides soundness guarantee, but only for bounded input size and bounded language size. And of course, one could also choose other way or other solvers to implement this primitive, and that's why this is a general framework. And as long as they're available, one gets an algorithm for synthesize sound and precise properties. And for evaluation, we have some simple program for specification mining, and we also have some case study to show its applications. For example, our framework can be applied to reasoning about non-determinism or concurrency. And the key idea here is to use the existential quantifier to model the random schedule. So here I take the classic dynamic philosopher problem as an example. This formula describes whether a deadlock can happen under some random scheduling order. And if we use an over approximation, we get some condition that must prevent deadlock. And on the other hand, an under approximation gives us condition that may cause deadlock for some unlucky schedule. And our framework can also be applied to synthesize symbolic strategy for 2-player games. So suppose 2 players are playing a game on a grid, and this formula captures the game process from the player A's perspective. And if we have an over approximation, it means that as long as player A follows any strategy satisfying this condition, the player A will win no matter how player B plays. And on the other hand, if we have an under approximation, it means that the player A follows some strategy satisfying this condition. The player A may lose if player B plays optimally. And if you are familiar with reasoning in Hoare or in corrected logic, you may already realize that our framework can also be used to find strongest or weakest expressible post-condition in both of this logic. And the idea is to use the existential quantifier to define the post image of the given precondition P and the statement S. And here, the over approximation corresponds to the post condition in core logic, and the under approximation corresponds to the one in incorrect logic. So to conclude, we introduced our framework for synthesize both over and under approximation, and we explore several applications. And our framework has good usability. For example, one of our collaborators asked us, after this paper is published, he asked us whether we could use this framework to find condition that trigger the worst case complexity of the quicksort algorithm. And yes, our framework can successfully synthesize the formula showing that, quicksort reach n squared time complexity when the input list is reverse sorted. And moreover, we don't expect our framework to solve every problem since the scalability is always a challenge. But the principle of the approximation is widely reusable. So for example, by relaxing the problem definitions, we can design more efficient solution for some specific domain. So for instance, we apply this principle to synthesize abstract transformer for LVM, which led to our paper that got conditionally accepted in Povo next year. And it has an easy to remember name called Nice to Meet You. And it's turned out to improve some precision for data flow analysis in LVM. And that's all of my talk. Thank you for coming, and happy to take any question.
Okay, let's thank the speaker. Yeah, we have time for questions. Yeah, while answering question, I think the last speaker could set up the microphone. Okay, any question from the audience? Okay, I have a quick clarification question. You mentioned that during your reachability, you're checking the reachability. What you do is that you find a counterexample by inverse existential quantifier to universal quantifier, but you still have another existential quantifier, quantification. So I don't know whether that affects. So how do you find an example based on that?
That's a good question. And well, the key is that if you only do safety property, you got two existential quantifier, and they can be merged together. So that's good. But when you do reachability, it's like what I showed is kinds of have a existential quantifier followed by a for all. So you need so the out layer is a kind of synthesized from positive and negative example. But when you generate a negative example, you need another layers of counterexample guided, we call counterexample guided quantifier instantiation. So you can think it of like, we have two layers of counterexample guided synthesis.
Okay, I see, thanks. Yeah. So, more questions? Okay, let's thank the speaker again.
Hello.
Oh, cool. All right, I'm Alex. I'm here to talk about Metamorph, a tool to synthesize large objects from Daphne specifications. This is joint work with Sasha and Jeff. Sasha, unfortunately, cannot come and give the talk. So I first want to talk about the motivation of our synthesis hacks. Testing in object-oriented language context may require setting up complex objects that has private fields. So you can only set the field to the desirable properties you want by a set of methods associated to the object. So the challenge here is to generate programs, mostly a sequence of method calls without complicated control flow that produce objects with required properties. So our idea is to use method specifications in the verification-aware setting. In particular, we're using Daphne to guide the synthesis. So let me walk you through Daphne through this small example that we're going to talk about. Daphne is a verification-aware, semi-automated language where the user guides verification by writing pre- and post conditions. So here, the post condition is written with ensure clause, where it's assumed after calling the method. And preconditions written with requires are always needs to be proven before you invoke the call. Important thing, so here's a social network database kind of like example where we have users modeled with natural numbers. Each user associates a set of friends and a set of friend requests. And the constructor, for example, constructs an empty map of users. We have other methods like adding a user to the social network database, removing a user, sending a friend request, and responding to a friend request. Another important thing to note is that Daphne uses SMT solvers for verification. Namely, verification success is an unsat from the SMT solver, and a verification failure can result in a satisfiable assignment, where the assignment is a counterexample from the verification query. Another two things to note is that here we use a ghost field to model the heap state. This is not available at runtime, so this is, echoes the private field that I introduced before. Another thing to note is the method bodies are hidden from hidden for here, which might be an external function call, can be implemented in Java or C#. And this is also some of the key ideas of Daphne to have modular verification. It only reasons with method specifications. So you don't need to look into the method body. So let me give you an example synthesis problem. So here with the social network database, we want to synthesize a clique of 3 users, which all of whom are friends. Here we write our synthesis goal as we have the 3 users, 0, 1, and 2. 1 is friend of both of them. So here we have an object invariant saying that if I'm a friend of you, then you will be a friend of me. And then user 2 is user 0's friend. So what is a sequence of method calls that can generate this desirable heap state? So it's pretty simple, right? You add 3 users, send 3 requests, and respond to the 3 friend requests. However, this is actually like a non-negligible larger calls to a bunch of methods. So we can remove the primitive arguments to all of the method calls and try to ask Daphne to generate the concrete arguments to these things. This already takes minutes. And this is already given we have provided the sequence of method calls. In particular, when we are trying to synthesize this program, this is unknown. So how are we going to synthesize large objects that needs dozens of method calls to get to the desirable object state? So here comes Metamorph, which we kind of performs a goal-directed backward synthesis. So we're, instead of generating everything all at once, we do things step by step, limiting the solver context. And another observation we have is the synthesis goal is a object state that satisfies the desirable properties you want, and it's also a conjunction of constraints. So we can reconstruct method arguments and prior object states from verifier counterexamples by doing this step-by-step thing. We generate concrete intermediate heap states to step through the backward search. We also guide the synthesis to minimize the number of unsatisfied constraints, where we introduce 2 distant metrics. I will talk about that with a concrete example. So here's our example. We are still synthesizing the clique with 3 users. So we are performing a backward synthesis, so we should look at the target state first, and we are trying to backward synthesize it to the initial state, where we just call the constructor when we have an empty map. So here we take one step, so we consider all of the method calls that is possible. And here for simplicity, I only list 2 out. So requesting one step away from responding to a friend request, one step away from removing a user. And we can ask the Daphne counterexample generation to synthesize a concrete heap state, which is the state where user 2 needs to respond to user 0's friend request, and the state where, state 2 where, oh wow. Ooh. State 2 where we need to remove the extra user 4. So here is obvious, right? We should explore state 1 because it is closer to the initial state. But how we are going to have a systematic approach for this idea? So we introduced the piecewise distant metric. Oops. Piecewise distant metrics to encapsulate this idea, where we reason about the lower bound of method calls required to go from the initial state to the intermediate concrete object state. So here, for example, state 1, we need to at least have 3 calls to add user. Here we use some pre-trainings with Daphne to reason with how the method specifications interacts with our conjunction of constraints. So now we can reason that add user can at most add 1 user, and no other method calls can have anything to do with adding users. So we need at least 3 calls to add users. We need at least 2 calls to the request respond. And we need at least 1 friend request, which has a lower bound of 6. I want to note that this is a lower bound. We actually need 8 calls from the initial state to get to the state 1. However, for state 2, we need to at least have 4 add user calls and at least 3 response for friend request, which adds up to a lower bound of 7 calls. So now it is obvious for Metamorph that we should explore S1. So we will go and continue and take it step by step until we reach to the initial state, where we just add the user and then the synthesis is done. So we evaluate Metamorph with a number of APIs, including some basic data structures and some more involved examples adopted from prior work. We compare Metamorph with a bunch of different ways of performing synthesis. So our baseline is we ask the Daphne verifier to prove that no program generates a desirable object using the counterexample generation process to synthesize the sequence of method calls all at once. So this is a solver context problem. And then we have Metamorph without the distance metrics to guide the search. And we have 2 different metrics. One is the piecewise distance metrics that I just introduced before. The other one is the greedy distance metrics, which only reasons about the number of constraints that a method can change. So we do not invoke Daphne to reason about how it really interacts with the conjunction of constraints. So here is the evaluation we have done on the social networks example I've introduced before. So the y-axis is the running time in log scale. The x-axis is the number of interconnected users in the target object that we ask Metamorph to generate. So this is basically the number of users in that clique. So you can see that the baseline, even though it performs synthesis pretty fast for a smaller number of objects, it doubly exponentially blows up when we are considering anything that is larger than 2. Similar things happen for Metamorph without a metric to guide a search, because it will always consider junk state where we just remove a user, so we have 1, and we just get farther and farther away from the initial state. And here you can see that the 2 metrics we introduced actually don't differ from each other that much. This is because we have strong object invariance on the social network database, where there's really not much states that we can explore. So instead, we have another case study that we relax the object invariant. And here, the greedy metric will consider unreachable states. And similar to the Metamorph without any metric, it will just get lost in some unreachable states, or it will just get farther away from the initial state. So in summary, we introduce Metamorph that uses counterexamples to reason about effects of method calls. We propose 2 distant metrics to guide a search over object state. We evaluated Metamorph on 8 APIs, and it can synthesize programs up to 57 method calls, some of which are not even automatically verifiable without user hint. We found that Metamorph performs better when a distant metric is used, and the piecewise distant metric is better than the greedy metric in some selected cases, like the one I introduced before. At last, we also prototyped an integration of Metamorph with the Daphne testing framework. All right, that's my talk, and I will take any questions. Thank you.
Yeah. Thanks for the interesting talk. My question is mainly about the concrete maybe implementation or maybe the algorithm. But did you try to deal with symmetric breaking? Like in your example, the 3 nodes are symmetric, and no matter you operate on one of them, then it's equivalent, right?
So yes, we have a generalized precondition method that is described more in details in the paper, where we try to generalize the constraints that we're considering. So yes, there are states that are basically the same, and yeah, we do need to work around with that.
Thanks.
A very interesting talk, thanks so much. I'm actually not from this area, I don't know the details, But it seems very much to me as A star, and you know,
Yes.
in A star search,
Exactly.
heuristics have to be optimistic. So I was wondering if you have this result for your heuristic functions that the distance they estimate is always less than what it actually is.
So the reason I use this metric rather than heuristics is because in the paper we have a more detailed comparison between A-star search and best first search, and we have some discussions over there. So I'll refer to the
My
paper.
question was whether you have a proof that your heuristic
We do
is
not have a
optimistic.
proof of the lower bound, but we do have a sketch of what the distance metric is trying to show.
Okay, thanks so much.
Thank you.
Yeah, thank you for the paper. So in this backwards search, you need to make solver calls. Hey, did you do any analysis of, like, are there particular calls that took a really long time and the rest were fast, or was it similar for each step in this process?
So we do have a verification time breakdown that is described in the paper. I'm not aware of like there's like one particular method. I mean, it's Daphne. Anything takes a very long time. But yeah, we have a breakdown where we kind of the context of this is because like you cannot just ask Daphne to generate everything because it will just takes forever. But yeah,
Well, I guess I was curious, like even within a particular example, is it the case that one of the steps takes a really long time and then others are shorter, or is it more evenly distributed?
I think it is more evenly distributed, but I need to refer to the synthesis time breakdown, or the time spent on solvers by different procedures.
Sure, thank you.
Thank you.
Okay, I think that's the end of this session. Let's thank all the speakers for the session for the great talks.
right, good afternoon, everyone. Welcome to the second synthesis session. We have a great lineup of talks for you. So the first talk will be on tunneling through the Hill multi-way intersection for version space algebras and program synthesis, and Shu Hao will be giving the talk.
Hello? Hello? Hello everyone, I'm Shu Hao Zhang from Peking University. I'm very happy to present our work in Singapore today. Our work is about the optimization of VSA-based program synthesis, a generalized synthesis algorithm. Let's start with the background. Version space algorithm, or VSA in short, uses a graph-like structure to represent program spaces. A node in the VSA represents a program space with same output. This figure shows a simple VSA. You can see there are three kinds of nodes. The two leaf nodes represent atomic programs with no operators. Program 0 and x belong to the same node since they produce the same output in this example. The drawing node at the middle layer combines the subprograms with the specific operators, constructing larger programs. You can see that the left drawing node represents the program space with program link 0 plus y and x plus y. The union node at the top merges program spaces with the same output. That means the two program spaces like in the drawing node have the same output. Here is the workflow of VSA-based program synthesis. VSA-based program synthesis follows program by example framework, where we synthesize programs from examples and semantics. As you can see, there are three examples and the corresponding semantics in our example. First, simple example VSAs are constructed from these examples and semantics. So, three corresponding VSAs are constructed. Then, these VSAs are intersected in some way together to get a final VSA. The essence of VSA intersection is the intersection of program spaces. After intersection, we will get a final VSA whose program space has programs in all simple example program spaces. Finally, a program from the program space of the root node of the final VSA is extracted as the synthesis result. In this example, x plus y and y plus x is the result program. Our work focuses on the VSA intersection process. This part of the course accounts for the vast majority of the entire algorithm. Traditional VSA intersection process is iterative. Single example VSAs are added one by one. To analyze the efficiency of iterative VSA intersection, we draw the trend of the number of VSA nodes in the intermediate VSA, since more nodes will lead to more intersection costs. As you can see, the curve is like a hill. The peak is higher than the resource limit on those challenge tags usually. So constructing such a huge VSA on the peak or intersecting with it is unacceptable. So when the curve forms a hill, there are two factors influencing the size of the VSA when new examples added. On the one hand, the equivalent program space in a VSA node are divided into some program space when new example added, making the size larger. On the other hand, fewer programs will satisfy all examples, making the size smaller. That concludes the background part. We propose the following optimization to the VSA intersection. For multiple VSA intersection, we propose multi-way intersection. For the intersection implementation, we propose bottom-up intersection. We combine these techniques plus some detailed optimization to build an efficient synthesizer called Mo. So, is there a way to avoid the huge intermediate VSA in the iterative intersection process? The answer is yes. We propose multi-way intersection, which merges multiple VSAs into one directly, making it possible to avoid a huge intermediate VSA in the iterative intersection process. Now, we need to focus on how to perform the intersection. Formal approaches choose top-down intersection. The intersection process starts from root. I made this animation to show the process of the top-down intersection. Here, we start from intersecting the two root nodes. Here, the left one is a union node, and the right one is a join node. When intersecting a union node with other nodes, we stack on the sums of the union nodes. When intersecting two join nodes with the same operator, as you can see, we do intersections on the corresponding operands. Intersecting two leaf nodes is quite simple. Just intersect the atomic point spaces directly. These nodes in purple represent empty point spaces, since we can't know which node is invalid until the leaf nodes are constructed. There are many invalid nodes in the result VSA when we perform top-down intersection, leading to low efficiency. Therefore, top-down intersection is not suitable to combine with our multi-way intersection, since the number of invalid nodes will explode when there are too many VSAs in the intersection process. We need to find a more efficient intersection way to combine with our multi-way intersection. So, to avoid constructing these empty nodes, we propose bottom-up intersection, which starts from the leaf nodes. Here is the animation. As the intersection starts from leaf, all nodes has corresponding valid programs. You can see that bottom-up intersection constructs fewer nodes in the same example. Now it's time to build a PBE solver based on these techniques. Can we use the multi-way intersection to intersect all VSAs directly? The answer is no. We have to face a huge overhead when there are too many VSAs intersected together. Our solution is to divide simple example VSAs into solver groups in the right figure. Firstly, simple example VSAs are merged into solver intermediate VSAs using the iterative intersection. Secondly, these intermediate VSAs are merged into the final VSAs using the multi-way intersection. Now, we have to deal with a limited number of VSAs in the multi-way intersection. If the intermediate VSA is small, the whole process will be efficient. However, grouping leads to a new problem. If there are too many examples in a single group, the intermediate VSA will reach the peak. Boom! One approach is to use partial examples for grouping, then add the remaining examples iteratively. However, too few examples will lead to the failure of turning through the hill. The ideal situation is a green line. The smallest intermediate VSAs are constructed. After merging these VSAs, the result VSA will fall to the right foot of the hill. We use a heuristic strategy to find the appropriate point. The following formula is used to estimate the final program space. A small final program space indicates passing the hill. Then we can convert to iterative intersection to deal with the remaining examples. Detailed information about the heuristic strategy can be found in our paper. Our intersection algorithm has some good theoretical properties. In comparison with top-down intersection, we prove that bottom-up intersection can handle commutative and associative operators efficiently. In comparison with observational equivalence, a generalized PBE solver, we prove it performs no worse than OE theoretically with a constant factor, and the evaluation will show that our algorithm performs better practically. You could get detailed information, including theorem and the proof, in our paper. Now comes the evaluation. The evaluation consists of 3 parts. Can we speed up VSA intersection? Can we speed up specialized VSA-based solver? And the ablation study of each component. Due to limited time, we will omit the ablation study in our presentation. You could view our paper to get this information. There are 3 solvers in the comparison. Our solver is MoFTA. It performs multi-way bottom-up VSA intersection with adaptive grouping. Raw VSA performs iterative top-down intersection. OE implements observational equivalence, a generalized synthesizer based on pruning duplicated programs with same output in bottom-up emulation. We chose these 3 domains from Sega's comp to construct the dataset. Here are the results on the circuit dataset. You can see that we saw more tasks with less time cost and fewer VSA nodes constructed, especially on those challenging tests. These results prove the effectiveness of Mo. To verify that Mo can combine with other VSA-based solvers to further improve their performance, we integrate our VSA intersection implementation into Blaze, a specialized VSA-based solver based on abstraction refinement. Here is the evaluation result. The result shows Mo can accelerate specialized VSA-based solver like Blaze. Finally, let's make a summary of our work. We notice that iterative intersection will reach the peak of the scale hill, so we propose multi-way intersection to tunnel through the hill. We notice that top-down intersection is inefficient when combining with our multi-way intersection, so we propose bottom-up intersection to avoid these invalid nodes. That's all. Thank you for your listening.
All right, we have time for a question. Any from the audience? I have kind of a naive question for you. So you made a comparison at the beginning with grammars, and so I was thinking about syntax-guided synthesis, which is more of a specification than a solution technique. But what's the relationship between version space algebras and grammars?
Pardon?
What's the relationship between version space algebras like you did here and, say, a grammatical formulation of the problem? Do they cover different things? Are they similarly expressive, or are they completely different? Sorry.
Oh, the node in the node in the VSA, like the drawing node, you can see the plus node connects the sub program and then build the bigger programs.
Okay.
Okay.
All right. Thank you.
Oh,
Let's thank the speaker again. All right, and our next talk is on language parametric reference synthesis, and Daniel will be giving the talk.
Thank you. I'm Daniel from TU Delft in the Netherlands, and I will discuss our paper, Language Parametric Reference Synthesis. So, we are going very quick through this. So what's the problem we're trying to solve? We perform refactorings to our code all the time. This is to improve its maintenance or just to improve the maintainability, to improve the maintainability, to improve the structure of the program. And the kind of refactorings that we do is to move code around or to rename variables and these kind of things. And often IDEs have automated refactorings that can help us do these things. That's great. But one aspect of refactorings that we would really like is that they preserve the behavior of the program. After the refactoring, the program should still do exactly the same as it did before. And in particular, it should preserve the name binding structure of the program. So if you have a variable x, like in the example on the left, that resolves to the x at the top of the file in class A or module A, then after the refactoring, where we move module C lexically in module B, the x should still resolve to that same x at the top of module A, but now instead it resolves to the closer x in module B. This changed the behavior of the program and the value has changed as a result. The correct refactoring would be to also change the reference here. So it should instead, in this example, be a.x. This would be the correct name binding, and we want this property in our refactorings. And we have a solution for this. It's called reference synthesis. Our approach, we use it as a building block to implement refactorings. So when you're implementing a DSL or another small language, just the added effort of preserving name binding is a lot already. So our approach is 3 steps. First, we lock the references in the original program. For every reference in the original program, we determine what declaration in the program it resolves to before the refactoring. We remember this, and then we perform the transformation. We move code around, we rename variables, and after this, we synthesize references. We take those locked references, and we find a concrete reference, concrete syntax in the language of the program that resolves again to the intended declaration. And here's an example. The same example program. We take our x before a reference to x in the print line before the refactoring. We lock it, saying, well, actually, it refers to x1 at the top of the file. I've added numbers to distinguish the different occurrences of x, but they are not in the syntax. Then we perform the transformation. We move the module lexically inside, move module C lexically inside module B, but we keep our locked reference just the way it is, saying that it resolves to x1. Now comes the magic part. We synthesize the reference. We take this locked reference and we find a concrete syntax that corresponds to it that will again resolve to the intended x variable at the top of the file, in this case a.x. And we do this using the static semantic specification of the language, which means that we can do it in a language parametric way. So not just for a specific language, but for any language for which you give us a static semantic specification, we can synthesize these references. Why do we do it in a language parametric way? It will help you when you're building your own language, because for those languages you probably already want to write the specification anyway, and then you already have this building block for implementing your refactorings. So how does it work under the hood? We use, in this approach, the type checker. We use the statics meta language of the Spoofix language workbench, which is a language where you use constraints to specify the typing constraints of your language. You specify things like the type of an expression is an integer, but you also use it to specify the name binding structure of your program. It comes with a constraint solver to solve these constraints on a particular input program. If all the constraints are solved, well, your program is type correct. If the constraints derive false, well, clearly you have a type error in your program. And it's also possible, in some rare cases, that the solver cannot really solve all the constraints yet, and it needs some more information. This typically doesn't occur in a normal programming language, but we will use this ability of the solver to get stuck to our advantage. So in our approach, we extended the solver with the ability to expand constraints. The idea is if we have a constraint and we make it such that the solver will get stuck on this constraint, then we intervene and we try different alternatives for completing this constraint, and this will allow us to find the reference that we need. I will show step by step how this works. We need several ingredients. Well, we need the static semantic specification of the language shown here on the left. It is a set of premises and conclusions, a set of rules. So, for example, the top rule says that the type of a plus expression is integer if and only if the type of its sub-expressions are also integer. But there are also constraints, like the one in tdef, that say something about the name binding structure of the program. This constraint says, for example, that from a scope in your program, you should be able to resolve to a reference with a particular name. How does this work? The program, shown in the middle, is represented by a scope graph that's representing the name binding and scoping structure of the program. So for example, module A, module B, and module C are all represented as a node in this graph named as A, as B, and as C respectively. And also the definitions x1, x2, and the function foo are represented as nodes in this graph. If two scopes are lexically nested inside each other, there's an edge between them that says lex. If there's a scope that you can reach from another scope through a particular name, then there's another edge, for example, mod or def. This represents the name binding structure and the scope graph of the program. So if we need to resolve a variable x in the program, say from the println statement, we are in the scope of sfoo on the bottom right. Now we try to find a path in the scope graph that brings us to some declaration that has the name x. If we find such a path, we've resolved the name. If we don't find such a path, well, it's an unresolved reference. And this path has to conform to a certain regular expression of the edges that it can traverse. For example, you might look for your variable x in lexically outer scopes, but you might not want to traverse to a completely different class without actually naming this class. So we take our program with the locked reference, remembering that it resolves to, or that it was locked to x1, and we replace this locked reference by a hole, a free unification variable. And by doing this, when we allow the constraint solver to use its static semantic specification on it, it will try to solve as many constraints as possible, and it will be left with some constraints that it just cannot solve. In this example, it is left with a constraint that says, well, the type of this expression, which is this free unification variable, should be integer. But the expression is, well, a free unification variable, so the solver gets stuck here. It stops solving. It didn't determine if the program is type incorrect. Also, it is not type correct. It just stops here. And at the same time, we're tracking that this free unification variable h corresponds to a hole and what we have synthesized for this hole. In this case, we have not synthesized anything yet, so question mark h still maps to question mark h. We take the typing rules of the program, and this is where our work comes in. We see what conclusions of these typing rules we could fill in the place of this stuck constraint. In this example, we have three typing rules that we could apply. The first one assumes there's an addition. The second one assumes there is a simple reference named x. And the third one is a qualified reference, some m.x. So we will try to insert each of these alternatives as an extra constraint. So we now end up in three different states. In one state, we assume it's an addition. In the next, it's just a simple reference. In the third, it's a qualified reference. And for each of these states, we've added these constraints. And we've updated the mapping of the holes to the syntax. We will let the solver solve these. It will try to solve as much as possible, again, using the static semantic specification of the program. For the top example, it solved so much that it now concludes that, well, it's an addition, but I still don't know the expressions on the left or right-hand side, so it got stuck again. For the middle one, where it is some simple name x, but x is also not named, it's an unknown name, the unsolved constraint is a so-called query constraint that will be used on the scope graph to find the declaration that we're resolving to, but since the name is unknown, it cannot solve this query yet. And the bottom one with the qualified name has both the query constraint left over and a constraint on the qualifier itself, saying that there must be some qualifier that it also doesn't know yet. Let's continue with the bottom two examples. We'll now expand the queries. We know what declaration this reference should resolve to. We know its name in the program, so we can actually fill in this query with the name that we expect it to be. So we do this for the middle example, and we fill in X, and basically saying, well, this whole is actually the syntax just X, reference X. And for the bottom example, there's two X's that we can fill in because there's two declarations that are named X that we can reach, and we try both of them. We again invoke the solver. Well, for the top constraint where we just filled in X, actually the solver concludes that it is not satisfiable. Well, actually we conclude it's not satisfiable. The solver is happily solving this constraint, this query constraint. It resolves to declaration X, but it resolves actually to SX2 in the scope graph, which is for X2 in the program. And we actually intended it to resolve to X1. So the first alternative we can discard. Just writing X is not going to bring us to the declaration that we intended. For the second and third, well, the query is also solved, and we get the two residual constraints. The difference between these two is that in the top one, it assumes that there is some scope SA, where the qualifier brings us to, in the scope graph, and for the bottom one, it's some scope SB. Both have an X declaration X in them, in the scope graph. So we come in again, and we expand on those constraints once more. So for the scope of mod rule, predicate, there's several rules that we can try. Again, the top one, which is just a simple name, or the bottom one, which is again a qualified name. We can, of course, repeat this as much as we want, adding qualifiers as much as we want. Well, we'll try to converge as quickly as possible to the shortest solution, because that we know will resolve to the intended declaration. Doing both of these alternatives to both of the inputs gives us 4 new states, where we basically create each combination of these rules and the predicates that we're expanding. Again, we invoke the solver. The solver leaves us again with a whole bunch of constraints, some query constraints and some predicate constraints. And again, for the unsolved query constraints, we can insert, well, actually, we know the name of the declaration that corresponds to SA or SB. So we'll just insert those. So for the top example, we get A.X followed by B.X, and for the bottom example, it's the same. However, if you look at the constraints, you will see that some of the scopes are actually different, so some of these will actually not unify correctly. So we invoke the solver once more, and now finally it can make some conclusions. For the top example, it actually solves all the constraints. And it concludes, well, actually the syntax for this whole that has to resolve to X1 is A.X. For the second one, actually the constraint that SA matches the target of where our qualifier resolved to is actually not satisfiable, and that's the same for the third state. And for the fourth state, it is satisfiable, but we conclude it's not resolving to the intended declaration, so we discard it. And this way, we have been able to synthesize the syntax for the whole that we were looking for. We now have a reference to the X in module A, despite us having moved some code around and changed the whole name binding structure of the program. There are some additional challenges here. Of course, performance. There's a huge search space that we can try, but we try to converge quickly to a solution by firstly only expanding the relevant constraints. Furthermore, expanding the oldest constraints, because those are probably the ones that have the biggest impact on the program. We try to expand query constraints, because those are the ones where we can insert actually the name of the thing we're looking for. And then we expand predicate constraints that yield queries, because the quicker we go to a query when we're looking for a reference, the more it makes sense. And additionally, there's a problem where solutions to one whole can depend on solutions for another whole. For example, here, if there's also a whole for the import, the print line X we cannot easily solve because it could resolve through the import, so we have to resolve the whole for the import first. We evaluated our approach, We've shown that it's sound, and it's sound by construction. And we have more than 2,500 test cases of 3 small languages, of which we had already an existing specification in statics, on which we applied our approach. We were able to solve for most of them all the holes within 60 seconds, and basically for every hole, except for some outliers, every hole we could solve in 1 second. So, thank you for listening. Find also our paper for more details, and if you have any questions.
Let's thank the speaker. All right, we ran out of time for questions, but please ask your questions right afterward. All right, so the next paper is UT-Fix, change-aware unit test repairing using LLM, and Shanto will be giving the talk.
Hello everyone. Today I'll talk about our paper, UT-Fix change-aware unit test repairing using LLM. I'm Shanta Rahman. This work has been done when I was interning last summer in AWS. So in the evolutionary software system, we very frequently update the software. So we need to update the software to repair the bugs, to add the features, and many more reasons. And when developers make their changes in the code base, many often they forget to update the test case. So as a result, spurious assertion failure or reduced code coverage can happen. In one study, Meta showed that 14 to 22% of the software failures are coming from outdated tests. This highlights the need to keep tests in sync with code changes to ensure software reliability. Here is an example of a unit test that is taken from an open source Python project. Here there is a focal method. The main responsibility of this test to check if this focal method is working correctly or not. So focal method can be any method that exists in the code base. So let's assume the scenario that this focal method is now updated by the developers. And here that red part is representing the deleted code, and the green part is representing the added code. So here the main changes is happening based on the value of force. From the test code, we see the value of force is set to true. When it is true, then the else branch is executing. So in the else branch, it is returning all the values of base ID except this specific ID. On the other side, in the test case, when it is trying to run this assertion that is expecting to get all the base IDs, the assertion is failing. So to mitigate this problem, we propose a technique that can automatically update the assertions. In this paper, we propose UT-Fix that can repair unit tests when their corresponding focal methods undergo changes. Our UT-Fix addresses 2 critical issues. The first one is spurious assertion failure, and then the reduced code coverage. For the evaluation purposes, we create 2 datasets. One is for synthetic dataset and another one is real world dataset. Now I'll talk about how our proposed solution work. So these 4 are our input to our UT-Fix. So here the first is original focal method, then updated focal method, original test code, and the failure message that we find. And then we send this to the UT-Fix, and UT-Fix can generate the updated test. Now I'll talk about UT-Fix in details. So here again we have the same input that I just said. And from the original focal method and the updated focal method, we measure the code diff. And using these informations, we create a prompt, and that are fed to the LLM. And the prompt are looking like this. It contains a set of instructions, constraints, and the data. And then LLM is generating a test code. Then we have a validator that checks if the generated test is correct or not. If it is a correct one, then we can directly take that test and we update the test code. Otherwise, we collect the more contextual information by the static and dynamic slicing. And then we generate the feedback considering all these contextual informations and pass it to the LLM. And we keep running this process until the chain of thought value is less than or equal 5. Now I'll talk about how validator works. So the input to the validator is the generated test, and then we have an execution validator that runs the test, and if the test passes, then we collect the code coverage. And then we check if all the changed lines are covered or not. If yes, then we are very happy and we update our test code. Otherwise, if the test fails, then we collect the failure log, and if it happens that the test is passing but all the changed codes are not covered, then we are collecting only the uncovered lines. Now I'll talk about how the context gathering works. So here we have two process. One is static code slicing and another one is dynamic code slicing. The static analysis here, we are depending on the focal file. So focal file is a file that contains the focal method. So using these three information, we create again a prompt, and our prompt is looking like this. It contains the set of instructions and the data. And then we feed these things to the LLM, and it generates the relevant code slices. Our relevant code slices are looking like this. And the idea of code slicing is mainly coming from the cohesion and coupling concept of the code design. And when we did that static code slicing, we still find that there are lots of relevant part of the code we are missing. So that's why we rely on the dynamic code slicing. Here, we run the test, we collect the code coverage, and then we find that sometimes the coverage report is too big. That's why our minimization scheme minimizes the code coverage report for this specific focal method. Finally, it generates the code slices, and our dynamic code slices are looking like this. Now I'll talk about the dataset that we consider, that we created in our research. So to evaluate the UTFIX, we generate scene bench and real world dataset. So we have three steps. The first one is we identify the focal method and the test code pair, and then the scene bench and the real world dataset. Now I'll talk about how identification of focal method and unit test pair happens. So here we collect the test code using the unit test loader, and then we collect the AST of the test code to look for what are the methods that are called from the test, and then we do the Jaccard similarity index to look for what are the focal methods or what are the methods that are called from the test which are very similar. And that is one way, and also we rely on large language models. We pass the test body and asking the LLM that what could be the possible focal method, and then we do the intersection between this suggestion and our prior suggestions that we found by the Jaccard similarity index. And then we collect the code coverage report, and finally we get 690 total FMUT pairs. And once we get that, now we will create our main dataset, that is scene bench. So here the main objective is to change the inject changes in the focal method. So here we collect the context. The context is mainly the focal file. And here we are also emulating what could be the changes, possible changes that developers usually make in their code base. And then using those informations, we are guiding the LLM. And then here our intent is to measure that our UTFIX is working when there is some assertion failure happens in our dataset. That's why we also instruct our intent to the LLM, and the generated code that we find by the LLM, we execute it and check if it satisfies our intent or not. If it does not, then we again give the feedback. Otherwise, we consider it is a valid instance of our dataset. Following this, we get 352 total pairs. And for the other case, we also follow the same way. So similarly, we provide the intent and we run the test. If it satisfies, then we are happy. We keep that instance as into our dataset. And in case of real world dataset preparation, here we mainly traverse the Git. So here we see, for example, we have 9 commit history. So we check, we start with the latest commit, that is C9. So we goes backward. For example, first we go to the C8 commit, and then we find there is no change happens in the focal method and the test code. So then we go back again, and we find that the code changes happens, and it is a valid commit. By saying valid commit, we mean like no assertion failure in this commit. If it happens, then we replace this T9 to T7. So this is how we create our real world data set, and following this approach, we get 20 pairs for spurious assertion failures and 30 for the T-twist code coverage. And we have 5 total research questions, but for the sake of presentation, I will talk about only 2. So for the details, please see our paper. And so the first research question that I'll discuss, that is how effective UTFix is in repairing failed tests and how much time it needs to repair the test. So to do the experiments, we have a baseline that has the updated focal method and the failure message and the original test. And for the UTFix, we make 4 different variants with the different contextual informations. So here our effectiveness, we see that when we have the UTFix with dynamic trace, at that time we can repair maximum number of tests, which is 314. And whereas the baseline is 295. And we also see that for other variants of UTFix can also performs better than the baseline. And for the runtime, we see that UTFix with dynamic trace, it takes a little bit more time than UTFix without any trace and with static trace. However, we see that it is better than the baseline. So we can say that UTFix with dynamic analysis is better than the baseline. And in conclusion, in this paper, we present UTFix to repair unit tests that suffer from the assertion failure and reduced code coverage. We create 2 data sets, and we can repair 89.2% assertion failures, and we find the UTFix with dynamic analysis performs the best. Our code and the data set are available in this repository. I'll be happy to take the questions for now and later. And I would like to also talk one more thing. So I'll be in the academic job market this year. I'll be happy to chat more about my research and for the future collaborations. Thank you.
Time for a question or 2? Come up to the microphones.
So if there's a session failure, how do I know which I should fix, the test code or the program code?
Now so if the assertion is problematic, we repair the assertions only, the test code. We do not repair that. We are assuming that.
I mean, if I'm a developer, I want to use your tool, then in what scenario should I use? How do I know that it's the test code that need to be fixed, but not the other part of the program?
Yes, so here our assumption is the actual code is correct. The changes, whatever the changes is happening within the code base, it's correct. We are assuming that the test code is not correct or updated with the changes in the code.
Okay, thanks.
Okay, hi, Yunbo from the Chinese University of Hong Kong. So I love the idea of static code slicing, but I'm wondering if you have ever encountered any file or focal methods that's related to many other external functions. If so, would LN understand such long context across like different files or even different projects?
Yeah. So you want to know would you please repeat that?
So I'm wondering if LN can process long context well, like in different files or in different projects.
So for the static slicing, so we are relying only the focal file. That means the file that contains the focal method. So we are not providing, that's why we are not providing too much context to the LLM. and we are limiting it to only the focal file. But later we realized that it is not enough because static slicing is missing lots of relevant code slices. That's why we rely on the dynamic slice. And here the problem, the thing that you are just asking, like, okay, what happens when we have loss of context? The problem, that's why we have a minimization scheme that minimizes the dynamic code traces so that we can give a reasonable amount of context to the LLM.
Okay, thank you.
Does this make sense? Okay, thank you.
All right, let's thank the speaker again.
Thank you.
All right, our next talk will be synthesizing DSLs for few-shot learning, and Paul will be giving the talk.
Okay, great. Thanks everyone for coming. This talk is about few-shot symbolic learning. So what exactly do I mean? Well, I was spending some time this week in the National Orchid Garden, not far from here. It's fabulous. I recommend it to you if you haven't been. I'm not much of an orchid expert, but I was looking at these flowers and wondering, how do you identify them, right? So many different colors of orchids, right? I thought there were 5 petals. It looks like there's a fancy lip in the middle. The petals seem fairly thickish. So what could be useful for the identification of orchids? Is it the color, is it the size, the shape, the number of petals, how big the plant is? So which features are relevant and which are irrelevant for identification of flowers? So I was asking about identifying a flower domain. Right? I knew very little. I guess after reading, I realized there's actually 3 petals and 3 sepals. The middle lip is itself a petal, right? So not knowing anything about this flower domain and only having seen a few orchids, could I classify some other ones that looked somewhat different, right? So the ones on the right are also orchids. They have these, the red one has these thin petals and the purple one's got these fat, plump ones, right? So the idea is that to do this kind of few-shot symbolic learning, classifying things in terms of their features, I had to understand something about the domain first. There's simply too many features to consider as a newcomer, right? And learning the domain should somehow permit learning concepts from few examples, right? I think this is kind of pervasive, right? And people tell me in bird identification, it's sort of similar. There's all these things that you learn to look for on the bird to classify them, right? I think it's similar also in other domains of learning, so understanding mathematical structures like graphs, right? You first figure out what are the relevant questions. There's nodes and edges, and people care a lot about connectivity. And then seeing a few examples of more exotic graphs, you're more prepared to quickly learn them. This also comes up in programming languages and verification, so trying to learn programs from few examples, the classic case being spreadsheet automation in Excel, so you have a few input-output examples. You're trying to learn a program that somehow captures a user's intent and can help automate filling in the spreadsheet. Or you're trying to prove programs correct, and you need to find these inductive invariants, and you can treat this hard problem as a learning problem. I'm going to learn a logic formula that expresses the invariant from states of a protocol, so sample behaviors of programs. Right? In all of these cases, the challenge is often to understand the domain well enough to write down a DSL which captures the common concepts and computations for that domain. And then often people have designed, synthesis algorithms specifically to those DSLs, right? But typically I think the step 2, designing the DSL, is done with an eye toward 3, right? So how can we come up with a DSL so that some kind of few-shot synthesis algorithm is likely to succeed? So this is the step we're interested in here. So one way DSLs can make this feasible, few-shot learning, right, is to express relevant things succinctly. Another thing they can do is express irrelevant things less succinctly or perhaps not at all. Right? So if we take the spreadsheet domain, many programs are going to do things like split strings on white space and capitalize things and manipulate dates and times and formats like that. But they're unlikely to do ASCII character code arithmetic, right? So a good DSL for spreadsheets will exclude that. Right? The more general observation is that useful DSLs are often less expressive than general purpose languages. This is the kind of abstract setup we're considering, right? So given just a few examples, some learner has to produce a hypothesis in a symbolic language, a DSL, that's consistent with the examples, except we don't have the DSL here. So the goal is somehow automatically construct a DSL so that this particular class of learners biased towards simplicity are likely to succeed from few examples. The first contribution of this work is a new formulation of DSL learning, or DSL synthesis, itself as a learning problem. So what do I mean? Suppose we have a few-shot learning instance, just a few input-output examples on integer lists, and we have a fixed DSL programming language, and we're going to take a very simple algorithm that just enumerates small expressions and increases the size as needed, enumerating programs until it finds one consistent with the examples. Okay, so here it found concatenating the input list with itself, right? That's consistent with those two examples, right? But now imagine that I held out a testing example on which the concatenation program is not correct, right? But perhaps if we had looked for a slightly bigger program, we would have found this one, the stutter program, which is just repeating each element of the list once. So that would have been consistent with the training and the testing examples. But we didn't find it because we were using an algorithm that was going to pick the simplest program. Right? So one could blame the algorithm, or one could blame the language here, and we're going to blame the DSL. So we're going to say, we like the algorithm that picks simple concepts, and we're going to try to get a new DSL that can solve these problems. So the idea is to take these learning instances, split into training and testing sets of examples, and treat them as a kind of DSL learning example. So the learner knows that it's going to be tested like this, and it gets to see the training and the testing examples. Okay, just to formulate the problem more precisely, the learner, the DSL learner, gets multiple of these few-shot learning instances, and its goal is to somehow construct a DSL that maps some concepts sort of higher up in the DSL in the sense that they require more complicated expressions to express, and the solutions, the expressions that solve both the training and the testing examples should be expressed more succinctly relative to those concepts. And another feature of this formulation is that the DSL can choose not to express some concepts at all, right? So whatever mechanism we're using to define the DSL, we might end up with one which is less expressive than we started with. So this is just a precise problem formulation. We fix some base language L, and a notion of complexity of expressions in the language L. And we're given a set of few-shot learning instances, as described, and then also some kind of metagrammar, which is specifying the space of possible DSLs. And the goal is then to synthesize a grammar in that space that contains some solution for each one of these learning instances, which is also somehow minimally complex among all the expressions that solve the training sets of examples. This is just formalizing the intuition from previous slides. So as an example, imagine you had a language of, you're trying to classify points in the plane, and your language consists of some primitives which are specifying rectangular regions of the plane, and you have maybe many of these regions at your disposal, but finitely many. And you're trying to cover some positive points and exclude negative points. And imagine the training examples are positive points and the negative examples are testing points. And what you see here is that for this language, it's not suitable for this learning instance because it expresses a very small disjunct which covers the positives but doesn't exclude the negatives. whereas a larger conjunction with 3 terms does capture the data set, but it's larger, right? So the idea is a DSL, in this particular case, should favor conjunction over disjunction. Okay, the second contribution is a set of decidability results for this problem. So what is decidability here? Remember, we're given some learning instances as input and some description of the space of possible DSLs. And decidability is trying to answer the question, does there even exist a DSL in this space which has these properties, right? So can we synthesize one if it does exist and also terminate and say, no, no such DSL exists? So that's decidability. We have a theorem which says that DSL learning is decidable when the complexity measure is parse tree depth. And this is actually a meta theorem. It holds over any base language with a finite aspect evaluator. So we get as corollaries concrete DSL learning results. Now this finite aspect evaluator thing, this is referring to some prior work of ours showing that a large class of languages admits decidable learning. So we have decidable DSL learning results for any of these base languages, including first order logic with recursion. Just a brief sketch of the proof idea. We have these learning instances, and we have to decide, is there any DSL at all that could work? So what we do is we design a tree automaton, that's A, which reads a tree that encodes a DSL, and it traverses this tree up and down many times to check these conditions. It says, does there exist some sufficiently succinct solution? Okay. And eventually it outputs yes or no, and hopefully it only says yes on the DSLs that have these properties, and it says no on the ones that don't. Once we have A in hand, the decision problem for DSL learning reduces to tree automaton emptiness with some standard techniques. Okay, there's more in the paper, including some variants of this problem and decidability results for those. In particular, we looked at a natural weakening of the problem, which we called adequate DSL learning. So this is the version where we don't have these test sets, and we just have a bunch of examples as a learning instance, and we're trying to make sure that our DSL expresses a solution for each of them. We also looked at varying the mechanism by which you define DSLs. So instead of using grammars, we can use something slightly more expressive, a macro grammar. So this is a grammar that has non-terminals which can take parameters. There were also some unresolved theoretical questions. In particular, are these problems decidable when the complexity measure is parse tree size? So we have results for depth, but is it decidable for size? We don't know. Future work will be to find an efficient algorithm and implement it. So this is the decision procedure here is very complex. I think an interesting question is, can useful DSLs be learned from this specification? And if so, how much data do you need, right? Okay, so that's it. This is I think a very interesting new formulation of DSL learning, which is about precisely identifying a domain for the purpose of few-shot learning. And it introduces a kind of signal related to inexpressivity and succinctness, where solutions to learning problems should be relatively more succinct to tempting non-solutions. And we proved decidability for a rich class of base languages. That's all.
Hi, cool topic. Are you familiar with ADF, automatic defined functions?
No.
In the world of genetic programming. So it's very similar to the DSL learning. They just, instead of using, well, they also use grammars, but their DSL is a subset of functions that can include new functions that are defined based on the basic elements. So I think your work should also apply to that area. And the part I want to ask you about is, do you know the ARC prize, the automated reasoning corpus?
Yes.
So would this work given enough computational time?
Yeah, this was actually partly kind of in spirit motivated a little bit by thinking about ARC, right? So you have in ARC these abstract reasoning puzzles, few-shot learning puzzles, but there's no formalized DSL. So there was a question of maybe one should discover the DSL for ARC. And I think this problem, you know, if you could solve it, it would be interesting to see. You know, run it on the publicly available ARC puzzles and obtain a DSL and then try to solve with that.
We should talk as there's a DSL available, but there's also the challenge of discovering it.
Yeah.
One more really quick question while Anna's getting set up.
Okay. Yeah, I'm wondering why do you define this in fusion learning? It seems that your problem definition is quite general and applicable to any DSL learning scenarios.
I'm sorry, I missed the first part.
Why do you add this few-shot learning scenario in your title of your paper?
Why few-shot learning?
Why few-shot learning?
Yeah, I think you know, if you have a lot of data and you want to learn something, you know, it seems more in the domain.
Your approach seems to be more general than few-shot learning, right? It's general DSL learning.
Yeah, well, I think the problem of identifying the domain is really a problem for few-shot learning. So you want to do learning from few examples. How can you possibly do that without somehow constraining the space, right? So.
Okay.
Yeah.
Yeah. Thank you.
All right, let's thank the speaker again. All right. So the next paper is Synthesizing Implication Lemmas for Interactive Theorem Proving, and Anna will be giving the talk.
Okay. Are we ready? Can you guys hear me? No? How about now? Yeah? Okay. Alrighty. Let's talk about lemmas. Okay, so we are all here because we're all computer scientists, specifically those that love programming languages. And so I feel like it's safe to assume we've all written a program before, and that means it's probably also safe to assume that we have written a program that does not work. And everyone's familiar, and maybe not everyone, but most people are familiar with formal methods, specifically with interactive theorem provers like Lean and Rock that are getting a lot of traction these days. And these tools let you formally verify your software, so you're able to prove properties about your programs or mathematics or other systems that you care to specify. But this still begs the question as to why we still have bugs in software. And it's because these tools aren't necessarily easy to use all the time, and there's a burden, whether it's time or difficulty, to verify your stuff in them. And so we're going to walk through an example of trying to verify selection sort. And this comes from the Verified Functional Algorithms textbook in the Software Foundation sequence. And the main property you might want to verify about your selection sort, or any sort for that matter, is that it correctly sorts your list. And the Verified Functional Algorithms textbook, along with the other Software Foundations textbooks, are in Rock, and they provide you with a sequence of lemmas to prove.
Your mic is, when you face that way, you break it so they're not working. Yeah, so just like that.
Keep it like that? Okay, hold on. Can I hold it? Okay, I'm just gonna hold it. I'm gonna hold it then. Okay, where was I? Okay, so if you want to prove that your list is correctly sorted, in this case, you might want to prove that this following property, that if you have an element n and it's less than every element in your list, and then you're able to correctly sort that list using your selection sort, then if you put that element at the front of your list, then the list will remain sorted. And it's important to note in this context that LEAL is a proposition, an inductive proposition, that is defined in conjunction with your list, and and you want to reason about how this proposition works in comparison with your property you care about. And when you're trying to prove this property, you need to prove it, and there's additional lemmas that might help you prove it. Okay. So when you're using an interactive theorem prover, you do it tactic by tactic. And whether you're doing it manually or you're using some kind of automated tool, it's doing a next tactic prediction. And often these tools, or you yourself as the prover, have access to prior context. And specifically, we're talking about lemmas. And so often these techniques will consider the helper lemmas, and the specific helper lemma that's useful in this context is the following, which states that if you have an element that is less than all elements in a list, and you know that another element is within that list, then the element that is less than all the other elements will be less than the element in that list, which is on the bottom there. And the Verified Functional Algorithms textbook provides you with this lemma, as well as others that are useful in completing your proof. But this begs the question of, if you're verifying your own software that you've created, or anything else for that matter, then what happens when you don't have access to these lemmas? And you might get stuck, whether it's you proving it yourself, or especially an automatic tool that's used to having access to prior context in a lot of its training. And so this is where we get our problem statement from. How can we determine useful helper lemmas that help us complete our proofs from scratch? And so we're going to define the problem of directed lemma synthesis. And there's a variety of different techniques that you can use to come up with lemmas or other useful properties. But when we say directed lemma synthesis, we're referring to the context where you have an incomplete or a partial proof, where you might be stuck, and you don't know how to continue, whether, again, it's you or some kind of automation technique. And the result is a list of potentially useful lemmas that can be used to help you complete or make progress in the proof at your given point. And so we created a ROC tactic called Dilemma that implements our approach. And there have been prior attempts at, and successful attempts at, lemma synthesis. And so I'm going to talk a little bit about what makes ours different. So if you remember from previous slides, this is the helper lemma that is provided within the scope of the Verified Functional Algorithms textbook that's used to help complete the proof that we care about. And you'll notice that this lemma includes implicants and is an implication. And so we're going to generalize this and say this is an implication lemma, just meaning that it has an implication in it. And a lot of prior lemma synthesis work targets atomic lemmas. So these are things that will be useful in rewrites or direct application. But for our context, and in a lot of contexts when you're writing lemmas, you often need implications. And so for that reason, we're targeting implication lemmas rather than atomic lemmas. And there also has been prior work that will yield atomic or implication lemmas, but these approaches are kind of restricted in how they search the space. They're specifically heuristically applying rewrite rules, which will only yield things that are constrained by equality. And so the search space of implicants is a little bit constricted. And so for that reason, we're going to reduce our problem to a data-driven program synthesis problem, which lets you increase expressivity over the types of terms and propositions that you're searching for. We had evaluated our tool on 226 locations in the Verified Functional Algorithms textbook, and what this means is that we had completed the proofs, someone had completed the proofs, and wherever there was a helper lemma used, we checked if our tool could find that helper lemma. And in 43% of the places we did either find an exact match or a similarly useful lemma, and the exact characterization of that is within our paper. And so the question is, how exactly do we do that? And so we're starting with our implication target. So we know we're targeting an implication lemma. And specifically, this is the one that we're looking at in this example. So LEOL of n in L, so n is less than all elements in L, and the fact that x is in the list L means that n will be less than or equal to L. And so for those who are not familiar with an interactive theorem prover, which leverages tactics, this is kind of what your interactive setting of the proof looks like. The top 4 lines are going to be your assumptions, so things you can take for granted or assume to be true in your proof. And the bottom line is the goal that you want to prove. And so for targeting a lemma that is going to be applied in this instance, it's kind of natural that you'd want your goal to match the result of your implication so you can directly apply it. And in this case, you'll see that that's how the lemma was used. And so we're able to get our goal or our result of our implication from the goal of our lemma. And then the question comes, how exactly do we find the implicant? So what are the preconditions or the guards on this goal? And a natural place to look is the assumptions. These are things that you can assume to be true. But in this case, you'll see that there's quite a bit of assumptions, and not all of them are always necessary. And oftentimes, good lemmas are more refined, and so it's kind of specifying the exact properties that you need in order to complete the lemma. And so that's our challenge. We have too many assumptions. How do we actually determine which ones are relevant to what we're trying to prove? And so our goal, with that being said, is to determine a minimum set of assumptions which imply the goal. And as I alluded to a little bit before, we're going to take a data-driven approach. And so before I describe that, it's important that we understand what exactly I mean by data. And in this context, data is a sample valuation over all the variables, specifically that falsifies the goal. So an example of this would be something like this, where you have values associated with each of the variables. And you'll see here, if you just plug the values through, that n is in fact not less than 2. And so we can also see how this example performs on the assumptions. And if we want the proof state to remain valid, either the goal has to be true, which is not the case, which means that there has to be some assumption that we are considering that will be false. And so in this case, it's the first assumption. And so we keep this assumption in our set, and you'll see that it is one of the implicants in our lemma that we're targeting. And so we repeat this process of ensuring that all the sample valuations that falsify the goal are somewhere in our assumptions, or falsifying an assumption. And we repeat this until based off of our type generations, or type-based generations, don't have any counterexamples on the goal that are not falsified by an assumption. And so we're left with this. And so if you look at this lemma here, this is actually a useful lemma. We've reduced our assumptions to be the ones that are relevant to our goal. And so we can return this, we can consider this and give this to the user. But oftentimes we want to do something a little bit more, and specifically we're targeting this lemma here. And it's pretty similar, but you'll notice that one of the assumptions is actually a bit too strong for our case. And so this will actually be the bottom lemma will be a stronger lemma than the top lemma, because one of the assumptions becomes weaker, which is hard to think about, but if your assumption becomes weaker, your overall lemma becomes stronger. And so now we're targeting weakening this assumption. And this is where the data-driven synthesis comes in. We want to reduce this problem of weakening an implicant to a data-driven synthesis problem. And we do this by isolating sets of positive and negative examples. And in this context, an example is similar in the last context. It's different valuations of every variable in the proof step. And we're in charge of splitting apart these examples into positive and negative ones, where the positive ones should be true on the resulting result of our synthesis, and the negative ones should make that result false. And so effectively what this does is this searches for a term that is implied by the assumption. In this case, we end up finding that x is an L. And if we look at the bottom, it's kind of maybe clear to see that if you sort a list L and it's equal to a list that starts with X, then X is in fact in L. And so this itself is also a lemma. And when we plug that value back in, we end up with our target lemma. But we were able to get it not by using our brains like the people of software foundations, but by using a tool that performed data-driven synthesis from the goal state. And so our overall approach has 2 passes that go through it. We just described the top one. The bottom one is a case where your proof state is a little bit different. And we don't have time to go over that, but it uses a similar-ish technique. Instead of weakening assumptions, you're inferring ones that are needed. You can see the paper for that. Directions for future work would include first improving the actual lemma synthesis. One big area that we'd want to look at is incorporating stronger forward reasoning. So we're targeting more of backwards reasoning, where your result is a goal and you're trying to get that. One forward reasoning approach would be to work forward from your assumptions and prioritize that. Additionally, we're all aware everyone likes to use LLMs for things, and so it might be beneficial to incorporate this tool with LLMs to help kind of determine, to synthesize helper lemmas as you go, or even further determining when a helper lemma is actually needed. And in summary, we have proposed a data-driven synthesis technique for implication lemmas and implemented it in a ROC tactic and evaluated it on some benchmarks. And going forward, I think this area is really interesting, and I think that it's worth thinking about how you can deconstruct proofs to aid in either proof automation or creating tools that help users actually work through their proofs in a way that makes more sense as opposed to just hacking at it. Thank you for listening. If you have any questions, comments, or discussion, feel free to reach out, and I can take any questions anyone might have. Sorry about the mic.
We have time for one question.
Yeah, thanks for the great talk. I'm wondering if in the current proof state, if we have quantifiers, like existential quantification, does your approach still work or not?
The approach, I think, conceptually works. In terms of the implementation, you run into some issues, so that would be included in the category of improving the implementation. Like, for example, we don't do function types because we weren't writing generators for function types. That's a little bit complicated. But so that would be a category where I think theoretically it would work, but in terms of like actually identifying and generalizing and instantiating examples, it would be a bit more complicated. Does that answer your question?
Thanks.
Yeah, thank you.
All right, let's thank the speaker again. All right, and the last talk of the session is synthesizing sound and precise abstract transformers for nonlinear hyperbolic PDE solvers. And Jacob will be giving the talk.
All right, everyone. Well, thanks for being here. I'm Jacob. I'm an assistant professor at Georgia Tech. And this is joint work done with my collaborators, Ignacio and Jan, who are at the Department of Energy. And I'm here to tell you why scientific computing needs program analysis. So partial differential equations are everywhere, whether you want to model things like fluid flows or electromagnetic effects, or even traffic congestion. All of these processes are described by partial differential equations, or PDEs for short. Now, in particular, these examples all fall under the umbrella of hyperbolic PDEs. Now, I realize that this is a lot of terminology to throw at you, so as just a brief roadmap of how we're going to get to a point where we can make sense of things, is that we're going to define what these equations are, then we're going to show how one solves these equations, and that will allow us the necessary background to understand how to analyze those solvers, and then we'll be able to see how to use that analysis for end-to-end verification. So the requisite PDE background is as follows. You may be wondering, what is a hyperbolic PDE? Well, the hyperbolic PDEs that we're going to consider are partial differential equations of this form, where you have a time derivative and a spatial derivative. And the solution U is a function of both space and time, and it quantifies where the wave is at different points in time. Now, we also see this function F, which is known as the flux function, and it governs how the wave flows. And it's typically a nonlinear function. So why are these PDEs so interesting? Well, it turns out that that nonlinear function leads to a lot of nonlinear behavior, which can even manifest as shock waves forming in the PDE. Now, these PDEs are also interesting because there's a lot of key numerical properties that must be satisfied. And the waves transmit at a finite propagation speed, which we'll see later why that's important. So going back to our roadmap, having now defined what these PDEs are, now I want to talk about how one actually solves these PDEs. So how are hyperbolic PDEs solved? Well, you might try to whip out a pencil and paper, but you won't get too far because these PDEs tend to be very intractable to solve analytically. So what you have to do instead is resort to numerical methods. And these typically involve some kind of discretization that you then implement as a computer program. Now, our work will focus on analyzing those programs. And why do you want to analyze these programs? Well, there are a lot of things that can go wrong with these programs. For instance, they can introduce artificial wave dissipations, they can introduce artificial oscillations, they can even experience things like overflows due to some of these numerical properties being violated, and shock waves, and many different things can go wrong. And so this is really a broad new class of numerical bugs that extends beyond traditional floating point errors. So wouldn't it be great if we could verify the absence of these bugs? Well, we can do that if we use formal verification. So before getting to that, let me just give an overview of how these solvers actually work so we know what we're actually going to verify. So what we'll do is we'll discretize our physical world into the computational domain. So that means we discretize space as well as time. And so we get these discretized mesh points at different points in space and time. Now, how do we compute those mesh points? Well, that's where finite difference schemes come into play. So we have the Lax-Friedrich scheme, the leapfrog scheme, and the upwind scheme. Now, there are other schemes besides these, but our paper focuses on these three. So the idea here is that we're going to compute the n+1th time step as a function of all of the earlier time steps. And then we can actually take that process and implement it in code. And we see that there's this natural loop that loops over the different time steps that encodes the finite difference scheme. So now going back to our roadmap, having talked about what hyperbolic PDEs are and how they're solved, now we're laying the groundwork to discuss how to actually analyze the code, which is really our core contribution. So our tool is called Focus, and the overview is as follows. So if we go back to these schemes, we'll have some code implementation, and then we're going to analyze that code using abstract interpretation. Now, we're also going to use numerical optimization techniques as well for reasons that I'll now describe. So here we have that Lax-Friedrich scheme. Now, our goal is to get precise bounds on the set of values that those mesh points could take on. So naively, you might think about doing some kind of interval arithmetic where you would abstract the values of these individual operations, like these additions, and then these subtractions, and just compose those intermediate results again and again until you get your final answer. But the problem is that the imprecision would accumulate. So rather than this imprecise strategy, we want something better. We want a tighter bound on the values that this mesh point can take. And so we want to actually optimize for a tight enclosure for the entire stencil. And that's the core idea behind our tool Focus. And we want this not just for the Lax-Friedrichs, but also for the leapfrog scheme and the upwinding scheme as well. So how do we actually optimize for these tight enclosures? Well, this is where continuous optimization saves the day. So this is really inspired by a lot of deep neural net verification works. And so our strategy will be to find a linear approximation of that finite difference scheme, bound the approximation error, and voila, we get abstract transformers that are sound for any linear abstract domain. So here we have the Lax-Friedrich stencil for the cubic flux function. And if you were to plot what that finite difference scheme looks like as a function of the mesh points, you get this nonlinear curve. But it turns out a linear approximation is pretty good. And so we can find one, and then all we have to do is get a sound enclosure around that linear approximation. And so that means we have to compute this term D. Now, we want the tightest such D to give the tightest bound. And that involves solving this non-convex optimization problem, which seems a little tricky, but actually using clever techniques from the optimization literature, we're able to make it tractable. Now, going back to our roadmap, having talked about how these PDEs are solved and how we can analyze those solver schemes to get precise bounds, I want to describe now how we can actually use those results for full end-to-end verification. So what properties can these PDE bounds verify? So we can reason about the robustness of the PDE to different initial conditions. So if you run the PDE with different initial values, what will the solution look like after a certain number of time steps? And if you want to get a robust range, well, you can use our analysis. Another key property is the CFL condition, which is a very important property for understanding the stability of the solver, because it relates the wave speed to the mesh discretization that you've chosen, and it must be satisfied at every iteration of that for loop that I described, and so really, it's a loop invariant. We also formalize the notion of total variation, which characterizes the amount of spurious oscillation and dissipation. And we also want to verify the absence of shock waves forming. And so given these 4 properties, if we have tight bounds, we can actually verify all of them. So you may be wondering, how well does this technique perform in practice? Well, we did an evaluation to see where we compare against like the standard abstract transformers with the zonotope domain, and the standard abstract transformers compose all the primitive operations together. And we'll see how that leads to imprecision. Now, we also solved the PDE for concrete sampled inputs as a sanity check, and I'll describe that later. And we measured the runtime, the bound precision, and we verified the properties that I described earlier. So we looked at 6 different partial differential equations where we have these different flux functions. And noting that the form of the hyperbolic PDE, the flux functions will be substituted in for that f of u. In fact, that's also what gets substituted in the finite difference scheme. So I'm going to focus now on the results for the Burgers PDE. So here we have the results for simulating the Burgers PDE with the Lax-Friedrich scheme. Now on the x-axis is the point in space, and to denote different time steps, we have these 4 different plots. So we have these green bounds that represent the values of concrete samples. So the desired behavior is to, as tightly as possible, enclose these green bounds. And this is really our sanity check, because any sound method should enclose these. So the naive bounds are sound, but they're not as precise as our bounds at enclosing those green dots. So the effect is even more pronounced if we look at the leapfrog scheme for the same Burgers equation. We see the naive bounds are very loose, and they're too imprecise to be able to verify the absence of shocks, nor can they verify the CFL condition. In contrast, our bounds are much more precise and can verify no shock waves, as well as the CFL condition being satisfied. Similarly, in the upwind finite difference scheme, we see that the naive method is very imprecise and cannot verify the properties, whereas our method, Focus, is much more precise and can verify those properties. And so even on different benchmarks, we see the same trends. And so as a measure of scalability, we also looked at what happens if you run for hundreds of time steps. And so in this benchmark, we ran it for 280 time steps, and this is about a little over 5,000 total mesh points. So about over 5,000 variables in your abstract program state. And we see the bounds are still very, very tight. And so in summary, we started with the notion of a hyperbolic PDE. We showed how those hyperbolic PDEs are numerically solved, and that allowed us to talk about our contribution of statically analyzing those solver codes, and then using those results for end-to-end verification of formal properties over PDEs. And so our tool Focus is the first abstract interpretation of hyperbolic PDE solvers that uses these precise linear bounds, and it's the first to verify these PDE-specific properties for scientific computing correctness. So on that note, I will take questions. Thank you.
Does it work? Okay, very nice talk.
Thank you.
I'm Chuan from UC San Diego,
okay.
And I'm actually working on probably the same problem, but in a different domain. We synthesize abstract transformer for compiler, data flow analysis in compiler.
Okay.
So I think we're also trying to identify the common pattern in the compile code, just like you synthesize a transformer for those complex function you show in as a large box to avoid the imprecision decreasing. So I'm wondering, like, did you manually discover this kind of pattern, or you have some way to automatically find this pattern, like in your PDE setting?
Yeah, great question. So did we manually find these patterns, these different finite difference schemes, or is there a way to automatically figure out what's a good pattern to design something more precise for? So for these, we did just kind of manually play around with different finite difference schemes and found that these ones had the nice properties that allowed the optimization to be precise and sound. And so we haven't explored yet if there's an automated way to figure out new types of expressions for which you could find a more precise bound. But I think that'd be a great future direction. Yeah, it's a great idea.
Oh, great. Thank you. If nobody, can I ask a second question?
Sure, of course.
So whether your synthesizer transformer always reach the tightest bound, or you just want them to be as tighter as possible?
So it's not the tightest bound because with zonotopes there is no most precise abstract transformer for the zonotope abstract domain. But for the given linear regression plane, we get the most precise bound for that particular plane. But whether or not there's a different linear regression that's more precise, it's not really possible to say with the zonotope abstract domain because they don't have what's known as a most precise abstract transformer. So it's probably more the latter. It's like as precise as possible. Yeah.
Got it. Thank you.
Awesome. Thanks.
All right, let's thank the speaker again. That was the last talk of the session. I did want to put in one plug. There was a speaker who couldn't get here, and so the talk, there's no talk, but the paper is multimodal sketch-based behavior tree synthesis. So you didn't get to hear a talk in this session, but be sure to check out the paper. Let's thank all the speakers again.
Glad you could join me in this very cold room. So I'll be talking about refinement, and I should say this is joint work between João, Peter, and myself at ETH Zurich. So let me quickly set the scene for what I mean by distributed programs. So imagine you are writing a server application in your favorite language, which is Rust, and you want to verify that it behaves according to some protocol. So for this simple example, we can say, okay, when this server receives a ping message, it should respond with a pong message with the same value. And that's fine for this kind of tiny example, but it doesn't really scale. So our main case study for this work was a system called memcached, which is an in-memory cache system that clients can connect to and use as a cache. So it has an implementation in C++, but crucially it has a extensive documentation which basically specifies what is the protocol that memcached implements. And we have developed multiple versions of sort of a subset of memcached in Rust, starting from a very simple implementation that was single-threaded all the way to a more complex multi-threaded implementation with fine-grained locking. And essentially our research question was, is it possible to develop a methodology that can apply to such realistic protocols, can support real-world languages such as Rust, allows for the code base to evolve over time and change, by which we mean we don't want to have too tight of a coupling between the implementation and the model. Allows for the eventual implementation to actually be efficient, so use things like atomics and multiple threads and so on, and all the while avoiding large manual proofs in thousands of lines of interactive theorem prover scripts. So we answered this question in the positive, I guess, with our methodology. So our methodology is using a refinement technique. So this essentially means that we want to relate the steps of the concrete execution to the steps of the model. So the concrete steps have some concrete states consisting of the program variables, the call stacks, the threads, and so on, and evolve according to, well, the definition of the Rust language, so the operational semantics. And if this is a distributed system or a multi-threaded program, then what you actually have is multiple nodes where no single node has a sort of a complete picture of the full state, and the steps that these nodes are taking aren't well ordered with respect to each other. They happen in parallel. And on the model side, well, I said we start with this specification of memcached written in technical prose, but this is not a formal approach, so what we use is a transition system. So you can think of formalisms like TLA plus or veil as ways to do this, but essentially you need to have a notion of state of a bunch of variables and their types, and a set of labeled actions which decide how one state can move into another. And the refinement proof is essentially trying to establish a connection between all of the actions of the implementation and this model, specifically by classifying each step of the implementation into stutter steps, which don't really reflect in the model because they're sort of local changes that are not observable, and actions, which, for example, things like sending a packet to the network, which are observable to other nodes in the system. So they had better behave according to the protocol. So let's zoom in on how we verify a single step of the implementation when it's performing an action. To do this, we make the observation that most of what the implementation does is not relevant to the refinement proof, because most of what the implementation does is changes to the local state or bookkeeping or method calls, which just aren't observable by other methods. By other nodes. And so the places where the action is actually taking place, where something is happening as far as the model is concerned, we delineate using what we call transition blocks. So you can think of these as critical sections of a global lock protecting the model state. And they basically tell us a couple of important things. They tell us where is the transition actually happening. So this is where we do our refinement proof. They tell us what actions we're taking in the transition block. They tell us how the implementation is updating the environment by using standard library or IO method calls, and potentially also how the model state is updated for the sake of the proof. And so it's important to note that these IO operations, like sending packets to the network, are just not allowed outside of transition blocks. But we face some issues, I guess, because we said at the very beginning to try to develop an automatable methodology. And so we want to verify these transition blocks in a modular fashion if possible. It should be possible to verify each of these in isolation without having complete knowledge of the global trace of steps that happened before the transition block. Which means that to be a completely modular approach, we must assume that the initial model state at the beginning of the transition block is essentially arbitrary, which is an issue because we sometimes want to perform actions which have preconditions. So we need to know something about the model state at the beginning of the transition block for us to actually take an action. And so the way we solve this issue is with something we call local reasoning or locally inductive invariance. So let me motivate this with a very simple example. So imagine you have a shared counter which starts at 0, and it can be reset back to 0 or incremented by 1. And you have multiple nodes operating on this shared counter in parallel. And now the question is, if one node performs an action like increment, can it assert that the counter is greater or equal to 1 immediately after? And the answer is unfortunately no, because immediately after the increment, the other node could have reset the counter back to 0. So what we can do is say that certain actions of the system are only possible to perform by certain nodes in the system. So we give them roles or guards. So if, in this case, the reset action was only performable by the left node, then after incrementing the counter, it can actually assert that the counter is greater or equal to 1, because the other node cannot reset it. It doesn't have the permission to perform the reset action. It can only increment the counter further. And so this kind of assertion is what we call a locally inductive invariant. It is not an invariant of the system in general, but it is an inductive invariant as long as you hold on to some guards which prove that it must hold. So back to our example, we make use of guards and guarded transition systems, as we've seen, to deal with these situations. So our notion of a model is no longer just a transition system. It is a guarded transition system with a set of guards and a specification which says which guards are required for which actions. But dually, the guards are also resources in the implementation. We represent these guards as a type, an opaque type in Rust. And what is very nice is that we can rely on the existing Rust ownership type system to actually track uniqueness of guards as they flow around the implementation. And so with the guard in hand, the implementation can basically use it as a justification for a locally inductive invariant. The actual reasoning that happens at the point where we are applying a locally inductive invariant is essentially a kind of induction principle. The relevant proof rule is here on the slides, but essentially it just encodes the intuition that we have seen before. But of course, feel free to check out the paper for more details. These locally inductive invariants are crucial to our methodology, and we have seen that they can indeed decouple implementations from the model. So at the beginning, I have said we have developed different versions of memcached from single-threaded to multi-threaded with fine-grained locking. And as you can see in the evaluation here, although the code has actually changed significantly, so this is the first first column of numbers, the model is almost the same. Like, we have declared more guards, but it's the same model that we're refining against. So this gives us very strong assurance that these locally inductive invariants is what we want here. On the topic of the evaluation, we have also implemented algorithms from the literature, such as Paxos, or concurrent data structures like a lock-free data set, hash set, and a queue which uses different kinds of atomics for synchronization purposes. All of what I've been describing exists as a library in Rust and more specifically in Proust. So if you look at our artifact, you can find extensive documentation on how these types actually work, and they map quite nicely also to Rust. For example, different models in our methodology are just different implementations of the model trait. So what I haven't talked about in this talk is, well, why this locally inductive invariant reasoning is sound. So we present a small formalization argument in our paper. We need to ensure that these transition blocks are actually kind of atomic. So we use a linearization argument for these purposes. We have also specified some parts of the Rust standard library, and we talk about how to write these specifications compositionally. So to summarize, I have presented a novel refinement methodology for languages like Rust, usable with verifiers like Proust, but really what is needed is kind of separation logic reasoning with a focus on modularity and compositionality. Our key ingredient was this locally inductive invariant concept, and all of this exists as a Proust library evaluated on several case studies. Thank you.
We have a couple of minutes for questions. Please come to the microphones if you have questions. I might get started. What kinds of properties might you extend this to be able to verify in the future? Is there anything that's out of scope at the moment but would be your future work?
Thank you. Yeah, so for now, this focused on safety properties. So basically showing that the protocol is not violated at any step. But we do want to extend this to liveness properties as well, and we have some prior work already on this that we will publish in the future, I guess.
Hi.
Yep.
To verify your examples, do you have to manually add those guards in your code, in your implementation?
Yes, you have to add some annotations to the implementation. You need to, I mean, this is the sort of setting of modular verification, so you need to add things like preconditions, postconditions, and loop invariants, and this is where you would interact with the guards the most.
So those annotations are actually checked by the Rust type system. It is a kind of...
The ownership of the guards is checked by the type system, but the way you use the guards is checked by the verifier.
Oh, okay, yeah, thank you.
So that you don't create two guards that are kind of allowing you to do the same thing, or how do you manage that?
There's a set of guards that exist in the system to begin with, the full universe of guards, and you can sort of from the start give those guards away. And in the case of something like a distributed system, you have to model this initialization because it doesn't actually happen in a single program.
Okay, I was also wondering about that. Thanks.
Thank you.
Okay, our next speaker is Chen Yuan, who will present to us Autoverus automated proof generation for Rust code. Please go ahead.
Thanks for the introduction. So hello everyone, my name is Chen Yuan. I'm a fourth year PhD student at UIUC. Today I'm very glad to talk about our paper, Autovirus, Automated Proof Generation for Rust Code. So I think many of you guys have already using learning model when you are coding. So for instance, Cloud, Cursor, Copilot. And a survey last year shows that over 60% of people are already using AI tools in their development process. So however, we could say that some of them say no, and I don't plan to. So the reason is that many people doesn't trust the output or the answers of AI. So a question coming in mind is, how can we trust the AI-generated code? So before answering this question, let's take a common usage of the AI when coding. So for instance, you want the AI to help you write the implementation code for binary search. Then the AI generates the implementation code, and here is an example implementation in Rust. After that, you may use some test cases, let's say, to say whether the implementation code passes the assertions. So however, we know that passing those test cases doesn't mean the code is 100% correct. And indeed, for this example implementation, there is a bug in it. So the question is, can we really trust AI-generated code? So the answer is yes, we can, and we can use the software verification, which can prove the properties of the code of all possible executions. So, but the thing is, as developers, so we don't want to write those proofs because it's tedious and non-trivial. So our solution and our talk here is about how to teach AI to write those code proofs. But before that, we need to select a good software verification tool that you can verify
So, as mentioned, I am presenting on information flow control. Fundamentally, however, what I'm talking about is the trusted computing base and trying to reduce it. There's a significant security problem with kind of just the world as it stands right now, which is that both developers and users have to trust code to do what it claims to do, or to do what it's supposed to do. So let's look at an example of this, of an application that users and developers have to trust. This is Servo. It is a rendering engine and web browser. And fundamentally, what's happening here is a pretty typical web browsing session. A user uses a keyboard to enter in keys, and then those are combined into various data. You can see here that what's happening is the user is attempting to donate to the Red Cross, so they're providing their credit card information. And at the same time, they're making the dubious decision to go check out evil.com and see how well that's going. And they're trying to enter in their login info there. Now, fundamentally, if the program operates this way, this is fine. Maybe the user is being a little unintelligent and going to check out evil.com, but there's no information being leaked here. There's no actual problems. But what if it doesn't operate this way? What if it looks more like this, where instead of the data flowing through the right streams and then it winds up getting sent to the right place, what if instead there's some other chunk of code that developers aren't aware of that just directly sends the information, all information, to evil.com? Or it goes through the networking but still sends it to evil.com. Developers have to trust that this pretty bad violation of confidentiality won't happen. And Servo's computing base is massive. Servo is over 1 million lines of code. So the trusted computing base for this example is insanely and impractically large. Now, to make matters worse, this is what real instances of this problem would look more like. It's not just the Red Cross and evil.com. The user might also have Google and Amazon and Twitter and another website and another and another and another. Just speaking practically, I've seen a lot of professors' computers at times in the middle of class where if they only have 10 tabs, it's impressive. So the number of tabs can be quite large, and more pointedly, it can't be known at compile time. It can only be known at runtime how many different tabs, different sessions you have active at once. Fundamentally, this is an information flow control problem. We need to limit what information can flow where. There have been decades of work on this problem, but it's still, in many ways, an unsolved problem. A couple of ways you could try to do this just don't work. Static analysis leads to numerous false flows, so trying to do a whole program analysis is impractical. And access control doesn't actually make the software trusted. You still have to trust the software to follow the access control policy. This is type-based information flow control. In other words, the type is changed. So instead of the type being a key, instead now the type is a key bundled with an attached label. You can see the upper label is R cross or Red Cross. The lower label is evil for evil.com. So this is signifying the information should only go to the proper destination. If this works, then the illegal flows that we don't want to happen, the breaches of confidentiality that developers have to trust won't happen, are automatically prevented. And this would reduce the trusted computing base down from the entire 1 million lines of Servo down to just the networking segment, down to a much smaller, much easier, much more practical to audit segment of the code. Now, there's a practical problem with this, which is that information flow control doesn't apply to unmodified languages in most work. However, I did very pointedly say most work, and there's a reason for that, which is my next slide. Last year, I presented, along with my fellow authors, the work Cocoon at OOPSLA. Cocoon prevented static information flow control in an off-the-shelf language and compiler, which is Rust. So, okay, this kind of leaves the obvious question, why am I here now? We solved this last year, didn't we? Well, unfortunately, Cocoon had a couple of significant limitations to it that required addressing. First is that Cocoon was only static. It could not do dynamic information flow control. So in the example that we discussed, where you have Google and Amazon and all these other tabs, Cocoon couldn't handle that. which means Servo couldn't actually have this policy enforced that developers would feasibly, theoretically, like to have enforced. And in addition, Cocoon had a very limited evaluation. The evaluation was closer to a proof of concept than a complete, thorough, comprehensive one. And if I'm trying to argue for practical information flow control, I need a real evaluation. If a developer wants to trust that information flow control is practical, they need to know there's good evaluation, there's good tests behind this. Our solution is Carapace. Carapace provides exactly the same benefits as Cocoon and more. It still provides static information flow control. If there's a compile time known policy that can be enforced, Carapace can enforce it at compile time. It is still off-the-shelf language and compiler for Rust, and in addition it adds dynamic information flow control so it can handle runtime policies, and it provides a thorough, comprehensive evaluation. Now, part of evaluation is metrics, which I will get to in a moment, but part of evaluation is also that we could do what we said we did. In particular, Cocoon and Carapace both had a relatively challenging programming model. So how feasible is it to really use this, to use this in real programs, not just contrived toy programs that maybe we wrote? So we wanted to retrofit real practical programs and change them to use Carapace. So what did this retrofitting process look like? This is what it looked like. The start is to bootstrap with Carapace. For a quick bit of background, Carapace is implemented as a Rust library. So for a developer to use Carapace, they would import the library, change the types to be protected, and then enter the middle block here. In the middle block, the developer would fix compiler errors using three things, which I'll cover in the next slide: secure blocks, wraps, and unwraps. Fixing the errors using these would lead to more errors as the information flowed down, if you will. Fixing these would lead to more errors, more errors, more errors, and repeatedly until eventually, hopefully, the developer would be done. Now, as you may be able to tell, that middle block covers a lot. So what exactly does this look like in practice? This is a real example of code from Servo. This is pulled directly from Servo, no changes, no modifications to it yet. It computes the length of a secret UTF-8 and UTF-16 string. The string is text, highlighted in bold there. And in our particular flow of information, the flow that we wanted to have, text should be a protected secret. It shouldn't be legible, it should be confidential. Because it's secret, that means its data would also flow into this UTF-8 lin value, which means it should also be secret as well. We, in retrofitting Servo, wanted to make this use Carapace, so we needed to meet these constraints. We needed to somehow make this work. The first step is to put it inside a secure block. Secure blocks are the only places that protected values can be accessed, as enforced by Carapace itself. If a developer marks a value as protected, it can't be accessed anywhere except a block, as enforced by Carapace. The code won't compile. Carapace enforces this using Rust macros. Developers need to, when doing this, provide what labels they want the block to have, or in other words, what labels the associated data that they're allowed to read are. Labels are in two flavors, static and dynamic. Static labels come as types in Rust, and dynamic labels come as expressions, which will be evaluated at runtime so that they can then be analyzed and runtime policies can be enforced. So the first step is this, just add the block. The second step is using unwrap and wrap. These kind of do what they sound like they do. Unwrap removes protection from something so that it can be accessed in red. Wrap rewraps it, reprotects it so it can be treated as protected and secure and continue to flow through the program properly as developers and as we desire. Now, developers have to add these changes. They have to add blocks, they have to add unwraps, they have to add wraps. But notably, without these changes, there will not be a violation of information flow control, there will not be a violation of confidentiality, the code won't compile. So developers have to make these changes, but the guarantees are enforced by Carapace regardless of what the developers do. The developers will either produce a secure program or the code won't compile. No insecure program will be produced. Now, We just covered the retrofitting. So what did we retrofit? We retrofitted 3 real-world programs. All of these are programs that we did not write, that we found on GitHub. They are publicly accessible and able to be checked out yourself. The first is Servo, which, as I described, is a web browser and rendering engine. As of the time of creating this presentation, it was one of the top 30 projects on top 30 Rust projects on GitHub as ranked by stars. For this one, we enforced the policy of when a user types a key, it should only go to the tab they typed that key into. It's the policy that the motivating example showed of if you type in your credit card information, it should only go to the website you typed it into. Avail is a calendar availability finder, or in other words, you have 2 calendars, you want to find what's a shared time where there's an open slot here. The policy here was only the shared time should be made public, the entire calendar should not be made public. And finally is an active online multiplayer game called MK48.io. It's a little ship combat game. You steer your ship around and fire missiles at other ships and so on. The policy here was you should only be able to control your own ship. A malicious player should not be able to take over someone else's ship and, I don't know, crash it into an island or something. Now, as I said, part of evaluation is that we could do this. Well, we did this. All of these policies were enforced, all of them used Carapace, and all of them worked. So now, on to the numbers. There are 2 particular numbers that we presented. Changed code we presented because it represents roughly how much we had to write and change in order to do this, so it represents, to a certain extent, effort as a rough indication. For all of these, as you can see, changed code is under 3%. For a larger program like Servo, it is in fact very low at 0.3% of the million lines. And then for all of them, we also measured runtime overhead. And for all of them, runtime overhead was undetectable. More results presented in the paper in more details. But in conclusion, Carapace provides practical information flow control and demonstrates its use in retrofitting real-world Rust programs. Thank you.
We have a couple of minutes for questions.
Hey, thank you. Very nice talk. I wanted to, maybe I didn't understand exactly. So how do you know that the policy was enforced, in the sense that how do you know that it prevented a bug that was possible in the first place?
I'm sorry, repeat the second half of that. I caught, how do you know that the policy was enforced?
Yes, how do you know that the policy was enforced?
Yes, so let me go to the right slot. So here, as you can see, the block here, this is you can see the exclamation point there at the end of the first line. This is a macro. Carapace defines a set of macros that will transform the code inside the blocks, essentially. As part of that, there are type checks, there are runtime checks. It will add in various checks to enforce it, make sure it happens. So all the checks will be enforced. All the constraints will be enforced via checks. The checks just aren't ones the developers write. They're automatically generated by Carapace itself.
Thank you very much.
Had mostly the same question, but I guess as another one, it seems like some of the changes, like wrap, unwrap, kind of painful, but also could be automated.
Kind of painful, could be what?
Automated? Like if it's a secret block and the secret variable always has to be unwrapped to be accessed, why doesn't the macro do it for me?
Yes. Long story short, my lab mate has actually been working on that somewhat recently. One of the things he's run into is, in particular, in figuring out where to add where to define the edges of the block. He found that it was relatively tricky to figure out how to do that because, to a large extent, where do you define the start, where do you find the end? For a human, it's pretty intuitive, it's pretty straightforward. In automatic synthesis, he found that it was quite challenging for computers to do in a way that generated workable code.
Can I ask another one? Do you do anything with like declassification at all?
Yes, I omitted it from the slides because of time, but yes, declassification is provided for. We provided a trusted block instead that has to be audited, but that's how you would do declassification.
Let's thank Vincent again. Next up, Andrew will present from linearity to borrowing. Please go ahead.
Hi everyone, can you hear me? Okay, great. Thanks for sticking around to the last session. You're almost there. I'm Andrew, I'm a student of Amal's at Northeastern, and this is joint work with my lab mates Oleg, Brianna, and John. Some of us are here, so come find us at the end if you have questions. Seeing as this is the Rust session, I feel I should start with a quick disclaimer that this is not actually a Rust talk per se, at least not really. I'll allude to Rust here and there, and of course it's related, but I want to be clear that our goal in this work was not to actually formalize Rust. Instead, it was specifically to disentangle borrowing as a language feature from the intricacies of Rust. And specifically, we wanted to ask how we could develop it as a feature that evolves from relaxing some of the restrictions of linearity. So in particular, we developed a lightweight borrowing extension for the linear lambda calculus. And by lightweight here, I mean first that we expose borrowing as this sort of safe API that's implemented using underlying untyped terms, rather than extending it with new syntax and operational semantics. And second, it sort of preserves the character of linear typing. It doesn't fundamentally change the way that the whole type system works, but rather the changes are mostly localized to the specific rules that involve borrowing. And in the paper, we tease apart borrowing into a sequence of distinct features in an almost pedagogical way, starting from standard linear references and then incrementally motivating and developing different borrowing extensions, starting with immutable borrows, then lexical lifetimes, then mutable borrows, and finally reborrowing. And we don't just consider linear typing in this work. We also work out how to incorporate borrowing into standard linear separation logic and also its semantic model. Our soundness proof is layered across these three levels, and we prove the type system sound with respect to separation logic with new abstractions for borrowing, and then we prove the logic sound with respect to a model that guarantees memory safety, leak freedom, and termination. And these last two levels allow us to validate some amount of unsafe code that can't otherwise be type checked, which we use to validate the implementation of that borrowing API that I mentioned earlier. And at each of these levels, we start with the sort of standard linear presentation and show how to adapt it for borrowing. And so our first stop is the type system. And before we get to the borrow checking part, we're just going to go back to basics and review the linear references. Okay? So we start with a standard linear lambda calculus with references that are manually managed using alloc and free. You can sort of think about these like box T's, except we care about leak freedom, so there's nothing like box leak. Now, the role of linearity in this calculus is twofold. First, to ensure that references aren't leaked. The type system doesn't support weakening, which means that you can't arbitrarily forget about variables that are in scope. This usually manifests in the type system as axioms being precise about exactly which variables they use, as you can see in the variable and unit rules here. Second, to ensure that references aren't used after they're freed, the type system doesn't support contraction, which means that you can't arbitrarily duplicate variables. This is sort of like the use of moved value error that you sometimes see in Rust, and it manifests in the type system as context being split between different sub-expressions, as is the case for the components in the pair rule. But linear references can be painful to work with because they need to be threaded around in this capability passing style. And also sometimes we really just want sharing. So this is where borrowing comes in. And before we actually see the rules, I just want to emphasize that when we level up to immutable borrows, we're building on everything from the previous level. In particular, the judgment is going to be the exact same. We're still using regular old context splitting and so on, which means that any intuition you may have about how linearity helps us manage resources still applies. And the changes that we're going to introduce for borrowing is going to be local to the rules that actually manipulate borrows. So we start by adding a new type in T for immutable borrows, along with axioms for explicitly duplicating and forgetting them, which sort of lets us circumvent the usual restrictions of linearity. In exchange, though, the borrowing interface will not provide all the rules that you would get for regular references. It's weaker, so for example, you cannot free an immutable reference. To actually introduce immutable borrows, the borrowing interface provides this with bar function. It takes an owned ref T1, passes it as an MT1 to some computation that's going to produce a T2, and at the end, it finally pairs the result back with renewed ownership of the original reference. Now, it would be dangerous for the resulting T2 to hold on to any copies of this borrow, since then they would be aliasing the owned reference. So in order to prevent this, the computation has to be guarded with this outlives modality, which we write with a box. In its intro rule, the outlives modality, box T, filters out inhabitants of T that use borrows by requiring that all borrows in context outlive all borrows, which for now just means that we can be sure they don't close over any borrows themselves. Unlike the rules on the previous slide, this one actually can't be written as an axiom because it needs to inspect the context, but we're still not going to grow the term language because the outlives modality is a purely static concept. It doesn't have any runtime significance. It can be completely erased. That's why you see the same E above and below the bar. Now, to elaborate on this outlive side condition a little bit more, it uses this judgment T outlives M for each T in context, and I'll show a couple of rules here. For example, base types like unit, they will outlive all borrows because they don't have any. Compound value types like ref or pair, they just inherit the property from their constituents. The interesting one is that the outlives modality itself outlives all borrows by construction, since that's exactly the property that the intro rule checks. On the other hand, an im obviously has a borrow in it, and a bare function might close over a borrow, so neither of these get rules. If you want to return a function from with bar, it has to be explicitly guarded with this outlives modality. But if you've ever used Rust, it probably feels like outliving all borrows is a little strict. So in level 2, we're going to distinguish between different borrows using lifetimes, which effectively tag borrows with these fresh names that are ordered according to when they're introduced. In this level, we do need to generalize the judgment slightly in order to keep track of this lifetime ordering in a new context delta. But most of the type system, and indeed the entirety of the standard linear fragment, pass this context round completely opaquely, and it's unrestricted, so there's no funny business there. We'll generalize the with bar rule so that the borrowing computation takes in a fresh lifetime A that's shorter than all others in scope, delta, and then we index both im and this outlives modality by the new lifetime A, so that results that use older borrows are permissible to return from this computation. To actually introduce this new index version of the outlives modality, the side condition now only requires that all types in context outlive A specifically, rather than all types indiscriminately. And the underlying judgment is now T outlives A given lifetimes in delta, which means that we actually can add a rule for ims now whose index B outlives A, and we conclude this just by looking up the relevant ordering information in the context delta. In the interest of time, I'm going to have to refer you to the paper for levels 3 and 4, which are mutable borrows and reborrowing, but for now I want to move on to the separation logic. So just as with typing, we're going to start with a standard linear separation logic and adapt it for borrowing. If you know only one thing about separation logic, it's probably the frame rule. It says that given ownership of P1 and Q separately, if we can run E to a result that satisfies P2 while temporarily ignoring or framing away P1, then after E we can reclaim ownership of P1 separately from P2. And I hope that this sounds at least a little familiar because it's almost like with bar. Here I'm showing a simplified version of with bar for mutable borrows, but I'm highlighting and subscripting related components in the two rules. You'll notice the only part that's different is that this mute AT1 in with bar doesn't have an analog in the frame rule. Whereas the frame rule completely ignores or frames away ownership for the duration of a computation, with bar instead gives weaker access in the form of a borrow. But we can just reflect with bar into the logic, giving rise to a new borrowing variant of the frame rule. Like the frame rule, it starts with ownership of P1, specifically associated at a location L in this case, and it temporarily borrows it for the duration of E before reinstating full ownership when E is finished. Unlike the frame rule, the premise will get limited access to P1 in the form of a mutable invariant, which will allow us to, in the form of a mutable invariant, which ensures that P1 at L will still hold when the computation is done. As in the typing rule, this is all going to occur under a fresh lifetime A, and we reflect the outlives modality in the logic as well to prevent escape in the same way as we do in with bar. I mentioned in the beginning that axioms like with bar are implemented using underlying untyped terms and then validated using the logic, and indeed the implementation of with bar is validated using this bar frame rule. I also mentioned in the beginning that the logic can be used to validate a subset of unsafe code, and it admits this rule, which is almost like the dual of the borrow frame rule, which allows us to temporarily break and reestablish this mutable invariant over the course of a computation. And the important distinct relationship between these is that the borrow frame rule has ownership on the bottom and borrowing on top, whereas in the borrow anti-frame rule, we have borrowing on bottom and ownership on top. And the names of these rules are inspired by some really great work by Chargareau and Poitier, which I encourage you to read. So the paper goes into much more of the logic, including how we use it to specify a logical relation for the type system, and we use it to prove semantic type soundness. But in the time remaining, I want to just cover out a few interesting aspects of the semantic model. So in standard models of linear types or linear separation logic, resources, which we'll call rho, are usually heap fragments or heaplets, which are composed using disjoint union, reflecting that a ref t or an L points to V represents this sort of disjoint or exclusive ownership. In our model, we do have one kind of reference like that, an owned ref, like in ref t. That's fully exclusive, and it allows arbitrary strong updates like freeing. So we write this in the usual separation logic way, L maps to a single value V. But mutable borrows are different. Being mutable, they're somewhat exclusive, but only temporarily, and the borrow will place limits on what states the reference is allowed to take on. Just like in models of mutable references, then, L maps not to a single value V, but to a set of states that sort of represents the range of legal updates. Finally, immutable borrows are different than the other two in that they're shared. They can't be updated. So L maps to a single state, but a confusing aspect is that this state might itself contain exclusive references if you have a mute or a ref that's nested under an im. This is a really subtle aspect of the model, since exclusivity becomes this sort of context-sensitive property. A ref or a mute, it might be exclusive, but only if it's not dominated by an im somewhere. In standard models of linear types or linear separation logic, they often bake in the frame rule by requiring reduction to preserve arbitrary frames. In particular, if E runs safely with the resource rho, then it should also run with and preserve arbitrary frames, rho f, which is joined on using the composition operator dot here. In our model, this condition is necessary, but it's not sufficient. And just to give you some quick intuition for why, suppose we have a mutable borrow at LA of an optional mutable borrow, which happens to be some LB initially. It is legal to update LA to none, but doing so shouldn't allow the borrow at LB to end prematurely. Since mutable borrows are exclusive, this won't actually be enforced by frame preservation on its own because no compatible frame can have LB if LA had it initially. There's a lot of details here about this in the paper. For now, the gist is that we have to add a stronger condition, which is sort of baking in the borrow frame rule in the same way that frame preservation bakes in the regular frame rule. I just want to say one more quick thing about the model. Typically, standard models of linear types or total correctness separation logic can be used to show termination. But remember I said earlier that mutable borrows are a lot like mutable references. And it's well known that models of mutable references have this circularity in their definition that usually requires some sort of stratification to break. Ever since Amal's thesis, the standard way to do this is using step indexing. But step indexing doesn't play so nicely with liveness properties like termination. Thankfully, mutable borrows are like mutable references, but they have a little bit more structure. In particular, whenever we have nested references, mute A, mute BT, we have this relationship sort of for free that B must outlive A, and we're able to use this to stratify our model by lifetimes instead of by steps, which helps us prove termination. So that probably felt like an avalanche of information. I still encourage you to check out the paper, which goes much, much slower and develops each of these concepts from first principles. So thank you so much for your time, and I look forward to hearing from you.
We could take a super quick question while the laptops are being swapped.
This looks really cool. I like the idea of sort of building on linear types. We tried to do something similar in Granule with like some kind of version, but it looks quite different. Is there some way of describing very succinctly the differences in approaches?
Yeah, I mean, I think that just the biggest difference is where we started from. Are you talking about functional ownership, fractional uniqueness, that one? Yeah, I mean, so in that one, you've got like the more information in the context, right? There's like the semi-ring stuff, if I'm remembering correctly. So here we don't have any more structure in the context besides regular old context splitting. It was just a different foundation, that's all.
You can sort of do it with less stuff, basically.
Effectively, yeah.
Cool.
We'll have to move on to the next talk. Thank you very much again. So Jacob is going to talk to us about garbage collection for Rust, the finalizer frontier. Please go ahead.
Thank you. Hi, everyone. So I'm going to present some work that I've been doing with Lawrence Tratt over at KCL. I understand that this is perhaps a bit of a controversial subject in Rust. Many of the Rust programmers in the room here might be wondering, why on earth do we even want garbage collection in Rust? And even that part of the selling point of Rust is that it doesn't even have garbage collection, right? This is slimmed down, you don't want it. But what I'd like to show really in the next 10 minutes is that when you get to the edge of the ownership model, you end up in this place where there are certain data structures that are very difficult to express. And Rust programmers will probably be aware of this in that when they want to deal with things like cyclic data structures, they end up writing either reference-counted data structures, or they use arenas or some sort. And what I'd like to show really is that another thing that can fit in here is garbage collection as a sort of opt-in tracing GC for particular areas of memory that you'd like to manage. And not only is it possible, but it can be done in a pretty ergonomic way that a lot of Rust programmers will be familiar with if they use things like the standard library's reference counting. But also that we can kind of address some classical GC problems this way because of Rust's unique type system. The title is a bit of a spoiler, but these are really to do with finalization. And I'm going to go over hopefully one or two little examples of how this will work. But it's probably best to start with a little demo. So I'm going to make this a bit bigger so people can see it. Is that okay? Everyone see this? Yeah, great. Okay, so what's going on here really is that we've got this small graph and it's managed by reference counting. So we've got this cyclic data structure, we have this node and a next pointer, and that next pointer is using an enum to determine whether it's a weak or a strong reference. Of course, this is reference counting, so the back edge needs to be represented using a weak pointer. So we construct these nodes, we link them together, we make sure that we downgrade to a weak pointer for the back edge. And that means that if we want to go and traverse around this, then we have to do this sort of boilerplate dance, really, to determine, well, is this a strong pointer, is this a weak pointer? And if it's weak, we need to deal with it in some way. And you can see that this is a bit of a sort of trivial example, but if you blow this up to graph-like data structures that are pretty large, this gets a little bit unwieldy to deal with. So what I'm going to show you now on the other side is, I'm going to make this a little smaller so you can see them both together. This is how you would do the same in GC. So this is, the GC that we've written here is called Alloy, and Alloy provides a GC smart pointer type, a bit like the RC type. And you can see it's very similar here in that you construct your graph just using this GC type. You link the nodes together. Notice there's no weak pointers for this. Everything can be a strong pointer because it's using tracing GC under the hood. And there's a couple of key differences, really. So the first is that you don't clone the reference counted pointers anymore because there's no need to incref or decref. And that means that there's no need for a drop method to do the decref at the end when that goes out of lexical scope. What I have shown here is a little drop method that just prints what's happening for the node here. And because this is GC, this will be run as a finalizer when that's unreachable. So what we have here really is context-dependent drops. So if they're used inside a GC, then those drop methods will run as finalizers. Otherwise, they're used sort of as your regular Rust-style destructors. And because tracing GC makes this stuff quite a lot easier, or more ergonomic to write, there's definitely like prior art that has explored this space quite well and come up with some really cool ideas. What I want to hopefully show you really is why Alloy, our GC, is a little different. And I go over 3 main points that kind of show this. And the first really is that Alloy is a conservative garbage collector. So unlike the others, which try in some way to provide an API for the user to precisely identify the root sets for GC, Alloy takes the opposite approach of saying, well, if something looks like it could be a pointer, then we'll treat it as such. And this has obviously the downside that it could over-approximate the root set in some way. The reason that we do this is that precise GC usually requires some restrictions on what you're allowed to use that garbage collected type for, right? So what we noticed is that you're either restricted in what you can GC or when you can run the GC, or you end up having to limit your Rust program as a whole to use a sort of subset of the safe language. That sounds a bit abstract, so here's a very simple example. What we have here is a simple pointer to, a reference to unsigned integer cast. So essentially what we're doing really is we're stripping away the provenance of that pointer. This is not ideal. We don't really want to be doing this, but this is possible to do in safe Rust code, right? And in safe Rust code, it only becomes unsafe when later on you want to go and dereference that. So why does this matter for a GC? Well, the GC needs to be able to know exactly where those pointers are at some arbitrary point in time. It's not actually just when you access that pointer in the mutator at some point. The GC is now this sort of thing running in the background that our Rust application never knew about. So this is something that we've got to deal with. And some of you might be aware that there are lints in recent versions of Rust that actually track strict provenance. So they don't really allow this, or rather they tell you not to do this. It's still possible to do. But even if we were to solve that, there's some other issues in the language where this becomes problematic. But also, Rust, the compiler, the toolchain, is an uncooperative environment for GC, right? So if you have this precise bookkeeping information that you're tracking, the compiler doesn't know about it, and you have to go through and somehow change your optimization phases to make it aware of this in some way, which is not really a small task. I should also mention, rather, that there are issues with conservative GC itself, and yes, you do have to restrict some parts of what the language can do too. The main thing really is that you can't obfuscate those pointers in any way. So that precludes things like XOR lists from being written in GC with, a Rust program with Alloy. But what we sort of found empirically is that the restriction that this imposes is less burdensome than perhaps some of the others that would be required for precise GC, especially because some of the things that you see in the standard library are things or are sort of patterns in Rust that the precise GC approaches would not be able to handle. So moving on really from conservative collection, Alloy was designed to be retrofit to existing programs, right? Conservative collection makes this a lot easier because it reduces the API service that needs to change. But there's a couple of other things. So I mentioned earlier that what we do is we take existing drop methods, turn them into finalizers when we can. And by doing this, we were able to take some mature existing Rust programs and convert them to use GC. So these programs here all in some way had reference counting for various parts of their internals, and we've replaced those where we could with garbage collection. Now what I should say is that in some of those it wasn't possible to do a whole translation because they relied on the semantics of reference counting that was not possible with GC. But for the most part where we could, we were able to convert them. And what we show here is just sort of one of quite a few experiments we did. And I'm just trying to highlight here really that on average, if we use the average heap, that comes with Alloy, then you're looking at around about 10% slowdown and maybe 1 to 2x of the memory consumption. Obviously, we do allow you to set a minimum and maximum heap, so you can change this calculus somewhat, but this is with the defaults that sort of grow and shrink as necessary. And finally, finalization. So I did allude to this earlier. This is the main issue that we found when we were dealing with this, this conversion. But one of the things to know is that in Rust, what could be a safe drop method, i.e. what could be safe to do at the end of a lexical scope, is not necessarily something that's safe to do at some arbitrary point in the future as part of a finalization of an object. And a lot of the cases that we found around this were to do with, in some way you have a reference that's managed to linger for longer than the object has stayed alive. And because with our GC, we want to say to people, if you use it in safe Rust code, you get a safe GC. Finalization is a sort of backdoor to break these safety guarantees. And so we needed to address these in some way. And we did this using something called finalizer safety analysis. And essentially what this is a static analysis pass that we added to the Rust compiler that looks at the control flow graph of the intermediate language. And for every drop method, we check, is this doing something that would be dangerous in a finalizer? And so there's quite a few different possibilities where that could be the case. But in general, what we found is that even though this over-approximates, we're able to get quite granular to be usable in real programs. And where it's not, the user can say, here's an escape hatch, I know what I'm doing, let me do what I want to do, please. So in the interest of time, we've only got a couple of minutes left, but I do want to just quickly show you how this might look. So here's a simplified version of the code I showed you earlier. I've just removed a couple of the nodes and some of the types in between because I don't want to kind of overload you with different error messages. But what we have here is something that could potentially be unsafe, because in this drop method for the node, we're dereferencing through to another garbage collected object. And because we say we're allowed to garbage collect through cycles, well, that could have been finalized ahead of time, right? Oh, sorry, before we get to this finalizer. So that's got the potential for unsoundness there. And so if I compile that, you see finalizer safety analysis has shown you an error, and it said, we're not going to run this program because this does something that might be bad. But what happens if you want the drop method to work as you would in your existing program? Lots of these drop methods would have been written in applications that never thought that GC would be used in the future. So if we remove any usage of those types from GC, what have I done here? Oh, I need to remove the call as well. This will compile fine because finalizer safety analysis only kicks in on types that are used in a GC in some way. The other thing as well I'll note is that if I put these back in, if we remove the problematic line and try and compile this again, this will work too. This will also traverse through function calls to a fixed point, because at the point that we do this, you have like a whole program analysis. Obviously with things like externally linked stuff, this is not possible, but for the most part we get pretty close. As I said, there's a lot of other things that can do which we don't have time to discuss, but they're in the paper if you're interested. Yeah, if you want to talk about those things, come and see me. I'm more than happy to speak about them. I'm also going to be really shameless here and say that my postdoc is coming to an end. So I'm on the job market. If you need a compiler hacker, please hire me. Thank you.
We have time for a quick couple of questions.
So it looks a little bit like the drop check issues that you have in the past. So I guess the Rust has in the past. So I guess I have two sort of related questions, which should be pretty quick. The first is, what is your analysis doing in the case of polymorphic types?
Yep.
And the second is, do you have any interaction with, for example, made angle attributes? Can I take something which wouldn't be a safe finalizer, I put made angle on there, and your analysis considers that?
With regards to your first question, where possible, we try and monomorphize those types.
Mm-hmm.
So this obviously can kind of have this like exponential blow up. So we have a sort of fixed point where we say we won't go further and we'll disallow this at this point. Sorry, what was your second question again?
The question was, does your analysis have any interaction with made angle attributes?
Yeah, so made angle attributes obviously create some trickiness around drop methods that our analysis looks at and says this needs to be manually verified by the programmer themselves. So no, we don't deal with that. It's up to it. We haven't really explored whether that's a space that's possible yet or not. But yeah, that's what we've got.
Thanks.
Cheers.
Okay, thank you again. For our last talk, Zach will present Place Capability Graphs, a general purpose model of Rust's ownership and borrowing guarantees. Please.
Thank you. Okay, so first I'd like to mention that this is joint work between collaborators at University of British Columbia, ETH Zurich, and NYU. Rust type system is special. One of the things that makes it special is that it tracks the notion of ownership. So values in a Rust program are owned by places, assignments transfer this ownership from one place to another, and by default, these values can only be directly accessed by the places that own them. But as we've seen before, programming exclusively in this style can be quite restrictive, so the Rust allows for borrowing. And this borrowing transfers this ownership from one place to another temporarily. And this is tracked by the type system. So while a place is borrowed, the type system places restrictions on how it can be used. So these features of the Rust type system make it more restrictive. But we are willing to abide by these restrictions in order to obtain guarantees about our program. Perhaps the most famous guarantee is that if we operate within these constraints, the Rust compiler will ensure that our programs are memory safe. But there is another important but less obvious benefit of this, which is that these type system restrictions facilitate reasoning. And in particular, they enable modular reasoning. So what I mean by modular reasoning is the ability to verify properties about a Rust program just by looking at individual functions in isolation. So for example, we can tell that this assertion will always hold in a Rust program regardless of concurrency or how f is called. The reason we know this is that the Rust type system ensures, amongst other things, that callers of f will pass in distinct references for x and y, so the second assignment cannot change the target of x, and the assertion will always hold. So Rust developers often reason informally in this way, and we would like our analysis tools to be able to do this kind of reasoning too. In order to do that, an analysis tool will require a model of Rust ownership and borrowing in order to take advantage of these guarantees. And a model is like a data structure that explains the borrowing of the program, and the development of such a model is the focus of this work. So now imagine that you are building a Rust analysis. You'll probably need some model, and your choices at this point are either to make your own model for the purpose of your analysis, or perhaps take an existing off-the-shelf model. So if you try the first approach, you'll probably realize that this is not easy. For example, your analysis might be concerned with when a particular borrow in the program expires. And this is challenging because there's no information on the surface that provides this. There's no, say, like syntactic annotation indicating when x expires. And to answer such questions in general would require your model to be about as precise as the Rust compiler itself. So that's probably not a good idea. Instead, maybe you try a general purpose model. And the good news is that there are many existing models of Rust. And the bad news is that they all aim to capture different aspects of the type system. So then you would need to decide which, if any, of these analysis tools would be suitable. So let's take a look at what analysis tools want to see in a Rust model. And by analysis, I'm speaking somewhat broadly to also include program verifiers. So many of these tools want to take advantage of the modular reasoning guarantees provided by the type system. And in order to do that, they need a model that can summarize borrowing across functions and loops. And preferably, we would like this to be automatic. Second, we would like a model to have a close connection to the Rust compiler's internal representation. So this might seem like it's a implementation detail, but it's actually important for a more fundamental reason. And that is that the Rust language does not have a formal semantics. So the closest thing we have to the formal semantics of Rust is whatever the compiler decides to do. But another reason is that Rust compiler has designed very nice intermediate representations. Analysis tools like to use these, and being able to use the same representation for the model and the analysis without having to do translation reduces places where soundness could get introduced, or unsoundness could be introduced rather, sorry. Finally, we would like the model to be able to reason about sets of borrows. So in Rust, you can have like individual borrows, but users can also define data types that contain sets of borrows inside of them. And the type system tracks these in kind of interesting ways. So for example, all of these different fields contain sets of borrows under the same lifetime, but the type system ensures that these will all be distinct sets of borrows. And your analysis tool might want to take advantage of this, so the model should reflect that. And so prior to our work, there was no model that could satisfy these three properties. So now I'll introduce our model, which we call place capability graphs, and I'll call PCGs for short. So it creates these modular summaries by taking the results from the borrow checker after the type checking of the program. It connects to Rust internal representation by capturing notions of ownership and borrowing analogously to the Rust compiler itself. And it's able to reason about sets of borrows via a novel construct that we call lifetime projections. Now I'll give an overview of the model. So our PCG analysis takes a function as input and computes this data structure for each program point. And we call our data structure place capability graphs because it associates places, which are roughly memory locations, with capabilities. And these capabilities describe what the compiler thinks can be done on these places at a particular point. Now, we chose the capabilities ourselves, but they correspond naturally to restrictions that arise on places from the type system. Nodes in the PCG describe memory locations, so these can be either places or these lifetime projection nodes that store a set of borrows stored under a place. Finally, edges in the PCG denote temporary transfer of capabilities. So for example, when a borrow is created in the program, an edge is introduced that describes the temporary transfer of ownership from the borrowed place to the borrower. We use unpack edges to split structs into smaller pieces so that you can move out individual components. Abstraction edges are used to summarize borrowing across function calls and loops. And there's other edges that are described in the paper. I want to highlight a couple other features of our analysis. So we track path-sensitive information about borrows created under different control flow paths. So this could be useful for, say, program verifiers that want to care about path-sensitive aliasing. In addition to producing these graphs, our analysis also generates annotations. And so these annotations roughly correspond to the actions taken to update the graphs through the course of the program. And tools can consume these annotations, for example, to generate memory safety proofs. Finally, our model supports many advanced use cases of borrowing, including operations on nested references. So when I say nested references, I mean references that store objects that they themselves store other references. And it turns out that reasoning modularly about operations on these nested references can be quite challenging. So in the paper, we described the features of our model that allow us to support that. Moving on to evaluation, we wanted to look at 3 different aspects of our model. So first, we wanted to see how much real-world Rust code we could support. Second, we wanted to see the extent to which we captured these ideas that we intended to, which is restrictions imposed by the Rust type system. And finally, we wanted to see the extent to which we could integrate our model into real tools. So to answer the first question, we went to crates.io and got the top 500 most popular crates and performed our analysis on every function on the crates to generate models. And our results were quite nice. We were able to generate models for almost all of the functions. About 2% we couldn't generate models for because they use features like raw pointers and line assembly that our model doesn't currently aim to support. And for a very small amount, we think we can resolve those with some more engineering work. Now, for the second question, we wanted to see that our PCGs were faithfully reflecting the constraints that the type system imposes. And so namely, if in the graph a place is lacking some capability, that means the compiler should prevent this place from being used in some way. So to evaluate this, we took a mutation testing approach where we would use our analysis to systematically generate programs that don't type check. So we would take a function from our corpus of functions from the 500 crates, generate a PCG at some point in it, identify a place lacking a capability. So here, the PCG is indicating that at line 3, vec does not have a capability because it's being borrowed. Then we would systematically generate a program that violates this constraint here by moving out of vec while it's borrowed. And then we would send this program to the compiler and confirm, verify that the compiler rejects it. And this works nicely for us. We generated 7 million mutants, and almost all of them got rejected. And if you're curious about the 0.01%, feel free to ask after the talk. Finally, we wanted to look at the extent to which we could integrate our model into real analysis tools. So we looked at 2 tools. First is Prousty, another project that we're working on. This is a deductive program verifier for Rust, and as part of its verification, it synthesizes a memory safety proof in Viper. Now, previously, this was done via an ad hoc analysis that could capture simple borrowing patterns, but didn't support a lot of real-world patterns like borrowing across loops and structures holding references. So we got rid of that and instead put the PCG in and had the Prousty implementation synthesize memory safety proofs just by reading off these annotations. And this allowed us to simplify the code base of Prousty and at the same time enable it to support more Rust code. The second tool we looked at was Flowistry. So this is a much different type of tool. It's an information flow analysis tool. And Will Crichton, the creator, had actually recommended this to us because he mentioned that internally it's using this ad hoc alias analysis to compute some results. So we took that out and had created a fork of Flowistry that instead queried the PCG. And as a proof of concept, this was successful. The behavior was equivalent to the original, and it passed the test suite. Now, what I want to highlight is that in both of these cases, the integration with the PCG was quite easy. All that the tools had to do was basically query the PCG API to get this information out, because both of the tools were written in Rust, operated on Mir, so it was a very sort of direct extension. So in conclusion, we've shown that these models are necessary for Rust analysis tools, identified that all of the, or none of the existing models really satisfy all the criteria we would like in general. We developed place capability graphs, which is a model of Rust ownership and borrowing that can satisfy these criteria. And in our evaluation, we showed that our model can support a lot of real-world Rust code and is easy to integrate into existing tools. So if you're building a Rust analysis tool and your tool requires some notion of ownership and borrowing, please try our model. It's available on GitHub. You can include it as a crate in your project. It works. And you can also reach out to us on Zulip. That concludes the talk. Thank you very much.
We have some time for questions.
Thanks for the great talk. How much of the model is, how much of the assumptions, or let's say the invariants of the Rust type system are needed for your model to work? I mean, specifically, if I were to try a different language that allows mutable aliasing, could I use the model to use different capabilities and things would still go through and I could represent things? Or are there sort of like assumptions that things behave the Rust way?
Yeah, that's a great question. For the most part, we keep assumptions minimal and trust the compiler to give us correct information about aliasing. So like, for example, our analysis doesn't require a particular borrow checker implementation. So we query certain borrow checking facts from the compiler, but we don't sort of verify any properties or make any assumptions about them. So I think extending the model to support other languages would be, or extend even other extensions of the Rust type system would be possible, yeah.
Cool, and when you say you extract these from the borrow checker facts, is this like the Polonius implementation and this data log stuff that you end up with the same facts and you turn them into your model?
So we support both the Polonius borrow checker and the current borrow checker because Polonius actually doesn't, or is very slow, so we also support the current borrow checker as well. And you end up getting different graphs for the different borrow checkers in cases where the behavior is actually different.
Cool, thank you very much.
Thank you for a very clear and well-composed talk. When you were saying that you are extracting information from borrow checker, and you were checking whether your borrow checking is complying with the Rust borrow checker. You said you're mutating the programs and then you're running your borrow checker, but how is it possible if the Rust borrow checker will fail on these ones?
Okay, so to be clear, what we're doing is we get the borrow checked program, and then we make a new program that we want to not borrow check. And so we're validating that it actually doesn't borrow check.
Yeah, but how your tool runs if you rely on Rust borrow checker?
So our tool only operates on programs that will borrow check. So we don't attempt to generate graphs for these like mutant programs. For those, all that's done is sending them to the compiler just to make sure that the compiler refuses to compile them.
But how is this testing of your tool and not just testing of Rust-C?
So what we're testing is like the way we're encoding these capabilities are actually reflecting the compiler. So for example, if we were able to make a mutant program and the compiler accepted it, that means there's a restriction in our graph that doesn't actually agree with the compiler. We could talk more after if.
Yeah. Thank you.
Can you give me a sense of how much information you extract from the Rust compiler versus how much information you synthesize? I didn't quite understand whether you were using, say, lifetime information at some point to inform your algorithm or not.
So for loops and function calls, we get all of that from the Rust compiler.
Okay.
For assignments, we basically do that ourselves because assignments are quite easy. And then for like control flow information, this is just from the control flow graph.
Okay, and perhaps I missed this also. Do you have an argument that you will always, you have a more formal argument as to why you are consistent with the Rust borrow checker? Or do you think there might be programs lurking that the borrow checker will accept and that you may fail to justify in PCG?
So based on our like top crates analysis,
okay.
That would give that. Another thing just to mention is that indeed the REST type system, we don't have a formal soundness, but for tools like Prusty that synthesize memory safety proofs, if the memory safety proof goes through, that's a pretty good argument, I suppose.
Yeah, sounds good. Thank you.
Thanks.
Let's thank Zach again. And this is OOPSLA, so congratulations for making it, and I hope you enjoy your evenings.